Welcome to Euron everyone, and welcome to our very first lecture of Deep Learning Masters. Obviously after your roadmap and a welcome lecture. So I believe you must have gone through a roadmap and you must be aware about the roadmap. Now in this lecture, to the point, I'm going to talk about evolution of a deep learning, like why we are talking about deep learning basically. What kind of a problem that we can try to solve, what are the applications that we are using even now in our day-to-day life, which is basically coming from a deep learning, and we'll try to talk a lot about work and the industry with respect to a deep learning in this particular lecture. This is going to be a day 0 introductory lecture for all of you. So let me share my screen everyone, and here, so I have prepared a beautiful slide for all of you obviously, but before that let me talk about basically deep learning from a layman perspective, right? For anyone who is trying to start with the deep learning. So see, we were having a lot of algorithm which was nothing but a simple straight plain mathematics to perform some sort of a probability operation, some sort of a regression operation, and yes, we were able to solve some of the problem. But those algorithm, the machine learning algorithm that we try to say nowadays, so those algorithm can solve a simple problem if data set gets complex, right? If data set gets complex, if things gets complex, so in that case, those algorithm was not sufficient enough to solve those complex problems. For example, understanding an image. Now, image is nothing but a combination of pixels. The screen that you are able to see, right? The screen that you are able to see, the video that you are able to see is nothing but a combination of pixels. So if I have to train my machine to recognize me or recognize any of the text over here, so it is supposed to understand thousands of pixels and a relationship in between, and that too with a lot of data, then only it will be able to recognize. Now, but we as a human, right? We as a human, so we can recognize easily, right? We can recognize easily. Now, same recognition will not be done by child. So if you will follow along from childhood to adulthood, so you will be able to find out that as a child, we were trying to explore, we were trying to learn by looking at something, by hearing out something, by sensing something, by testing something. And as we have grown, so we have learned a lot, right? We as a human have learned a lot, and day by day, so we are learning a lot of things. We are able to digest a lot of information on a regular basis. Technically, we are learning as a human being, and we are even able to learn a complex things, right? So the things which looks complex for a machine, for a human, maybe it doesn't even looks complex, right? I can just see at this particular image, this particular slide, I can recognize that the image is basically a neural network image. Now this is me, I can recognize myself, and then I can recognize all the later, which is, and that too in the easiest possible way, right? So scientists, researcher have started exploring a way, a technique where if they can try to create a kind of a network or kind of a system, so where system will be able to understand something, system can try to find out some pattern in between the data, the way we as a human being try to find out, right? The way we as a human being try to find out. And this is where the concept of deep learning comes into a picture. Because we as a human, so we are very good at finding a pattern. We are very good at observing something. We are very good at even collecting a data, collecting information. So people have started looking for a way, and they said that okay, so the way human learns, maybe I can try to create an exact similar kind of a system even for a machines. And this is where the concept of neural network comes into picture. Now, what is a source for a human being? When we try to learn something, when we try to observe something, so it's our neurons, right? Our entire body is full of neuron, which is connected to our brain, and which is so neurons can take all kind of our data, all kind of our senses, whatever we see. So it can collect all the information, say to the central system, which is our brain. It is going to process it, and then this is something called as learning in case of human. So now scientists have started talking about a artificial neural network, a similar kind of a network like we as a human have. Now, this is where this entire deep learning evolution have started. Now, so in today's world, if I'll talk about AI, so it's a 65% application which has been powered by a deep learning. Now you will say, can you please name one or two application? I can name 10 over here. You must have seen a Dizzy Yatra, right? So when you go through an airport nowadays, you must have seen a Dizzy Yatra. So with the help of Dizzy Yatra, you have just registered your face once in a Dizzy Yatra application, and whenever you go through a gate, automatically it opens up. So basically, automatically system is able to recognize you. So that's a facial identification, a facial recognition system. In many offices nowadays, you must be able to see a facial recognition system, right? Example of a deep learning. And again, inside deep learning, there is a department called as computer vision, example of that. Now, nowadays, you must have seen even on a street, even on a road, that whenever you are going to violate a traffic signal, immediately it will try to take your picture, and it is going to send a challan to you, right? It is going to ask for the fine immediately on your maybe like a registered number or maybe an email ID. Yeah. So again, application of deep learning. So where it is able to recognize your vehicle, it is able to recognize what kind of violation you are trying to do. It is able to extract a number out of your number plate with the help of OCR or ANPR, automatic number plate recognition, and then automatically it is sending a challan to you. So again, one of the amazing application in a day-to-day life, part of computer vision once again, right? Now, Google Translator, we all have used it, right? Example of deep learning. ChatGPT, we all are using it. Example of again deep learning. The generative AI itself is a complete generative AI itself is a part of deep learning, right? So there are tons of application around you, especially in 2025, you will be able to find out which is getting derived from the deep learning. And like I have mentioned over here, 65% of today's AI application has been powered by deep learning. Maybe it's a computer vision, maybe it's a NLP, maybe it's a reinforcement, maybe it's a generative AI application that you are going to build. But yeah, it's coming from a deep learning basically. So just imagine how powerful deep learning is. And again, like I said in the beginning, that so researcher was trying to build something so which can try to mimic a human brain, and that was the evolution of a deep learning. So the way our neurons are connected, the way human being is having a neural network in between. So in the similar manner, we try to talk about a neural network and its relevant concept in deep learning. Yeah, so there are a lot of relevant concepts that we are going to discuss as we will start unfolding the lecture on day 0. I'm not going to take all those names because it will be very difficult for most of us to digest those names. Anyhow, we have to learn. So overall, we have to understand like what is deep learning, right? Now, the market is projected to reach 93.34 billion by 2028 in terms of just a deep learning, right? So industries from healthcare to autonomous vehicle. I think we all are aware about nowadays autonomous vehicle, especially Tesla and others, right? So Tesla is one of the most famous one. I believe we all are aware about it. So it's autonomous car, which can see the lane, which can see everything around the car, and which can take a decision, which can drive itself. Amazing application in a real world. And this is going to be a reality for all the country out there on this planet, right? All the countries. So again, an amazing application of a deep learning. Now, what is deep learning? I believe I have already talked about it. Yeah. So a kind of a training system, a kind of a neural network system. So which will be able to take a data, means the way we as a human try to take the data by looking at something, by sensing something, by testing something, by hearing out something. In the similar manner, we try to provide a different kind of a data to a artificial neural network. It's having its own name as well. It's called as perceptron, right? It's called as perceptron. So to the artificial neural network, we are going to provide a data, and then eventually those artificial neural network is going to learn the pattern. How? That is something that we are going to explore, right? Because this class is all about that how we are going to train a different kind of a network, by the way. So we are going to send the data. We are going to there is something called as multiple layers that we use to connect, and then with a minimum human intervention. So we try to give a capability, we try to train a model which will be able to do some sort of a task, maybe a facial recognition, right? Maybe a pedestrian recognition, maybe a people counting, maybe a particular object in a particular image or a video, maybe a text generation, right? Maybe a language translation, maybe a voice and speech recognition. Yeah, a lot of things over there. So here, previously we were talking about a machine learning a lot, like a decade back, if you'll say, right? A decade back. So obviously we were having a lot of mathematical model, and that falls under machine learning. But here we have started talking about deep learning nowadays a lot. So just a simple comparison. So here machine learning is nothing but, again, a bunch of algorithm, a collection of algorithm, or a collection of mathematical model, or like I could say mathematical equation, which can solve certain problem like a classification, or maybe a regression problem, or maybe some sort of a unsupervised problem. It will be able to work, and it will be able to give you some sort of a good result, right? A good one. But when deep learning comes into a picture, so whenever and wherever you have a very, very complex relation between the data itself, where machine learning is going to fail, then deep learning comes into a picture, and that is going to help you out in terms of solving the problem, right? For example, maybe like language translation, it's one of the complex tasks, right? Facial recognition, it's one of the complex tasks. Object detection, it's one of the complex tasks, right? Machine learning can't do it. Means it can do it, but with the worst of worst. So we have a deep learning. We have a lot of algorithm inside it, right? That we are going to explore. Now, so if I'll talk about like a basic of deep learning, like I said, that it's been inspired by a human brain, right? Human brain and the entire human body is having a lot of neurons. All of these neurons are connected to your brain. So it sends a data, right? It sends basically a data, and then it tries to learn the pattern. This is how our entire brain is designed. This is how our entire neural network has been designed, right? So in the similar manner, we are going to create an artificial neural network. So where there will be a input layer. Input layer means a data, right? Where we are going to pass the data. Like for example, for a human being, my input layer is my eyes, my ears, my skin, my tongue, right? My nose can be an input layer for me. And then there will be a hidden layer, there will be an output layer. So hidden layer, so where it will try to learn something, like our brain, right? So it try to learn something, it try to find out some sort of a pattern. That is something called as hidden layer in case of artificial neural network. And a lot of things goes inside that hidden layer. I'm not going to talk about now, but yeah. So in the next lecture onwards, obviously I have to talk about it with a mathematics and with the derivation of it, right? Output layer, which is going to give you the final output. Yeah. So neural network in the real world. So computer vision, a lot of application and example I have shown it to you, right? Self-driven car basically, or maybe a kind of a system which can recognize your face, which you will be able to find out a lot on an airport, in offices, everywhere, right? And again, so kind of a system like a ANPR, automatic number plate recognition system. So all of these things is technically an example of a deep learning and eventually a computer vision. So wherever we deal with images and videos, we say that, okay, it's a part of computer vision. Natural language processing, biggest example is the LLMs that we are dealing with since last two and a half year, right? A lot of LLMs we have seen, ChatGPT we have seen basically a Cloud Sonnet model, Gemini, Llama we have seen, basically Mistral we have seen, a DeepSeek we have seen, Shravan AI we have seen, a lot of models we have seen, right? Which is good at generating a data, which is good at understanding the pattern, generating a mathematics, solving the problems, everything, right? So again, that is coming from the NLP. Translation, sentiment analysis is one of the application, but yeah, the biggest one is LLMs, by the way, which can do all these things. Now, healthcare. So obviously, like in terms of drug discovery, or in terms of analyzing the disease, or in terms of even going through the scans, deep learning is lethal, right? Computer vision or deep learning is lethal in terms of like it is going to be fast. It is basically like in some of the area, in some of the segment, the kind of a result it is trying to give is amazing, right? It's phenomenal. So the another one is autonomous vehicle. I think nowadays we all know autonomous vehicle is not a fancier stuff which we see just in a Hollywood movies, but autonomous vehicle is something which is a reality, right? Otherwise, we would have like seen this autonomous kind of a vehicle in some of the movies, like movies from Tom Cruise or maybe from someone else. But now it's not that fascinating things. It's a reality. We can see that on a road as well. Yeah. So this is where this thing comes into picture. Now, so when we talk about deep learning, right? So like I said, once we'll do it, we'll know it. But as this is day 0, I think we should know a little bit about something, right? So what is the life cycle of a deep learning? So first of all, obviously, like any other AI stuff, data collection and a preparation. So for example, if I'm trying to build some sort of a computer vision model, right, which can recognize something in images. So obviously I have to collect a lot of images, a lot of variation with a different lighting condition, different angles, or I can say with the different shape and sizes, from near, from far, I have to collect those images. So data collection and then preparation, pre-processing we have to do, which is pretty much like and again, for a different kind of application, this approach is going to be different. It's not going to be same, right? It's not going to be same. And then there are tons of model architecture you will be able to find out. So it depends upon the task. We try to select those model architecture, by the way. For example, we talk about LeanNet, we talk about the ResNet, LXNet, we try to talk about VG16, talk about DarkNet, EfficientNet, we talk about GoogleNet, we talk about. So all these are basically for a image classification, right? Again, we talk about YOLO, we talk about basically some sort of a model for a segmentation, for a tracking, for a detection. So a different kind of applications we used to build, and depends upon the application, depends upon the problem statement, we go and choose a model, right? We go and choose the model. So model architecture selection, and again, to know that you have to go through a lot of models, right? So these are just a computer vision model again. So if I'll come on a NLP side, there is a recurrent neural network. Inside that there is a LSTM, there is a GRU, and again there are multiple different kind of a connection that you can tune in a encoder decoder. There is a transformer architecture. So a lot of things, right? A lot of things. So it depends upon the task that we are going to solve. We try to select the model architecture, and that is something that we are going to explore in depth again inside your lectures. Now, once architecture is done, once architecture selection is done, once your data is prepared, then we try to go with the training basically. So we try to feed our data, and then once training is done, we try to do our testing, and then once testing is done, then deployment comes. Now, these 5 things falls with these 5 things always comes with all the project you are going to build out there, with all the project, right? Not just with one single project, but in this 5 things, lot of things comes in between. Lot means a lot. There will be a lot of variations, a lot of different approaches you will be able to find out in this 5 things itself. Now, moving ahead. So here, library wise, so majorly a TensorFlow. Keras is a high level API which has been built on top of TensorFlow itself, and a PyTorch. There are other libraries as well, but yeah, these libraries are pretty much famous, Keras and PyTorch, and we will be using these libraries. These are basically a Pythonic library, right? Although TensorFlow supports other language as well, but yeah, Keras, PyTorch, all these are a Pythonic library which has been especially designed and built for a deep learning, machine learning, computer vision reinforcement. So we are going to use these libraries, which is going to help me out in terms of converting my conceptual understanding or my mathematics in a reality, and eventually into a real-time application. So these libraries are very easy, and wherever it is required. So again, I'm going to come and do a discussion about it in a step-by-step manner. We will go through this entire lectures. Now, whenever we are talking about this training of the model, so obviously we need a system, we need a hardware, right? We need a hardware. With most of us, right? This hardware will not be available. Hardware means most of us is having just a laptop, maybe just an i5 laptop. So this i5 laptop is more than enough for a learning purposes. Now, wherever we have to go for a heavy training, right, wherever we need a GPU, because in our laptop, most of us will be having just a CPU. And even though if you'll be having a GPU, so maybe an integrated one, or maybe not a kind of a GPU, which is required to train this heavy weighted model. So I'm going to teach you, I'm going to even talk about that how we can try to use some of these hardware which is available over a cloud, right? That's a standard approach. That's a standard way of like doing a training. So how we can try to access something which is available over a cloud, and how we can try to make use of it. Yeah. So all of these things we will be talking about inside our lecture, everything, right? Everything. So hope guys, our understanding is clear with respect to deep learning, that what deep learning is all about, obviously mimicking the human brain, and what kind of application that we are using even now. A lot of application example I have given to you that we are using in our day-to-day life. And apart from that, so what we have to learn as an algorithm, or what basically we are going to explore the entire life cycle, like starting from a data pre-processing, data collection, data pre-processing, to a selection of the model, to a training, and then testing, and then finally a deployment. So this entire cycle we are going to close. And again, so system wise, it's completely fine. If you have just a i5, it is going to work. It is going to work, and wherever it is required. So obviously I'm going to tell you that, okay, fine. So you can try to use this particular cloud platform, and this is going to help you out. So with that understanding, guys, I'm going to stop myself over here, and let's begin a chapter number 1 of Deep Learning Masters from next class onwards. With that, thank you so much, everyone. Take care. See you again in my lecture. Welcome to Euron, everyone. And in this lecture, guys, I'm going to talk about a roadmap for deep learning. Obviously, there is a lot of things which comes under deep learning, like computer vision, reinforcement, NLP, generative AI, but I'll be focusing more and more on a core deep learning roadmap. And then I'm going to guide you. Then I'm going to tell you that if you are going through it, then how you should do a preparation. Plus, I'm going to give you a recommendation that from where you are supposed to do all of these preparation. So here, let me share my screen, and I believe my screen is visible now. So as I have already mentioned, that this roadmap guides you from a mathematical foundation to advanced neural architecture. Now, the mathematics part, right? It's very much important for a deep learning expert. But again, so that depends. So how deep you should understand a mathematics depends upon the role that you are going to take up inside an industry. For example, if you are going to join as a researcher, obviously your mathematics level should be very, very high. Unless and until you are not aware about the very, very deep of a mathematics, like a probability, statistics, derivations, or maybe algebraic calculation, it will be difficult for you to crack those kind of a profile. Now, if I'm just going to join as a developer, right, as a lead, as a manager, in that case, not an in-depth understanding is required, maybe a basic understanding is required, but in terms of a practical implementation, right, a practical implementation. So now, so if when we are talking about this practical with respect to a practical implementation, so where you will be able to, right, so where you will be able to see those mathematics. So here on Euron, you will be able to find out stats for a data science masters. This is the new batch, right? This is the new series that we have started. Apart from that, there are other batches as well. So where you can go and you can learn, right? It's not just this one. So here it is, this one is going to help you out in terms of building your strong mathematical fundamentals, a strong mathematical foundation for a deep learning. Now, coming to the next, right? Coming to the next, by the way. So the next part is an essential prerequisite. Like I said, mathematics is one of those prerequisites. Without mathematics, it will be very, very difficult to learn, to understand it. And I have even shown you the place. Now, for everything you can go and check on Euron, you will be able to find it. Whether it's a mathematics, it's a programming, it's a DL, ML, NLP, whatever, right? Just name it and you will be able to find out some of the courses, some of the books, some of the projects over there. Now, so mathematical foundation, a linear algebra, calculus, probability, statistics, all should be sorted and depends upon the label. If you're a fresher, then I don't think that a lot of mathematics is required. So maybe you just need a revision. So you just have to revise the concept that you have already gone through maybe in 10th or 12th. That's it in terms of fresher. Now, the second part is basically, so mathematical foundation. And then the second part is basically programming skills. Now, there are a lot of programming language out there, C, C++, Java, JavaScript, Perl, Ruby, Python, PHP, a lot of things, right? I will not recommend any other programming language other than Python for the whole AI ecosystem. Yeah, if you are into a web development, then you can, in that case, go through other programming languages. But if you are, right, if you are trying to get into a AI ecosystem, in that case, Python is the only language I will recommend. And I believe everyone in this world is going to recommend. So Python, and only Python is required. So Python mastery with data science libraries. Now, what kind of a libraries? So obviously from a deep learning perspective, a TensorFlow Keras, basically it's a Keras, right? Keras you should learn. Generally, we try to use a Keras API, Keras wrapper for TensorFlow. That I'm going to use it inside your batch as well. PyTorch, basically for a deep learning, specific to a deep learning. Then in terms of like data processing, for a deep learning, right? For example, if I have to talk about a image data kind of processing, then OpenCV kind of a library we can try to learn. For maybe a structured data processing, so Pandas kind of a library we can try to learn. So these are the library that you are supposed to be aware about, and then a Python, a core Python, right? Core Python till a modular coding, so that you can go and you can try to develop a couple of things on your own. Conceptual understanding wise, a basic of machine learning is required, because when we start talking about a deep learning neural network concept, right? When we started like deriving the forward propagation and a backward propagation over there. So if you are aware about a little bit of machine learning algorithm, not all I would say, but yeah, if you are aware about a little bit of machine learning algorithm, believe me, it helps you out, right? It helps you out in terms of understanding a concept in a much better way, right? So this is where this conceptual understanding comes into a picture. 35% of deep learning success depends upon the strong mathematical foundation. So this is just a number, 35%, but yeah, so majority wise 65%. So again, I'm talking about just a developer, not that much is required. Now, so once these three things is clear, programming skills, mathematical, conceptual understanding, right? So then a neural network fundamental, obviously, right? Neural fundamental. So there are a lot of like a neural network that we are going to explore from a different segment, from a computer vision segment, from a NLP segment, Gen AI perspective. So depends, right? Depends which area we are going to touch upon, and based on that we are going to discuss the neural network. So a lot of neural network we are going to discuss here. Backpropagation, which is nothing but how we train a neural network. So that is something called as backpropagation. That is something which happens in backpropagation actually. Then activation functions and neural network and practical implementation. So these are the fundamentals of a neural network that we are going to explore, and that you should know, right? As this is the roadmap, so you should know these things basically, right? These things are very much important for any like deep learning expert. Now, these architectures, convolution neural network. So we have LXNet, we have LeNet, we have like VGGNet, RustNet, we have SSD, we have YOLO, we have DarkNet, we have EfficientNet. So all of this convolution neural network architecture you have to understand for an image classification, for an image detection, for image classification, object detection, object tracking, object segmentation. So they are the tasks that we try to solve inside with the help of CNN kind of a network, convolution neural network. Now again, regular neural network. So a lot of things again comes into a picture, like a LSTM, GRU and its variants. Transformer. So yeah, BERT, Elmo, GPT, or maybe a T5. So these are the transformer based architecture, which you will be able to find out. And generative model like a GAN, VAEs, all those algorithm, all those architecture and a mathematical intuition behind this, you should understand. If you are targeting a deep learning master. So one by one, you can clear out your checklist if you are planning to do it. Now, so framework, what and all framework you have to learn. So yeah, framework wise, like a PyTorch TensorFlow, because it's a Pythonic framework basically, and on top of TensorFlow. So we have a Keras development workflow wise. So here we can try to like opt for some of the platform which provides a complete end-to-end infrastructure in terms of like a shipping out our entire model, in terms of training the model. So I believe cloud platform, AWS Azure GCP is one of the best in terms of providing that. And optimization technique, basically you should be aware about. So where we try to do a lot of parameter tuning, we try to like reduce the size of the model. We try to decrease the inferencing time of the model. So all this technique you are supposed to be aware about. And even from an interview perspective, these things are very much important. Yeah. So from an interview perspective also, these things are pretty much important. Now, so the last part, right? The last part is basically this. Now, what is this? A project. Because see guys, doesn't matter how much things you know, doesn't matter that how many things you have learned, doesn't matter how many notes you have created or you are going to create now or maybe in the future, nothing is going to help you out, right? Nothing is going to help you out. At the end of the day, you have to prepare, right? At the end of the day, you have to prepare your resume. Now, when you are preparing your resume, you have to mention the project that you have done, right? Your expertise, your experience during those projects, you have to mention inside it. Then only you can go and you can apply for a job or maybe for an internship or maybe for any kind of a research work, right? So at the end of the day, what matters? Only and only project. How you can try to demonstrate your knowledge? Only and only through a project. How people are going to recognize you as a talent? Only and only through a project. And that's a reality, right? That's a reality. So only project. At the end of the day, you have to do. You are not learning these things to pass some sort of exam. Yeah, if you're in college, obviously like some of us are going to do it. But at the end of the day, if you're going for an interview, which is a real world exam, right? So not an academic world exam, by the way. So here you have to deal with a project. You have to explain projects. So at the end of the day, you have to do a project, a lot of project, 3 or 4, maybe a very, very big one, good one, and a bit complex one. But yeah, as many experimentation as possible, because that is going to give you a real learning. So hope it's making sense to all of you, right? Now, so how much time you should dedicate? So as I have already mentioned, fundamentals, maybe 2 months in terms of building a mathematical fundamental, programming fundamentals and all those things. Yeah. In terms of learning a core neural network architecture, so maybe like a 3 to 4 months, you can try to dedicate. And then a specialization. So again, maybe you can go with the specialization of a computer vision, NLP, reinforcement, generative AI. You can choose your own field, right? Maybe you can choose some domain as well. Maybe go for healthcare, go for some sort of autonomous car industry, right? Depends what you are going to choose. So maybe you can try to dedicate some time over there, and then portfolio building. So as you will work, as you are going to experiment, as you are going to build project alone or maybe with team, right? It's going to like build your portfolio, and that is ultimate point, right? So hope guys, this roadmap is pretty much clear for a deep learning to all of you, right? A deep learning roadmap is clear to all of you. Hope all of you are going to follow this entire deep learning, and then whatever module which I have mentioned over here, whatever segment which I have mentioned over here, you will be able to find out everything even on Euron platform. With everything, literally, you will be able to find out on Euron platform. So maybe you can go, you can try this out. And then if you have any kind of a feedback, if you have any kind of a suggestion, do let me know. We are here to take your feedback. We are here to make our system better and better for learner like you, so that you can thrive. And again, so we can try to build a better world for tomorrow together. With that, thank you so much, everyone. See you again in my upcoming lecture. Welcome to Euron and welcome to lecture, everyone. And in this lecture, guys, I'm going to talk about a neural network. Now, so I have to talk about a neural network in a very, very depth, that what happens in a forward propagation, what happens in a backward propagation, what kind of activation function we are going to use, what kind of output function we are going to use, what is a meaning of a loss function, how many different type of loss function exist, what is the meaning of an optimizer, and what are the different optimizer which exist. Now, many of us may be not aware about all of these fundamentals or all of these concepts, and this is where this entire lecture comes into a picture. So where in a step-by-step manner, we are going to talk about it, and in my upcoming lecture, not in this one, obviously. So in my upcoming lecture, so I'm going to show you each and every step, each and every derivation in a very, very smoothest possible way. So let's get started, guys, and here is my screen. Now I would like to show you something so that those who are new, they will be able to understand a philosophy behind a neural network. As we all know that a neural network is nothing but it's a replica of a human brain. The way human brain works by receiving a data, and then we try to find out the relationship in between, we try to correct if there is some sort of a mistake, we try to relearn with the help of a feedback or without a feedback, and then eventually we try to perform some sort of a task. Now, on the same philosophy, you will be able to find out that neural network is going to work. But before that, so let me show you in an animated way that what component comes in between when we talk about a neural network, so that we can break it down going forward, and then we will try to understand things in a even deeper and deeper manner. So here there is a platform called as TensorBoard, TensorFlow. TensorFlow is one of the library, and this is a library which has been prepared by Google, by the way, and it's been made as an open source in a later stage, and now it's one of the popular library that we use in a deep learning, computer vision, or reinforcement learning, or I can say NLP, and even generative AI. So when we have to train a model from the very scratch. Now, so inside this TensorFlow, so along with this TensorFlow, there is something called as a TensorBoard Playground. So here, if you will go and search a TensorBoard Playground, so basically this is a simulation that has been created. So where you will be able to find out a input, a data, right? So this is a pattern that you will be able to observe. So these are the data which is given to you. Now, so input feature you can try to build, means input you can try to build over here. And then you will be able to find out that there are multiple hidden layers, right? So by default, there are 2 hidden layers which has been given to me. And in one hidden layer, there are 4 neurons. In other hidden layer, there are 2 neurons. And then there is an output. And above that, so you will be able to find out epoch. You will be able to find out learning rate. You will be able to find out activation function, realization rate, and then a problem statement that you are trying to solve, whether you are trying to solve a classification problem or a regression problem. Now, as we are just trying to start, so if we are trying to start fresh, so most of these things, or maybe all of these things, looks alien to us. Maybe we are not able to understand that what is what, maybe what is the meaning of a epoch, what is the meaning of a hidden layer, what is the meaning of the output layer, what is the meaning of an activation function, what is the meaning of a learning rate. And that's pretty much obvious, right? That's the reason. So we are trying to learn it. And if you're not able to understand, or if you don't know, or if you have never heard about these terms, it's completely fine. There is no issue with that. So we'll try to understand all of these things in a step-by-step manner. But let me show you a demo in a very first place, that how things works. So here, at the end of the day, whatever that we are trying to do with respect to a neural network, what it is trying to perform. So it is trying to basically learn a pattern. That's it, right? It is trying to learn a pattern. Apart from learning a pattern, it is not doing anything extra, anything else, right? So maybe it's a classification problem that we are trying to solve, or maybe a regression problem that we are trying to solve. Going forward, object detection, segmentation, or maybe we'll try to train a model based on the textual information. So everywhere, we are trying to find out a pattern. We are trying to build a relationship between our data, so that my neural network, it doesn't matter what architecture I'm going to take for maybe a vision, or maybe for an NLP task, or maybe generative AI task, what kind of architecture we are going to consider. But at the end of the day, all of these architecture is having one common philosophy. All of these architecture try to learn a pattern between a data set. And almost all the architecture, you will be able to find out that they follow the same kind of a philosophy, even in terms of a training. There will be input, obviously. there will be a multiple hidden layers, right? Again, so depends upon the architecture, so how you are going to build all of these layers, because if architecture is going to change, all of these layers are going to change, obviously, right? So it's not going to be same at all. That's the reason, so we talk about hundreds of different architecture, and those architecture even helps us in terms of learning things in a better way. So here there will be an input layer. You will be able to find out a hidden layer somewhere. You will be able to find out even a learning rate, activation function, realization, everything you will be able to find out everywhere. Now, if I'm going to execute it, if I'm going to click it, so you can see that its loss is decreasing. Difference, loss means a difference between expected output and the resultant output, or the output that we are getting from the model. And here, so you will be able to find out that this is trying to concentrate based on the pattern, right? So let me re-execute this one so that you will be able to see it once again. So as you can see that it is trying to do the classification, blue region with a blue color, and this orange dots with the orange color. So orange dot segregation in orange region and blue dot segregation into a blue region. And you must be able to see that things are flowing from one places to the another places, right? So things is flowing from X1 to the hidden neurons, all the hidden neurons, and then from here to this neuron, and then finally we are able to get the output over here, while all of these parameter is been selected. Now, if I'm going to change all of this parameter, maybe a learning rate, maybe activation function, maybe regularization, maybe a regression rate, or maybe a problem type, things are going to change, obviously. I can try to even change a batch size over here. I can try to change a noise over here. I can try to change a ratio of training and a test data as well. And eventually other things will start changing, right? Other things will start changing, as you can see, right? It's not going to be same. So now the things that you are able to visualize now, it's called as training. It's learning. It's learning what? It's learning a pattern inside the data. Doesn't matter what kind of a data I'm going to select. Let's suppose I'm going to select this data, which is having a complete different in terms of patterns. Now, if I'll try to execute it, you will be able to find out that yes, it is trying to learn a blue data as in a blue region and orange into a orange region with some error rate I can see, right? But yeah, it is able to learn. So at the end of the day, it is trying to learn a pattern between a data, nothing else, and all the neural network out there does the exact same thing, right? So more complex data obviously means more complex pattern. So when we talk about a textual information, right? So obviously textual information will be having a lot of complexity in terms of semantics, syntactic, grammar, and a lot of things, right? If I'll talk about the image data, so again, image is nothing but a combination of pixels, and in terms of computer, so basically it's a array or matrices that we can say as a in terms of like a mathematics. So we have like a hundreds and thousands of pixels. So between that, we have to find out the relation. We have a millions and millions of combination of a textual information, and between that, so we have to find out the relation. So like I said, guys, that doesn't matter which neural network you are going to choose. At the end of the day, those neural network or the architecture is trying to do one thing, which is very, very common. They are trying to learn a pattern between a data. And this is how we are going to move gradually, even inside a class, that we will start from the basic. We will start learning all of those architecture, and we will keep on finding a better and better and better architecture. Depends upon the task. So the architecture that you will be able to see in general, in case of a deep learning and computer vision and NLP and a generative AI. So basically those architectures are like built based upon the task, a different kind of a task that we try to perform in a generative AI or NLP or deep learning or computer vision, right? And we will try to follow along those things, and we will try to understand those things. But here, so I believe you are able to get a little bit of idea about a neural network, that what neural network does, and how this neural network try to train itself, how basically things is going to flow. So there will be input layer, there will be a hidden layers, right? And then there will be output layer. Now hidden layer, I can try to add as many hidden layer as I want. Yeah. And in one single hidden layer, I can try to add as many neurons as I want. Not here. Here they have given you a final number limitation, but yeah, in reality, you will be able to add any number. Any number means literally any number, you will be able to add it over here. Now input wise, so input data, you can try to add as many times as possible. Now see this structure. This structure is literally a very, very complex structure, right? It's a very, very complex structure. And now you can see that it is able to learn even a complex data, right? Complex data. So when, let me refresh this entire things once again. Maybe I'll just remove this entire parameter. Yeah. So here, let's suppose I'm going to select this complex data, and if I'm going to train with this simple neural network architecture, right? Now, so the question is that why do we need a different kind of architecture? Because see, every architecture will not be able to understand or find a complex pattern. For example, I have just taken a 2 input layer, as you can see, and then a 2 hidden layer. In one hidden layer, I have 4 neurons, and in another hidden layer, I have just 2 neurons, right? Now, I am just trying to learn this pattern, the spherical pattern that we have or elliptical pattern that we have inside the data. And it is very much difficult, and you can see a loss over here. A loss is very, very high, right? Loss is very, very high. A test loss is 0.48 and train loss is like a 0.36. I was expecting loss somewhere maybe close to 0, right? Then only I can say that my system is able to learn in a perfect way. But it is not, right? It is not. So this simple neural network is not able to yield me a better result. Now what I can do is maybe I can try to increase the complexity a little bit, right? I'll try to increase a hidden layer. I'm just doing it randomly, just as an experiment, right? I'm doing it. So as you can see, and now we'll see that we'll try to increase even input data. Now let's see that whether it is able to converge or not. And yeah, now it looks like that my loss is coming down, as you can see, and eventually same thing I'm able to see even inside my images. So where it is able to learn the pattern, it is able to learn. So blue region is been surrounded by blue colors, and then like this orange region is been surrounded by orange color. So now somewhere it is able to learn things in a better way. Yeah, learn things in a better way. Maybe I can try to play around with other parameters over here, right? Maybe I can try to make a learning rate is equal to 0.01, and then I can try to like check. So this is a reason. So we need a more number of controllable parameter. I can keep on changing it. I can keep on experimenting it, and I can try to create as complex network as possible so that my network will be able to learn in a best possible manner. Right now, see how complex this network is. So the kind of network that I have built, it's literally a very, very complex network that I'm talking about, right? But you are able to see even a result that, okay, so this complex network is somewhere helping me out in terms of learning a pattern in a better way. I'm not saying that, or I'm not advocating that more complex network will always yield a better result. No. It always falls down to an architecture, because after this lecture, many people will come and say that you said that, complex architecture, complex network always try to put hundreds of hidden layers, and inside the hidden layers, try to put up hundreds of neurons. It's not going to work all the time, right? It's not going to work at all, I would say. And this is where a different kind of architecture falls into a place to solve a different kind of a problem. Every problem statement, every kind of a data, every kind of a pattern will be having its own hierarchy, and it is going to follow its own lineage. So what I'm trying to explain you over here is that yes, till certain extent, this complex network is able to solve my problem. As you can see, I can play around with the learning rate. And what is learning rate? I'll be talking about it. I can play around with the activation function. Now, what is activation function? I'll be talking about it. Relation, I'll be talking about it. Problem statement, I'll be talking about it. So I'll be talking about all of these things one by one in my upcoming lecture. But here, so I'm just trying to give you a basic intuition behind a neural network, that how neural network actually works and what is a basic funda behind a neural network. A simple input, hidden layers, right? And then output over here. And so it is called as forward propagation. So it's basically called as forward propagation. Now it learns means what? So let me take a small neural network. Let me refresh it. Yeah. So when I say that a neural network is trying to learn, what is the meaning of learning, by the way, right? So see, here we have a weights, right? So this input is connected to this one, and this one. Now, whatever output that we are getting from here, it's going into this and this layer. Now, there are some calculation that we are trying to do in between. There are some calculation which we are doing here, and here, right? So here, when we are like not training this network, so you will be able to see that this connection, which is called as also weight, right? This connection, which is also called as weight. So this weight will be having some sort of a value, some random value you can say, right? Some random value this weight will be having. And once I will start, so just remember weight for the very first one is 0.19. Now, once I'll start training, see my weight has changed. So from 0.19, it became 0.66. And it will keep on changing. It will keep on changing. So as long as it will learn, basically, right? As long as it is going to learn, it will keep on changing at the end of the day. Now, this weight is something that we try to learn. Now, this weight is nothing but it's been learned based on what? Based on the loss that we are going to get. And this is something that we are going to derive. As of now, I'm just trying to talk about fundamentals, so that at least you must be aware about small terminologies and the words, nothing more than that, right? So this is the only expectation that I have, that you must be aware about a little bit of a fundamental. That's it. So with that, guys, thank you so much. Hope all of you are able to do that. Just go ahead and play with it. No need to understand anything as of now, because anyhow, I'm going to give you all the explanation, by the way, right? Step-by-step manner with a proper mathematical derivation, right? So I'm going to do the calculation. I'm going to do the math for a layer by layer. So weight, update, and the training. So for propagation and the backward propagation and derivation and a chain rule, everything I'm going to do it. So no need to worry about anything. Just try to get used to this entire terminologies, because this entire terminology, whether it's a noise or batch size or epoch or learning rate, all of these things will come again and again and again, right? Again and again. No need to understand everything on a day zero. It's completely fine if you're not able to understand. I'm not even expecting that. I'm not even trying to explain you, or I'm not even trying to make you understand that what is the meaning of epoch or learning data activation. I know I haven't even talked about it, right? So I'll be talking about it in my upcoming lecture. So with that, thank you so much, everyone. Take care and see you again in my next lecture. Okay, so welcome to lecture, everyone. And in this lecture, we are going to understand that what are the major term, or what are the major component generally we talk about when we see, or when we try to understand, when we try to learn a neural network for the very first time. And believe me, these terms which I'm going to discuss now, you will be able to find out these terms everywhere, every time, whenever you will go ahead with any kind of a neural network in your entire life. And these terms are very much important. I believe anyone who is trying to understand a deep learning concept, machine learning, not machine learning, I would say, but yeah, a deep learning, computer vision, NLP, generative AI. So obviously you must be aware about all of these terms in a very, very clean way, so that it is not going to give you any kind of a pain in a future. So let me share my screen, and let's start talking about a neural network. So here I'm going to write it down, that neural network common term. Yeah. So as I have already shown you in my previous lecture, that what is our intuition behind a neural network, and what in all component which comes into a picture. I'll just try to list down over here in the simplified manner. So in terms of any kind of a neural network, there will be a input layer. So where anyone can pass a input data, and maybe you can try to call that as a x1 and x2, right? So x1 and x2 is a input data. Now I can have a multiple input, that's completely fine. So x1, x2, x3, x5, x10. So n number of x I can have over here. Just a term, so you can try to label it as a different term, but yeah, this is what you will be able to find out. Now, so there will be a hidden layer you can try to find out inside any kind of a neural network. Now, what is this hidden layer, by the way? So hidden layer is nothing but it is going to help you out in terms of building a relation, basically, right? In terms of building a complex mathematical calculation, because as my mathematical calculation is going to be complex, so it will be illegible enough, or it will be powerful enough to understand a relationship between the data set. So I can try to add a multiple hidden layer, that's completely fine, inside a single hidden layer. So I can try to add as many number of neurons as I want, that is also fine. Depends upon me, so how I'm going to create or architect the entire neural network. and then there will be a output layer. So where you will be able to see your y hat, or you can say you can see your prediction or classification or regression, whatever it is, right? Or generation. So you are going to pass a x data, x1, x2, x3 and xn, and then you are going to get some sort of a final response. Now in between, like I said, so there will be a hidden layer. So here there will be a hidden layer that you can try to find out. Now, so how this input and a hidden layer and output will be connected? So let's suppose this is my like a x1. So x1 will go here and x1 will also go here. Means x1 will try to flow through this two hidden layer at a time. And then similarly, so x2 will go here as well as x2 will go here. As simple as that. And then so this is how this entire things will be connected, as you can see. So as you can see that x1 data, so whatever input that you are going to give, whatever number that you are going to pass, it is going inside a hidden neuron. And then whatever x2 that you are trying to pass, so this red mark is trying to represent that it is getting into this hidden neurons. Okay, that's completely fine. Now this is the hidden layer, and I can label this as a output layer. Output layer. Okay. Now, so what happens inside a hidden layer, by the way, and why we are even talking about a hidden layer, and what goes inside a hidden layer, what I will be able to find out at this point, at this point, at this point, and at this point. So here, a simple intuition is that whenever we are trying to create a neural network, a random weights will be initialized. For example, so here, let's suppose I'm trying to say that W1, right? W1, and this is my H1 and this is my H2, right? Hidden 1 and hidden 2 that we have. So W1 to 1 and then W1 to 2. So weight is a weight which is connecting with the X1 and H1, and weight which is connecting between X1 and H2. Now, what is this weight? So this is nothing but it's a random number, by the way, right? It's a random number that we try to consider. And initially we assume that okay, so these random numbers are trying to, like, create a relationship, build a relationship between the data set. But eventually this is something that we are going to train. We are going to basically change it. We are going to basically train it. Now here, so let's suppose I have a weight 2 connected to hidden layer 1. So I can write weight 2 1. And here I have a weight 2 connected to hidden layer 2. So weight 2 2 I can try to write. So as you can see, that we have a weights, right? We have a weight. Weights are going to be random, and this is something that is a trainable parameter. We try to train it. And then there will be a bias B1 will be attached to this one, and bias, let's suppose a B2, which will be attached to this one. Okay. So biased. So again, this is a trainable parameter. So we try to attach some sort of errors with respect to this one. Then there will be a output layer. So even over here, so you will be able to see a B of 0 means bias you are going to attach. And here also you will be able to find out a connection, a weights, because we have a connection over here, we have a connection over here. So if we have a connection, so obviously we'll be having a weights over here. So here you can say that weight from hidden layer 1 to output, and then weight from hidden to output. So maybe I can try to name it in this particular way. That's completely fine. So this is how this entire neural network will be connected to each other. At the end of the day, what we will try to do? So at the end of the day, we will try to change a weight, and we will try to change the biases. Now, so inside a hidden layer, it's completely fine. We are trying to send this X1 and W1, X2 and maybe a W2, something like this. We are trying to send over there. But what will actually happen inside a H1? Let's try to understand that. And what will be the input inside the H1? So means at this point, what will be the input? So the input which will go inside this H1 is nothing but the combination of this and this. Yeah, combination of this and this, the two dot which I am trying to represent over here, that will go inside H1. Now combination of this and this, that will go inside H2. Right, combination of this and this, that will go inside this final output layer or output function, whatever we are going to assume. So what is something that will go? it's a very simple and straightforward. So let's suppose if I'm talking about maybe a Z and I'm writing that as a Z1, which will go inside H1, input to the H1, right? Input to the H1. So let's suppose I'm trying to write maybe a Z1 over here. So the simple like a calculation will be x1 w11, right? x1 into w11 plus I can say x2 into w21 plus the bias b1. So plus a bias b1. Now this will be like a going inside basically this one. So one component from here, x1 and w11, and second component from here, so x2 and w21 plus a bias. Now this combined things z1 will go inside this h1, which is a hidden layer. Now what will go inside a h2? So let's represent that as a z2 basically. So the things which will go inside like a h2 is as a z hidden layer 2 basically is going to be x1 w12 plus x2 w22 plus bias, right? Plus bias over here. So it is going to follow a simple linear equation, y is equal to mx plus c kind of a philosophy, right? So where the data which will go over here is nothing but this weight, which is eventually m over here, and then the input data plus c. C means bias in this particular term. So Z1 and Z2, so it will go inside H1 and H2, and H1 and H2 is basically a hidden layer. So obviously hidden layer must be doing something, right? So must be implementing some sort of function. So in general, what hidden layer try to do is, so hidden layer helps a neural network to non-linearize the data so that it will be able to understand a relationship in a better and better way. This is what like a hidden layer does all the time, by the way, right? All the time. So okay, so Z1 and Z2 will go inside H1, and inside this hidden layer, so we try to implement something called as activation function. So we are completely okay with the input, we are completely okay with the hidden layer, and now we are completely okay with the output. So inside hidden layer, you will be able to find out something called as activation function. So inside hidden layer, you will find activation function. Now, so what kind of a activation function we are going to find out? So there is activation function called as sigmoid, there is something called as hypertangent, there is something called as ReLU, leaky ReLU, Swiss. There are a lot of activation function that you will be able to find out, which I'm going to talk about it for sure in my upcoming lectures, step by step manner, all the activation function. But the major responsibility of this activation function is to achieve a non-linearization into a data set. So means whatever linear data that you are going to pass, so it will always helps our data set in terms of understanding a non-linear relationship. Simple as that. So here we have an activation function which will go inside this one. So let's suppose, for example, I'm just going to assume that whatever you are going to pass inside this hidden layer, right? Whatever you are going to pass inside this hidden layer. So here, let's suppose I'm going to apply a function is equals to x square, right? X square means whatever you are passing inside the hidden layer, it will become a square. As simple as that. So let's suppose if I'm going to pass a Z1 and Z2, so the output that I will receive out of this one, let's assume that, again, this is not a real activation function I'm talking about, but let's assume that here I will get Z1 square and here I will get a Z2 square. As simple as that. Yeah. So Z1 square and Z2 square, maybe I can take a cube, maybe I can take a to the power 5, maybe I can take a exponential, maybe I can take a logarithmic of it. Simple, right? As of now, I'm just trying to say that there is a one activation function I have taken. So that activation function is basically x square. So whatever you are going to pass, it will become a square of it, right? Just for the explanation purpose, I have taken that, nothing more than that. So, okay, so Z1 square and Z2 square I will be able to get. So once I will be able to get Z1 square and a Z2 square, then again same thing I will try to do. So this into this, this into this, summation of this will go where? So go into the output one. So what is the output? So what is the Z of 0 you will be able to find out? So Z1 square into W10. So weight 1 0 plus Z2 square weight 1, so sorry 2 0. So weight 2 0 plus bias B0. So this is something, this Z0 you will be able to find out that which will go inside this output neuron, Now, if you will go inside the output neuron, so obviously there must be some sort of a output function, right? Output function. So which is going to produce a Y, right? So there must be some sort of a output function. So again, there are multiple output function that we can try to choose, which is similar to the activation function, I would say. So output function will help you out in terms of giving a output of the entire neural network. So let's suppose if I'm trying to do a binary class classification 1 0, let's suppose I can do maybe a multi-class classification. Let's suppose I'm doing a regression, so which is going to give me some sort of a numbers. So here there will be an output function. So inside this, so let's imagine that output function is basically a root. So whatever you are going to pass, so it is going to give you the square root of those data as a output. Okay. So Z0 you are going to pass. So what is going to be the output? So output, or you can say Y hat, Y prediction. So let's imagine that it is giving me root of Z0. So Z0 I have passed over there, right? Z0 I have passed over there, which is a combination of these two. So it is going to give me this one. So that will become what? That will become basically a Y hat, means Y prediction. System is going to give, or neural network is trying to give me basically a Y prediction. Okay. Now, once you are going to get a Y prediction, now, so by doing or while going through this entire neural network, if I'm able to get a Y hat, now it's pretty much obvious that these weights was, or these numbers that I have taken, the biases that I have taken, which is responsible for building this relation and eventually giving me the final outcome, it was a random one, right? It was a random one. It was not the exact one, and so it will not be able to understand the real relationship between the data, right? It will not be able to understand the real relationship between the data. So to avoid it or to mitigate it, basically, right, or to make it correct, what we can do, so we can try to change these weights and biases so that my relationship will be better and better. Because how I'm getting Z0? Obviously, I'm trying to do some sort of a multiplication addition with respect to this weight and biases, right, which is eventually helping me out in terms of establishing the relationship in a layer by layer fashion, right? So what I have to do is I have to change this weight and I have to change this biases. Now, when it comes to changing a weight and biases, right, when it comes to changing a weight and biases, so obviously we can try to change a weight and biases. That's completely fine. But based on what, right? Based on what? So based on basically a loss. Now, what is a loss? A difference between Y and Y hat, means the expected value of Y and a Y hat is called as basically a loss, or in other term, you can even say as a cost. So somewhere you will be able to find out cost as a term, somewhere you will be able to find out loss as a term. Technically, loss and cost is actually same, right? It's not different at all. Now, there are different kind of a loss function or cost function you all will be able to find out, right? So there are like a multiple function which even I will be talking about based on the different kind of a task. So there will be a loss function and there will be a cost function. Now, or both are same actually. Now, what it does is that it will always try to find out the difference between Y and a Y hat. Now, once you will be having a difference between Y and Y hat, let's imagine, right? Then what you will do, you will try to do a backward pass. So far we were trying to perform what? A forward propagation. So in a forward direction, we were trying to move. So it's called as forward pass or forward propagation. So in a forward propagation, so we were going through whatever data is available and we were doing the very simple calculation. Now what we will do is that we will try to move through a backward propagation. So backward propagation or backward pass. In a backward propagation, what we try to do is that based on the loss, so based on the loss, we will try to change a value of this weight, this biases, this weight, this weight, this weight, this weight, this bias, and this bias. This is what we do, right? This is what we do with respect to the loss all the time. So with respect to loss, we will try to do that. So here, what we can do is, so we have to find out everywhere a new value of weight, right? And we have to find out everywhere a new value of our biases. This is the whole idea. That's a whole like a reality. So what will be the new value of weight? So new value of weight is basically old value minus eta. Eta is called as learning rate. I will be talking about that. And then the partial order derivative of a loss with respect to what? So with respect to the weight. And here, so biases, so old biases, eta, partial order derivative of loss with respect to the biases. So this is something that we try to find out because we are already aware about the old weight and old biases. We already have a value of old weight and old biases from the neural network, right? We already have that value. So what we have to find out that we have to find out the eta. Now, what is eta, by the way? So see, just try to observe this equation. My major objective in a backward propagation is what? My major objective in a backward propagation was to change the weight and the biases. So eventually when I'm trying to change a weight and the biases, so I'm trying to change the whole relation, right? So the way it is trying to yield my y hat. So I'm just trying to change the whole approach, whole like a relationship between. So here I'm trying to find out a new value of weight and a new value of biases based on the old weight and the old biases. So where I'm trying to use this old weight and old biases minus I'm trying to do eta, which is nothing but a learning rate. Now this is basically a constant in general. So we try to take a value of eta is equals to sometime 1, sometime maybe 0, 1 and sometime maybe 0, 0, 1. It's a standard one, but yeah, you can try to take any kind of extreme value. Now why this one is significant, and this is the hyperparameter, you can tune it basically. So why this learning rate is significant? The learning rate is significant because whenever you are trying to change your weight and biases, the old one and the new one, you should not change too fast or you should not change too slow, right? So whatever like a numbers that you will be able to get from here, whatever number that you will be able to get from here, so you should just do the multiplication with any of these numbers, which is eventually going to control the whole changes, right? Because as you can see, if you're going to complete, for example, I'll just try to give you a real life example. So when you will try to learn really fast, so actually you don't learn, you try to skip things. And when you learn very, very slow, so again, you don't learn in a proper way. So you basically start forgetting things that you have learned a long back. So you should not be too slow and you're not supposed to be too fast over there, right? In terms of learning. Same thing I'm trying to apply over here. So here, what is the meaning of learning? Adjusting a weight and biases. So we are not supposed to be slow, like too much slow, and we are not supposed to be too much fast. And that's the reason. So there is a eta, and eta is a hyperparameter. Hyperparameter means you can try to tune it. You can try to change this value. You can try to do the experimentation, right? Experimentation over here. The major component is basically this one, right? Basically this one. So now this is going to help you out in terms of, right? In terms of optimizing the entire weight and the biases. And this is where the concept of, this is where the philosophy of optimizer comes into a picture. That rate of change of like a L with respect to W, rate of change of L with respect to biases, right? Or maybe partial order derivative with a loss with respect to weight and partial order derivative of a loss with respect to biases. So how we are going to change it? How we are going to change it? And this is where the philosophy of optimizer, which I'll be talking about, comes into a picture. So I believe this flow is clear. The whole idea was not to explain you the calculation. The whole idea was to explain you the whole core concept behind a neural network, which I'm going to reiterate in my next lecture once again, when I'm going to consider a input data, right? A real value, a numerical value, basically I'm going to consider. And then with the numerical value, I'll try to show you the entire calculation in a forward pass as well as in a backward pass. And then by using one of the optimizer, I'm going to show you even this derivation. And then I'll change the value of weight and biases. I'm going to show you that part as well. But logically, hope we all are able to connect that what happens in a forward pass. Let me reiterate. Simple input will go multiply with the weight, and then like a combination of this will go into the hidden layer. Hidden layer will be having some sort of a function basically, right? So input, and then that function will give me output. Again, same thing will happen, and then eventually I will be able to get some sort of a output. Once I'll get the output, so I'll try to do the comparison with the original expected one. So difference between the original expected one and the output that you have received from the neural network is called as basically loss. Now, once I will be able to get a loss, I will move into a backward propagation. Simple. I will move into what? I will move into the backward propagation. Now, in a backward propagation, what I'm going to do, right? In a backward propagation, what I'm going to do? So in a backward propagation, basically, I'm going to change all of these values. Which values? So weight and the biases. How we are going to find out the new value of weight? How we are going to find out the new value of biases? By using this equation, So new weight is equal to old weight minus eta. Eta is nothing but a learning rate which controls the changes into the previous one, right? We should not be too fast and we should not be too slow, because both is going to harm my entire learning curve. This is what happens even in a real time. Now, so when we talk about a derivation of, or I can say a partial order derivative of a loss with respect to weight, a partial order derivative of loss with respect to biases. So here the concept of optimizer comes into a picture. I'll be talking more and more about it, right? So just wait for another lecture, right? And then you will be able to understand even in a numerical way, and hope till this part calculation is clear and whatever assumptions that I have made is clear. This slide will be available inside your dashboard, so you can go and you can try to fetch this particular slide, and then let me know about your thoughts if you have any. And with that, thank you so much everyone. Take care and see you again in my next lecture. Welcome to Euron everyone, and these lectures are going to be one of the most important part to build a base for any kind of a neural network architecture you are going to explore maybe today or maybe in future. So in these lectures, guys, I'm going to give you a complete means literally a complete derivation of a forward propagation, and then in my upcoming lecture, so complete derivation of a backward propagation with respect to optimization and a chain rule and derivation, obviously, right? Because once you will be able to understand the complete flow of forward propagation and a backward propagation, then in a future, so we are going to add a multiple things in a hidden layer, multiple things on an output layer, multiple things on a so-called loss function, and multiple things with respect to the different kind of optimizer. You will be in a position to understand each and everything, believe me. So you will be in a position, but yeah, so basic understanding, a basic chain rule is important, and it's not tough at all. It's not at all tough means literally it's not at all tough. You all will be able to understand with ease. You all will be able to understand with a basic example. I'm going to take a simple mathematical formula. I'm going to take a simple numerical value, and with the help of those values, I'm going to explain. But yeah, so these things are once in a lifetime kind of a explanation that you have to understand. Then for a lifetime, you are not going to face any kind of a problem. So in my last lecture, I was talking about a basic component of a neural network. Now in this lecture, I'm going to extend a same thing, and I'm going to teach you that how training actually happens, right? So as we all know that training means understanding a pattern, understanding a relationship between a data set. That is something called as training, a neural network, right? So this is something which I'm going to explain you that how exactly this calculation happens, because at the end of the day, computer is trying to do a mathematical calculation, right? When I say that computer is trying to find out a relation between input and output, or between the data set, it simply means that computer is trying to find out the relation in between. So let's try to understand that how it will be able to find out a relation at the end of the day. So let's suppose I have a input, right? So basically I have a input given to me, and that input is basically x1 and basically x2. Now value of input x1 is 0.05 and value of input x2 is 0.10. So this is basically my x1 and this is basically my x2. Now obviously I will be having a y, right? I will be having a y. So value of y is 0.01. So this is the 3 value. Now likewise I can have a multiple rows. This is just one single record I have taken. So likewise, I can try to take a multiple record over here, right? Multiple value of x1, x2 and a respective value of y, and maybe I can try to build a relationship. But just with this data, I'll try to build a relationship. Just with this data, I'll try to explain you that how forward propagation works in case of a neural network, right? So here I'm going to write a chapter name that neural network forward propagation. Now, so forward propagation is very simple. The main thing, the main learning is going to happen in case of a backward propagation. So which I am going to explain you. based out of the same understanding, based out of the same data. So when I will give you a derivation of a chain rule. Okay. Now here, so I'm going to create a very simple neural network. So I have two input. So, okay, I'm going to create a two simple neuron in case of a input. So here I have, let's suppose x1, and here, so I have, let's suppose x2. Now what is the value of x1? So value of x1 is 0.05, and what is the value of x2? So value of x2 is basically 0.10. I have taken that, right, as per the data set which is given to me. So this is going to be the input layer. Yeah, this is basically what? So this is a input layer. Input layer. Okay. Now, so if there is a input layer, what I will do is I'll try to create even a hidden layer, because we know that hidden layer is something which helps a neural network in terms of understanding a data, right? In terms of understanding a data set. So if there is no hidden layer, so it will try to take an input and then it will try to give you just an output, right? So if there is no hidden layer, so I'm going to create a hidden layer. Now this layer, I can name it as a hidden layer. Okay, and I have taken two neurons, so I can try to take a multiple hidden layer, and in one single hidden layer I could have a multiple neurons. So as I have shown you while showing you the TensorBoard playground basically, right? Okay, so only one hidden layer I'm going to consider as of now, and then I will be having a output neuron, so which is going to give me output. Now which is going to give me output? So my actual output is what? My y is what? So 0.01. So this is my actual y, actual, right? What this neural network is going to give, we'll try to figure it out. Yeah. Now how this network or how this neurons will be connected with each other, how input, hidden and output neuron. So now this is a output layer. Let's name it in this way. Yeah. So how this entire neural network will be connected with each other, that is something that we all have to understand. And if we are able to understand, so again, a little bit of problem we are able to solve. Okay. Now inside this hidden layer, I can name this neuron as H1 and this one as a H2. Okay. This one as a H2. Simple. H1 and H2 I'm going to name X1 and X2. So this is the name of an input layer. Now this from X1, it will be connected with H1, and from X1 it will be connected with H2. Okay, fine. Now from from X2, it will be connected to H1. Okay, this line is not great. So let me delete that line. Let's delete all of this line. Okay. So here from X1, this will be connected, and this is how it will be connected. Okay. And then from X2, so it will be connected in this way, and then it will be connected in this way. Fine. And then there will be a connection from this one to output 1 and this one to output 1. Now this is how my final neural network looks like. Yeah. So this is how my final neural network looks like. Now here we have created a connect. We have created a connection. That's completely fine. But when we are trying to create this connection, so we try to define some value for this edges, which is called as weight. We try to define a weight, and that weight is basically a random weight we try to define. Now these weights combinedly all together, so it is going to help me out in terms of understanding a pattern between input and the output, means the x value and the y value, x1, x2 and the y value. Simple. My x value is 2 over here, x1 and x2. So it will try to help me out. So I'm going to define some sort of a values for this one basically. So here from x1 to h1, so I'm going to name it as w1, and I'm going to give a random value for now. Initially there will be a random value. There is a technique by which we try to initialize a weight. So there is a JVA technique, there is a heap, but yeah, that will come into a later stage. As of now, just try to focus on this one. Now from x2 to h1, so I'm x2 to h1, I'm going to define a weight called as w2, this one, and the value of this weight is, let's suppose, 0.20. Yeah, again random, fine. Now from x1 to h2, I'm going to define a weight, and I'm going to name it as a w3, by the way, to this one, and value I'm going to keep it as a random, so 0.25, let's suppose. And from x2 to h2, I'm going to define a weight called as w4, W4, and I'm going to give a weight is equal to 0.30. Yeah. So these are the random weights which I have given, guys, right? These are the random weights I have given, and not just a weight, there will be a biases which will be attached to a hidden network. So for example, y is equals to mx plus c. So x value we have, right? And we have value of m, so we have to define a value of c as well. So here the corresponding value is called as biases. So we are going to define a value of biases. So let's suppose value of biases for this neuron is going to be 0.35, and even for this neuron value of biases is going to be 0.35. Fine. So bias b1, maybe I can try to call it as, so bias b1. Okay, that's completely fine. Now the next one, right? Now the next one. So here from h1 we are giving, or we are sending a value to the output neuron. So this is the output neuron, right? This is the output neuron. So we are sending the value. So there will be a weight over here. So I'm going to call this weight is equals to W5, and W5 is equals to 0.40, and this weight I'm going to call it as a W6, and W6 is going to be 0.45. So now this is the whole neural network, plus even a biases will be attached. So let's suppose bias B2 I'm going to name it as, and value is equals to 0.60. So now there is a neural network I have, and for everything I have some values, right? For input I have a value. What is the output, the real output, the expected output? I have a value for that. What will be the weight, means whatever connection or whatever edges that I have created between one neuron to other neuron, all the possible connection. So for all the possible connection, I have a weight and I have a biases. Okay, that's completely fine. Now this is something which I need, right? This is something which I need. Now in a later stage, what we are going to do is that the weight that we have created and the biases that we have created, as of now, it's a complete random value. Yeah, as of now, it's a complete random value. So eventually, the learning, what is the meaning of a learning? The meaning of learning is very simple, that we will try to get the output. I'll show you that. I'll show you the calculation. So we will try to get the output. Now we will try to find out the difference between the output which neural network is giving and the actual one. Which is the actual one? This one, right? This one is the actual one. So we'll try to find out the difference between the output given by a neural network and the actual output. And eventually that difference is called as loss. And there is a different loss function we are going to use. It's not just going to be a difference simple, right? So there is a loss function that we try to use, and then we will, according to the loss, what we will do is, so we will start changing the value of all of these weights and biases in a backward direction. So first B2, then W5, W6, then W4, then W2, W2, W1. In this way, we will start changing layer by layer in a backward direction. We will start changing the weight. Weight as per what? We will start changing as per the loss, because these are the weights which is responsible for giving me a loss, giving me a wrong value of y, because my input is not going to change, my expectation is not going to change, but why I'm going to get a wrong value, why I'm going to get a loss, why I'm going to get a difference between the output from a neural network and the actual expected output, because of these weights and biases, right? Which I have introduced in between. So I have to tune these weights and biases. I have to tune it, and I have to tune it as per the loss that I'm going to receive. So this is something that we are going to establish, guys. So let's go ahead one by one, and then let's try to understand that eventually how it is going to work. Yeah, how it is going to work. So here, what we will do is that let's do a mathematical operation, layer by layer, and let's try to understand the calculation. But before that, right? So here inside this hidden layer, right? Inside this hidden layer, the hidden two neurons that we have. So we will be having an activation function, as we all know, right? We will be having an activation function. So we will be having what? We will be having activation function. Now there are so many activation function which I'm going to introduce in a upcoming lecture, not in this lecture by the way, in an upcoming lecture. Just I will try to give you the intuition behind the activation function. So activation function is a kind of a phenomena or kind of a function, so which try to introduce a non-linearization into a data, right? Non-linearization into a data. As of now, just try to understand this part. There are so many activation functions. There is something called a sigmoid function. There is something called a hypertangent function, a ReLU function, leaky ReLU function, Swiss function. All of these things I'm going to talk about. But as of now, I'm going to take an activation function as a sigmoid function. So how we can write a sigmoid function, by the way? So sigmoid function is nothing but, I can write it down in this way. So for any input, any given input x, whatever input that you are going to give, it will be 1 by 1 plus e to the power minus of x, right? So this is going to be the sigmoid function. This is going to be the sigmoid function, by the way. Yeah, this is going to be the sigmoid function. Okay, that's completely fine. So this is a sigmoid function, and this function I will be considering as what? As a activation function. So this function will be available here, and this function will be available here. Now, this function is going to give me an output between 0 to 1 all the time. This function is going to give me an output between 0 to 1. Okay, that's great. So if this function is going to give me output between 0 to 1 for any given like a input, right? For any given kind of any given input that we are going to pass. So if I'm going to draw a graph for this one, so maybe I can, this graph will look like this. Let me draw a simple small graph for this one, for a sigmoid function. So if I'm going to like draw a graph for this, so this is how this graph will look like. So for any input, this is how this will look like. So starting from 0 till 1 for any input of x. So negative of x to a positive of x, minus infinity to positive infinity. So it is going to give you output between 0 to 1. So whatever data you are going to pass over here, whatever x value that you are going to pass over here, for every x value, it is going to give you any values between 0 to 1. Now, so I'm going to consider that function even as an output function. So I'll be using a sigmoid function as an activation function to introduce a non-linearization into my data, as well as I'm going to use the same function as an output function. Simple, yeah, as an output function, I'm going to use it. And I'm going to call it as a activation function, by the way. Okay, that's great. So activation function as well as output function, both. So I'm going to use the same function. I can try to use a different function, but yeah, as of now, it's not required as my y value is like a 0.1. So I'm assuming that between like a 1 to like whatever value of y that I will be having. So it will be between that kind of a range. So now, so let's do a calculation, guys. Let's do a math, and based on the math, so let's try to understand that which layer is going to give me what kind of a output. So first of all, I'll try to start with a minor calculation, right? A minor calculation. Now, what that calculation could be. So here, I'll try to start with x, and I'll try to understand that at this point, this dot which I'm trying to draw, what is the value which will go inside, and at this dot, what is the value which will go inside, and then at this point, what will be the value which I will be able to get. So means this is the H1 hidden layer. This is the H1 hidden layer, right? So what is the value which will go inside this H1 hidden layer? Let's try to write it down, that particular part. Yeah, let's try to write it down. So here I can write it down that H1 input in, right? So what value will go as inside this hidden layer? So it is going to be x1 W1, by the way, plus x2. X2 is also going, right? 2 arrow is going inside this one. So x2 W2 plus there is a bias, right? There is a bias B1. So there is a bias B1. So this is the value which will go inside, right? So inside this, we have an activation function. Over here we have activation function. Over here we have an activation function, right? So we have an activation function. So inside this is the value which will go. Now, if I'll start doing the computation, so value of x1 is 0.05. Value of w1 is basically 0.15, as we have written 0.15, plus value of x2 is 0.10 into value of w2 is 0.20 plus biases. What is the bias? So bias is basically B1. B1 is basically 0.35, right? So 0.35. Now, if you are going to do the math, I have already done the math. So it is going to be 0.3775. Now, this is the value which will go in, right? in. So as a combined value, this is the value which will go here inside this sigmoid function. So inside this sigmoid activation function which I have written, so it will go inside this one. Now what is the h2? What will be the value which will go inside h2 in, right? So it is going to be x1 w3, x1 w3, simple linear like equation like mathematics we have, and then x2 w4 plus bias b1, right? This is the value which will go inside this. So here what we can do is, so we can write it down, a value of x1. So value of x1 is basically 0.05 into w3. So value of w3 is 0.25, 0.25 plus what is the value of x2? Value of x2 is basically 0.10. What is the value of w4? So 0.30. And what is the value of b1? So value of b1 is 0.35. Now if you are going to do the math, you will be able to get this particular value as 0.3925. So this is the value which will go in, right? In. Now this value is going into what? Into this neuron, into this perceptron, right? Artificial neuron is called as perceptron. So this value is going into this neuron, this particular perceptron. Now inside this, what I have applied? I have applied the activation function. Yeah, I have applied the activation function. So this data, this particular data and this particular data will go inside that activation function. Now what is the activation function which I am considering? So I am considering basically this sigmoid activation function, right? Sigmoid activation function I'm trying to consider. So where for any value of x, it is going to give you 1 plus e to the power minus of x, right? Sigmoid activation function. So between the value 0 to 1, it is going to give me. It doesn't matter what value will go as an input, 1000, 2000 or like a millions. But yeah, all the output is going to be in between this. So now if you are going to apply sigmoid on H1, right? So what is the output of H1? You will be able to get, what is the output? So H1 out, you can write in this way. So H1 out is nothing but this value going into sigmoid, right? This value going into sigmoid. So H out is going to be what? So H out is going to be sigmoid of 0.3775. Yes. So H out. So it will be approximately, if you are going to do the math, so approximately it is going to be 0.59327. Fine. So this is the value which I will get here, right? Output of H1. Now similarly, so what will be the output of H2? So sigmoid of this value, so like 0.3925 is equals to approximately 0.59688. Now this is the value that I will be able to get as a output here and here. So H1 output and H2 output. Okay. Now this value will get multiplied with what? Weight and plus biases, and then it will go where? It will go here. Means input into the output layer. Yes, input into the output layer. So this is something that it will like go. So here, what will be the, so input into the output layer, input, right? I'm not calculating the output. Output I will calculate, but yeah, input into the output layer. So what will be that? So basically H1 into W5 plus, right? Plus H2 into W6 plus bias B2. So this will be eventually the input into the output neuron, because in output neuron I have an output function, a sigmoid function I have applied, right? So in an output, so I have a function again over here. So there should be some input, right? So input will go and then it will go into the sigmoid, and then I will be able to get the output. Okay. So here H1 W1. So what is the value of H1 by the way? So H1 is 0.59327, and then H2 is 0.59688, and then W5 is 0.40, W6 is 0.45, and biases is what? Bias is 0.60. Okay. So I'll try to put up all those values over here. So 0.059 into 0.40 plus 0.59688 into 0.45 plus our biases, so 0.60, which is eventually going to be 1.10591. So I have done the mathematics. Yeah, this will go into, right? into means, so combinedly this will go inside this neuron, inside the output neuron. Now inside output neuron, so I have used the output function, right? So it is going to give me output. I'm going to write output as a y hat. Y hat means a predicted output from the neuron. So y hat means predicted one. Y means the expected one, the original one. So y hat is going to be the sigmoid output of 1.10591. Okay, sigmoid of this one. So now if you are going to do the math, so it will be approximately 0.75136. 0.75136. Okay, fine. So this is something that I have received as a output from the neural network. My weight was random, my biases was random, right? So I have received this one. My input output is fixed. And what was my expected y? So my expected y was 0.01. Okay, so my expected y was basically 0.01. Okay, that's great, right? Now clearly we are able to see that I was expecting this value 0.01 and I have received basically 0.75, and there is a difference, right? There is a huge difference between the expected value and the between the expected value and the value that I have received from a neural network. Means there is a lot of margin, means there is a lot of mistake, means there is a lot of error over there. Yeah, means there is a lot of loss over there. Now, so if there is a loss, so who is responsible? Who is responsible for this loss? So obviously the weights and the biases with which I have done some sort of a multiplication, and then there is activation function. So all of these things together are responsible for giving me this one, right? This output. Now what I have to do is, so based on this loss, right? Based on this loss, if I can try to change a value of this weight and biases, right? If I can try to change a value of weight and biases based on loss, right? Maybe there is a chance. I'll try to decrease the loss, by the way. Yeah, I'll try to decrease the loss, means it should not give me a loss. So based on this, if I'll try to change the value of weight and biases with the intention to decrease the loss, then maybe I will end up building this entire mathematical relation, because at the end of the day, it's a mathematical relation that we have built, right? So H is going here, here, and here. So everything is just a mathematical equation. Yeah. So maybe, right, there is a possibility, there is a very high possibility that it will be able to understand a relationship between my input and my output, and it will be able to give me an output which is close to my actual output. Yeah, close to my actual output. Then I can say that yes, learning is successful. It is able to learn something. It is able to learn a pattern between my input data and the expected output. That is something that we have to do with respect to a neural network, right? That is something that we have to do with respect to a neural network. So this is how this forward propagation has happened. Forward propagation, right? So this is something called as basically a forward propagation. Forward propagation. Yes, this is a forward propagation. Now, in a backward propagation, as we have received a value of y hat, and value of y hat is what? So it's basically 0.75 and 136, which is this is the value which I have received, and this is the value which I was expecting. There is a huge difference in between. So now my responsibility is to change a value of B biases, means B2 and W5, W6, B1, W1, W2, W3, W4, so that when I'm going to pass a data next time, it should give me a value of y hat, which should be closer to a y, right? Which should be closer to a y. So I have to do the updation of the weight, and the biases. Now that is a place where actual learning happens. So based on like a calculation, we got the output. Now I'll do the backward propagation in your next lecture. So with that, thank you so much everyone, and take care. See you again in my next lecture. Okay everyone, so welcome to the lecture once again, and in this lecture guys, so I'm going to explain you that how backward propagation happens, and eventually it will help you out to understand that what is a real meaning of a learning with respect to a neural network. So far we have seen that in a forward propagation, so we are going to pass an input, and then there is a weight in between, and finally we will be able to get our output. Now there is a difference between our output which we have received from a neural network and the output that we are actually expecting, right? The original output. So there is a difference between these two output. So the original one, the expected one, and the received one. So which we have received from the neural network, which I am representing with the help of y hat. Okay. So here in this situation, so what will happen is that we are going to consider a loss function. So because we have a difference, right? We have a difference between y and y hat, and which we should not get. So basically we are going to consider that as a loss, or we are going to consider that as a cost. So in general, you will be able to get a word called as cost or loss, right? Both are actually same. So there are so many different kind of a loss function and or cost function. Both are same, by the way, just a term. So you will be able to see a different kind of a loss function and a cost function, and that too with respect to a different kind of a example or scenario that we are going to solve. Here I'm going to consider a very simple loss function so that you all will be able to find out its derivative, and you will be able to even do a math. And similarly, I'm going to show you the mathematics behind it. So here I'm going to consider a cost or loss function called as MSE. So what is this MSE? So it's called as mean squared error. It's also called as error function, by the way. So here MSE or this loss function which I'm going to consider is nothing but 1 by 2 y hat minus y of a square. Yeah, y hat minus y of a square. So this is going to give me a difference between the expected one and the resultant one, the one that we have received from a neural network calculation. Okay, so where I'm going to use it and how it is going to help me out in terms of learning a pattern. So this is going to help me out in terms of changing my weights and the biases, so that I will be able to build a relation, so which is going to be perfect enough to give me the expected output. Yeah. So how I'm going to change a weight? A formula is very simple. The new weight. So we have so many weights over here, right? We have W1, W2, W3, W4, W5, W6, and we have a biases B1 and B2. So this new weight that I'm trying to find out, the generic formula is new weight is basically a old weight minus eta, right? Minus eta. So this is the symbol of eta. And then partial order derivative of this loss with respect to a W. Yeah. And then a new bias is basically old bias minus eta and partial order derivative of loss with respect to the bias. Now, this is something that we are supposed to find out. So we are already aware about a old weight, the existing one, by the way, right? At this particular point, at this particular stage, right? So whatever is the old weight. So we are already aware about this old weight. Now, what is the meaning of this eta? So eta is called as, or maybe I can write it down here. So eta is basically called as learning, Learning, learning rate. Now, just look at this formula. So here what we are trying to do, so we are trying to change a weight and we are trying to change our biases, and eventually we will try to find out a new weight and the new biases. With respect to what? With respect to the old one, and with respect to the rate of change of loss with respect to weight, rate of change of loss with respect to biases, partial or derivative of loss with respect to weight, partial derivative of loss with respect to biases. Eventually this will turn out and this will try to give me the new weight and the new biases. Now here when we are trying to change it, right? So eta is a parameter. Now, so this is a learnable parameter. You can try to give a different value of a eta, and this is going to help me out to change a weight by a certain ratio. For example, so if we are trying to learn something, so if we are learning very fast, right? If we are going through page by page, and in an hour, so if we are going to complete hundreds of pages, it simply means that we are trying to change our learning. We will end up learning, but the thing is that we will not be able to retain each and everything. So if we are learning very fast, and if we are learning very slow, so again there is a possibility that I will start forgetting whatever things that I have learned in a past. So same kind of a things which has been applied even with respect to a neural network. So here we always try to take a value of eta in a balanced way. So in general, maybe 0.1, maybe 0.01, maybe 0.001, or maybe 0.5, this kind of a value we try to consider. And these are the learnable parameter. These are the parameter that, sorry, these are like a hyperparameter basically. So these are the parameter that you can try to tune, you can try to experiment with. You can try to experiment with the different kind of eta values. And then you can try to check that which eta value is helping me out in terms of minimizing a loss, means in terms of achieving me a local minima for a particular epoch or for a particular input or for a particular iteration that I'm trying to do with respect to a neural network. So the main thing, so eta is a constant, right? Eta is a constant, and I can try to check with a different constant over here. I have to take the balanced one. So the main part is that I have to find out partial order derivative of a loss with respect to W and partial order derivative of a loss with respect to B, a biases, for each and every weight and for each and every biases. If I'm able to find out that, obviously I will be able to change it. Now, how I will be able to find out that particular part? Now, here is my loss function, right? Here is my loss function, as we all can see. Now, what is a derivative of this loss function? What is the derivative of this loss function with respect to? So let's suppose if I'm asking you that try to find out a derivative of loss with respect to y hat. Now, what it is going to be? So here, if you are going to expand this entire equation, so this equation is x minus y of a square divided by 2, right? So if you are going to expand this L, so it will be something like 1 by 2 x square minus 2, sorry, not x, I'm just writing it with respect to x. So y hat of a square minus 2 y hat y plus, I would say, y of a square, right? This is going to be the equation. This is going to be the equation. Now, if I'm going to ask you that try to find out a derivative, this derivative basically. So derivative of this L with respect to y hat. Hypothetically, if I'm asking you, so what it is going to be? So here, what is a derivative of, let's suppose my y is equals to x square. Now, if I'm going to ask you that try to find out dy by dx, so it is going to be what? So 2 into x to the power 2 minus 1. So eventually it is going to be 2x, right? And derivative of anything with respect to constant is going to be 0. We all know about it, right? So we all have gone through this kind of a things in our childhood. So here it is going to be 1 by 2 and then y hat squared. So we are trying to find out the derivative with respect to y hat. So it is going to be 2y hat minus, so here it y hat to the power 1 we have, so 1 minus 1 0, so it is going to be 2y, and then this part is going to be constant, right? This part is going to be constant for this derivative. Y is constant because we are trying to find a derivative with respect to y hat, so it's going to be 0. Now if I'm going to rewrite this equation, so here it is going to be 1 by 2 and then 2y hat minus 2y. Now take out 2 common, 2 by 2. So it is going to be y hat minus y. So derivative of loss with respect to y hat is basically y hat minus y. Now we are able to find out this, but keep it aside. I'm going to use it. I'm going to use it somehow. So I'll try to show you. So where I'm going to use it, by the way. First of all, try to find out a loss in terms of a number. So what is my loss? 1 by 2 y hat minus y of a square. So what is the value of y hat that we have received? So value of y hat that we have received is equals to 0.75136. And what is the value of y? 0.01. Okay. So let's try to find out here this loss, by the way. So it is going to be 0.75136 minus 0.01 of a square, and it is going to be like a 0.2748. So this is the loss that I have received. So clearly there is a difference between my expected value of y and the predicted value of a y. Okay. And eventually we are able to even find out that what is a derivative of loss with respect to a y hat. But at the end of the day, I have to work on this equation and this equation for each and every w and each and every b. So each and every weight and each and every biases, so that I will be able to find out a new value of w. I will be able to find out a new value of a biases. I will start doing it in a backward direction. Backward direction means, so first of all, I'll try to start from this bias B2 and then W5, W6 and eventually B1, W1, W2, W3, W4. In this manner, I will start changing it. I will start changing it. So to change this one, what is a mathematics that we have to establish? Let's try to understand that part. So here, ultimately, right? Ultimately, what we are supposed to find out. So ultimately, we are supposed to find out a rate of change of, or I can say a partial order derivative of L with respect to the output, which was the input in an output layer. So now if I have to rewrite this equation with the help of chain rule, so I can try to do one thing. So I can write it down in this way. L by ON, and then I can try to multiply and I can try to divide it by delta of y hat and delta of y hat. Maybe I can try to rewrite in this way, same equation. So this by y hat into delta of y hat by delta of output, which was on an input layer of the output, basically. So here I'm talking about. So this layer, right? This particular layer, this particular point I'm talking about. Okay, fine. So let's try to find out this value and then this value. If I'm able to find out this value and if I'm able to find out this value, then obviously I will be able to find out this value, which will help me out, right? Which will help me out in terms of changing a weight and in terms of changing a biases. Okay, so this dl by dy, right? Dl by dy. So we can try to rewrite in this way. So dl by dy hat. So dy hat is nothing but y hat minus y. Y hat minus y. So I can try to write it in this way because I have done this derivative. And from this derivative, we are able to find out that rate of change of loss with respect to the output, which is y hat, is y hat minus y. So the first term, right? The first term I can mathematically even write in this way, that value of y hat is what? So value of y hat is 0.75136 minus 0.10, which is a value of y. So eventually it is going to be 0.74136. Okay, so this is something that we are able to find out. Now, what about this? What about this particular term? So delta of y hat with respect to a input. So delta of y hat with respect to input. So means rate of change of output, rate of change of y hat is my output. So rate of change of y hat with respect to my input. How I will be able to find out that? So if you remember, we have used basically a sigmoid function over here to get y hat. How I have received y hat, by the way? So I have received y hat. If I'll talk about like receiving a y hat. So I have received y hat how? So basically I have passed this O in into a sigmoid function. So I have passed this O in into a sigmoid function. And what was the sigmoid function? So 1 by 1 plus e to the power minus of x means minus of O of in. Right? This is what I have passed, and based on that I was able to receive basically y hat. This is called as y hat, by the way, for me, right, as per the equation, and this has helped me out to get a y hat. Now I have to find out a derivative of this y hat, means this one with respect to O in, means with respect to the input, because input is eventually giving me the output when I'm trying to pass my input into my sigmoid function. Okay, that's completely fine. So now what is a derivative of this sigmoid function, e to the power x? So what is a derivative of the sigmoid function means? So what is a derivative? So what is a derivative of this sigmoid function with respect to x, right? With respect to x. So it's nothing but a sigmoid of x 1 minus, if you are going to find out the derivative, right? X. So this is going to be the derivative. Yeah, this is going to be the derivative, as simple as that. Fine. So let's try to substitute, and this is the sigmoid function. Basically, this sigmoid function is basically my y hat, right, with respect to O in. So eventually, right, eventually what I can do is I can try to write it down that here, so here, derivative of y with respect to O in is equal to y hat 1 minus y hat, because y hat is what? Y hat is my sigmoid function. So I'm just replacing sigmoid function with my y hat. Eventually y hat is basically a sigmoid function, right? Or at this particular layer. Okay, so what is the value of this one, this particular term? So I'm going to compute a value of y hat in both the places. So what is the value of y hat? So 0.76, sorry, so 0. Let me erase this one. So here it's going to be 0.75136 into 1 minus 0.75136. Now if you are going to do the math, so it will be going to be approximately 0.1868. Now this is the value that I will be able to get for a rate of change of y hat output with respect to the input. Okay, fine. Ultimately, what is supposed to be find out? So ultimately, I'm supposed to find out this one, and this one is a combination of this and this. So for this, I'm able to find out the value. For this, I'm able to find out the value. So I know a value of both now, right? I'm able to find out the value of both now. So basically, I'm using a chain rule over here. So with the help of chain rule, so I'm able to find out this particular value. Ultimately, rate of change of loss with respect to input, I'm supposed to find out, because this input is responsible for giving me the error. Input is responsible for giving me the loss. So here, right, so here if I'm supposed to write down once again, so rate of change of loss with respect to input is going to be, right, is going to be L with respect to a y hat into y hat by input, right? Simple chain rule. Now I know the value of this, right? So what is the value of this? So value of this is going to be 0.74136. So 0.74136 into, right, into this value. So 0.1868. Now if I'm going to multiply, so it is going to be approximately 0.1385. Okay, so I'm able to find out this delta value, or I'm able to find out this rate of change of loss with respect to the input that I have given. Rate of change of loss with respect to input that I have given, I'm able to find out. Let me redraw a neural network, right, over here. So we have an input layer, then we had an output layer. Now this is how this entire neural network was connected, right? This is how this entire neural network is connected. I'm able to get y hat, right? I'm able to get y hat. This is where our input, output, input was there, right? Inside the sigmoid function, I was trying to pass it. And now I'm trying to do a backward propagation where I have a weight 5 over here, where I have a weight 6 over here, and then we have a bias 2 over here. Now I have to find out a value of new weight 5. I have to find out a value of new weight 6, and I have to find out a new B2, a bias 2. This is something that is my objective, and I have to find out that particular one. How I will be able to find out that one, right? How I will be able to find out that one. So here, so far, I'm able to find out a rate of change of loss with respect to this input. Rate of change of loss with respect to this input, I'm able to find out. That's completely fine. Now I have to find out a new value of a W5. So new value of W5 is going to be a old value of W5 minus eta. So eta is going to be constant that we are going to consider, and it's called as learning rate, and rate of change of loss with respect to a W5. Then only I will be able to find out a new value of a W5. Then similarly, if I have to find out a new value of W6, same formula will be applicable, right? So rate of change, so old W6 and then minus of eta, rate of change of loss with respect to W6, because this W5, W6, B2, everyone is combinedly, everyone is affecting my loss altogether, right? So with respect to a loss, I have to find out a new value, or with respect to loss, I have to change a value of W5. With respect to loss, I have to change a value of W6. With respect to loss, I have to change a value of a biases B2. Okay, that's completely fine. So here the main component is this one, right? The main component is basically this one. So how I will be able to find out this main component? So I can try to write down this main component in this way: delta of loss or partial derivative of loss with respect to W5 is equal to, right? With respect to this one is equal to, I can try to write it down, that this equation, this one, right? So DL partial order derivative of loss with respect to the input that I have given, the combined input of W5, W6 and B5 that I have given, and the input that I'm receiving from this one, right? So I can try to write it down, this rate of change of loss with respect to this one, maybe in this way, dot H1, the output that I have received from the H1. Now, if I'm going to do the computation, so it is going to be, this value is going to be 0.1385. So 0.1385. And what is the value of H1, by the way? So value of H1 that we have already computed is 0.59327. So eventually this value is going to be 0.0822. Okay. So this value is going to be 0.0822. Now, what is going to be this value for a W6? So same, right? This into H2. So H2 is nothing but the output that we are receiving here, right? From this neuron, from this particular hidden neuron that we have received. Okay. So again, I'm going to do a calculation over here for this one. So here 0.1385 into, what is the value of my H2, by the way? So my value of H2 was 0.59688. So here H1, but here H2, and this is going to be 0.0827. So this partial derivative of loss with respect to weight, I am able to find out weight 5, and with respect to weight 6, I am able to find out. Okay, that's completely fine. Now, what is a partial order derivative of this loss with respect to a bias B2? So again, this same equation, this one, this like a rate of change of loss with respect to the input that we are giving, because input was the combination of W5, W6 and B2, right? So same. So let me write it down. Okay, so now we have to find out, like I said, we have to find out basically a rate of change of loss with respect to a B2. So how I will be able to find out? So I can try to write this equation in this way. So rate of change of loss with respect to B2 is, with the help of chain rule, so rate of change of loss with respect to B2 is nothing but we are going to multiply and divide with O in here, right? O in here. Now, so rate of change of loss with respect to O in into, I can try to write delta of O in divided by rate of change of B2. Okay. Now, what is this, by the way? So what is this, by the way? So this value we already know, right? This value we already know. So rate of change of L with respect to O in, and this value is basically 0.1385. So I can try to write it down. This value is going to be 0.1385. Okay. What about this value, rate of change of O in with respect to B2, rate of change of O in? So what is this O in, by the way? What is this O in? So if you remember, we have already written O in, right? We have already written O in. So here O in is what? H1 into W5 plus H2 into W6 plus B2 means whatever we have on an outer layer of neural network, so H1 into W5 and H2 into W6 plus B2. So this is going to be O in, by the way, as per the neural network. Okay, so let's try to write it down over here. So W5 H1 plus W6 H2 plus B2. Now this is going to be my input. Now, if you are going to find out a derivative with respect to B2, so this is constant because there is no B2 over here. So this will become 0. This is constant, this will become 0. And here B to the power 1. So it is eventually going to be 1. So here, this entire term is going to be 1. So 0.1385 into 1. And this is going to be 0.1385 eventually. Simple, right? So now we are able to find out even a rate of change of loss with respect to a B2. And this was the whole idea. This was the whole objective, because unless and until I'm not able to find out a rate of change of, so as per this equation, so I have to find out a new value, but to find out a new value, I have to find out a partial order derivative with respect to the old value. Now, for a weight 5 and weight 6, I am able to find out this term. And even for a biases, I am able to find out this particular term. Now I'm in a position, basically, right? Now I'm in a position, so where I will be able to find out a new value of weight, and I'm in a position to find out a new value of a biases. As simple as that. So now I'm in a perfect position where I can try to do a computation for a new value of weight and a new value of a biases. So fine, we can try to do it. So let's go ahead and let's try to do it, guys. Okay, so we just have to do a computation once again. So a new weight is equals to old weight minus eta, which is a learning rate, and partial order derivative of loss with respect to the weight. Okay, old weight. Now a new bias is equals to old bias. New bias is equals to old bias minus eta, which is a learning rate, and then rate of change of loss or partial derivative of loss with respect to the B old. Okay, that's great. Now, so for this W5, W6, and for B2, we are aware about this and this. Yeah, we are aware about this and this. Let's suppose I'm assuming that eta is going to be 0.5. This is just my assumption. I can try to take any other values as well. So this is just my assumption, means just my assumption. So if I have to find out a new value of weight, so old value of a weight. If I have to find out a new value of weight means, so let's suppose I'm doing a calculation for maybe a W5. So new value of W5 is going to be, so NW5 is going to be old W5 minus eta, which is 0.5, and partial order derivative of loss with respect to a W5 old. Now I'm aware about this term, I'm aware about this term. So let's do a computation. So my old value of weight 5 was what? My old value of weight 5 was 0.40. My old value of weight 6 was 0.45. And my old value of bias B2 was 0.60. I'll be considering that value itself. Okay, let's come down. So here we can try to do a calculation. So 0.40 minus eta, which is my assumption, by the way. And then we have calculated a rate of change of L with respect to W5. What is that? So let's go and check rate of change of this. So basically 0.0822. Okay, so 0.0822. Now, if you are going to do a calculation, you will be able to find out 0.3589. Now, this is my new value of weight. So I'm able to update my weight 5. Yeah, I'm able to update my weight 5. Similarly, I'll try to update my weight 6. I'll just write W6, simple, right? So I'm not writing old or new. So I'm just writing a W6 over here. So again, my old W6 minus my constant, which is eta, which is my learning rate, into rate of change of L with respect to W6, which I was able to find out as what was the value? 0.0827. Okay, that's great. So 0.0827. So if I'm going to do a math over here, so I will be able to get 0.4086. Now, what is the new value of biases? So old value of bias, by the way, so old value of bias was 0.60. If you will go and check, eta is 0.5, rate of change of a loss with respect to bias B2 is 0.1385. And if I'm going to do a math, so I will be able to find out 0.5308. So in a backward propagation with respect to a loss, now I am able to change a value of W5, W6 and a B2. So if I'm going to redraw my neural network, so where I had an input and then I have a weight connection in between here, and this is my y hat. So with respect to y and y hat differences, so here I had a W5, here I had a W6, and here I have a B2, and I have now a new value of W5, W6, and a B2. So what is the new value of W5? So new value of W5 is 0.3589. What is the new value of W6? New value of W6 is basically 0.4086. So 4086. And what is the new value of bias? B2. So 0.5308. So I'm able to find out a new value of W5, W6, and a B2. This objective is achieved. Yeah, this objective is achieved in a backward propagation. We are able to change this weight. Now it's time to change B1. It's time to change W1, W2, W3, W4. So if I will be able to change it, it simply means that in a backward propagation, I'm able to change all the weights and the biases, but with respect to what? That matters a lot. So what with respect to a loss? L basically, right? So let's go ahead guys and let's try to change it. So again, I'm going to follow the same principle. I'm going to follow the same philosophy. I'm not going to follow anything different. So the way I have find out the value of W5, W6, and B2, in the similar manner, I will try to find out the value of basically other one. So here, let me change my pen and I'm going to change a value for this one. So here, right? So here, this is my neuron H1 and this was my H2, hidden layer H1 and so in this hidden layer, so there is a neuron called as H1 and there is a neuron called as H2. Even over here, I had a sigmoid function. Even over here, I had a sigmoid function. As a activation function, I have chosen. And even over here, I have used the sigmoid function, but as an output function, I have chosen. Just for the simplicity so that I don't have to go ahead with the different kind of a derivation. So here what we can do is, so we can try to find out a loss. We can try to find out a loss with respect to what? With respect to H1. We can try to find out a loss with respect to H2. We can try to find out a loss with respect to what? With respect to a B1. If I'm able to do that, right? If I'm able to do that, then only I can say that, okay, I will be in a position to change these weights, because even these weights are contributing over here in terms of getting me the output, right? So I'm going to follow the exact same philosophy that I have already followed above to change my W5, W6 and a B2. And I will try to find out a loss with respect to H1. I will try to find out a loss with respect to H2. I will try to find out a loss with respect to a B1 as well. So let's do it. Let's do it now. Yeah, so let's write it down. I know this entire thing is going to be a little bit complex, but yeah, it's not complex. If you are going to do it in a step-by-step manner, it's pretty much like amazing to see this entire calculation. And once in a life, I believe those who are trying to learn a neural network, they should do it, right? They should do it so that they will be able to understand things in a much better way. Okay, so here what I can do is, so if I have to find out a loss with respect to H1, so I can try to write it down that loss with respect to, right? With respect to basically the output. So output into W5. This is the loss with respect to H1. And we know this particular value. So this value is 0.1385 into, what is the weight 5? So weight 5 is basically 0.40. So eventually it is going to be 0.0554. Now, loss with respect to H2, if I have to find out, so loss with respect to H2 is going to be what? So here it is going to be again same. So loss with respect to the output into weight 6, and this is going to be 0.1385 once again into, what is the weight 5? What is the weight 6? So my weight 6 was basically 0.45. 0.45. So it is going to be, my weight 6, 0.45. Yeah, that's correct. So 0.0623. Okay. So this is something that we are able to find out. Yeah, this is something that we are able to find out. Now, so I have to even find out for this one, right? This is something that we are able to find out rate of change of like a loss with respect to H1. Fine. But we have to even find out a rate of change of H1 or partial derivative of H1 with respect to input, the way we were able to find out y hat with respect to like a output, like the input of the output that we were trying to give. So we have to find out even this particular term. So we have to find out basically rate of change of H1 with respect to H input, means what will go here with respect to what will come out. And we know that there is a sigmoid function in between. So the same thing that we have done above. So to find out, so we were using a sigmoid function derivative, and it's pretty much simple, 1 minus H1, right? This is the sigmoid derivative that I'm using. So it is going to be 0.59327, 1 minus 0.59327. This was the H1 that I was able to receive out. So output of the sigmoid function. So it is going to be 0.2413 for this particular layer. For this particular layer, right? For this particular layer, I'm trying to do the derivation. Okay, so these two we are able to find out now. So final delta, so final, right? Final rate of change of loss with respect to H input is nothing but this into this, right? This into this. We are doing a chain rule operation over here. So it is going to be 0.0554 into 0.2413 is equals to 0.0134 if you are going to do the math. So this is required. Rate of change of loss with respect to input means whatever loss that we are receiving over here with respect to this input, with respect to this input, and then with respect to this input, because this input is responsible for a loss over there, right? And then only I will be able to change this, this, and this. Okay. So here again, let's do the same thing for this one. So rate of change of basically here maybe I can try to write. So rate of change of H2 with respect to rate of change with respect to H2 in. Yeah. So it's nothing but it's a sigmoid function in between. So we can try to write it down in this way, and then 0.59, and there is nothing different I'm writing, guys. So it's a same thing which we have already used. So I'm writing it down. So 0.0 sorry. So 0.5969688. Now this will become what? So this will become 0.2406. So eventually, if I'm going to do a chain rule, so this into this, it is going to give me rate of change of loss with respect to H2 input, right? H2 input, which is nothing but this into this, right? This into this. So here, this into this. So 0.0623 into 0.2406 is going to be 0.0150. Okay. So we are able to find out rate of change of loss with respect to H2 input and H1 input. So for this neural network, so we are able to find out a rate of change of loss with respect to the input which we are giving from here, right? Input that we are giving here, the mark that I am trying to create over here. Now, once we are able to find out that, right? Once we are able to find out that, then what we have to achieve? So even for this layer, I have to find out a new value of W1, new value of W1. I have to find out a new value of a W2. I have to find out a new value of W3. I have to find out a new value of a W4. And what is the new value of W1, 2, 3, 4? So it is going to be old value of W1 minus eta learning rate, rate of change of L with respect to rate of change of W old one, right? Then new value of like a W2 is going to be old value of W2 minus eta rate of change of loss with respect to old value of W2. So new value of W3 is going to be old value of W3 minus eta loss with respect to W3. And the new value of W4 is going to be old value of W4 minus eta learning rate O4. Now, so this is the component we are supposed to find out. This is the component which is supposed to find out. So how I will be able to find out this particular component, by the way? So I will be able to find out this component. Now this component, like delta L by delta of W old 1 is going to be what? So it is going to be, right? It is basically going to be delta L with respect to a delta H1 input, right? Delta H1 input into it is going to be x1. So x1 was the input. Because of that, we are able to receive this one. So rate of change of L with respect to W is going to be this, right? Similarly, so rate of change of W2, 3, 4 is going to be same, right? With respect to H input 1, H input 2, depends. So what kind of an input, what kind of a H input that we are going to consider. Okay. So this is going to be my this one. And here, so I know the value of this. So rate of change of L with respect to H1, which is going to be 0.0134 into 0.05. Value of x1 is 0.05. So it's going to be 0.00067, a minor change, right? Now, similarly, rate of change of L with respect to W2, right? With respect to W2. So it is going to be what? So with respect to W2, loss with respect to H1 input into x2, right? X2 input. So 0.0134 into 0.10. Value of x2 was 0.10. So it's going to be 0.00134. Okay. Now, what is going to be a rate of change of L with respect to W old 3, third basically? So it's going to be delta of L with respect to H2 input, and then into basically x1. So it's going to be 0.0150 into 0.05 is equals to 0.00075. Now, what is the rate of change of loss with respect to W old 4? So W old 4 is going to be rate of change of loss with respect to rate of change of loss over here with respect to H2 in into X2 is going to be 0.0150 into 0.10 is equals to 0.00150. So now we are able to find out a partial derivative of loss with respect to all the weights. Okay, that's completely fine. Now we have to find out a partial order derivative of loss with respect to even B1, because we have to change the value of B1, right? We have to change the value of B1 as well. So for that, it is basically going to be a rate of change of loss with respect to H1 input plus rate of change of loss with respect to H2 input. That is going to give me basically rate of change of loss with respect to a bias. So 0.0134 plus 0.0150 is equal to 0.0284. So now here, I know all of these components. Now, if I know all of these components, I will be able to update and I will be able to find out the new value of W1, W2, W3, W4 and a B1. So W2, W3 and then a W4 and then the B1, a new value of all of these things. So what is the new value of this one? W1. So old value of W1, which is 0.15 minus eta into rate of change of W1, rate of change of loss with respect to W1 is going to be 0.00067. So it is going to be 0.1497. Now, so what is the new value of W2? New value of W2 is going to be old value of W2 into eta. So eta is 0.5 into 0.00134 is equals to 0.1993, right? Okay. Now, what is the old new value of W3? So new value of W3 is going to be old value of W3. So old value of W3 is 0.25 minus eta 0.5 into 0.00075 is equals to 0.2496. What is the new value of W4? New value of W4 is going to be old value of W4 minus 0.5 into eta into 0.00 rate of change of loss with respect to W150 is equals to 0.2993. What is the new value of biases? So old value of bias 0.35 minus eta. So 0.5 into like a rate of change of loss with respect to bias is going to be 0.0284. All this value we were able to find out above. So 0.3358. So this is how we are able to find out a weight W1, W2, W3, W4. Now you are able to see that in a second layer, right? In a first layer, we were able to change a value marginally, right? We were able to change a value which is like a visible to me. So there was a old value of W5 is equals to 0.40 and now it's become 0.35. Significant changes we are able to see. W6 significant changes we are able to see. As we are going deeper, right? As we are going deeper on a second layer, the changes that you must be able to observe is very less, right? It's again going forward. So I'm going to talk about a vanishing gradient problem. So here you are able to see, because as we will go deeper and deeper and deeper, the changes will be less and less. So now this is the new value of W1, W2, W3, W4 and B1 we are able to find out, and it's very less amount of changes that we are able to find out. Now, if you are going to draw a new neural network now, right? If you are going to draw a new neural network now, so now your new neural network after this first backward propagation, so after this first backward propagation will look like this one. So again, architecture is not going to change. It is going to be same. Your X1 and X2 is again not going to change, right? Your X1 and X2 is going to be exact same. So it is going to be 0.05 and it is going to be 0.10. If you're trying to give the same value once again, right? Otherwise you can go ahead with the second row over there. So here, the new value of W1, W2, W3, W4 and biases, everything has changed. W5 and W6 has changed, and even your B2 has changed. So all of these value basically has changed completely. So initially, if I'll go here, so W1, W2, W3 and W4. Let me write it down here. W1, W2, W3 and W4 and W5 and W6, and this is going to give me Y hat. Everything has changed, right? Everything has changed, and even B1 over here and B1 over here and B2 over here has changed. Now, if it has changed and if it has changed with respect to the loss, means a difference that we were able to receive with respect to expected Y and the predicted Y. So obviously this time when you will try to find out a new value of output, means new value of a Y hat with the same data, you will be able to find out that loss has decreased. Loss has basically decreased, and it has decreased how? So it has decreased based on the backward propagation. Backward propagation we have done how? So with respect to a loss, we are changing all the values. So this is how, guys, a calculation is going to happen. And I advise everyone to look into this calculation at least once in a life. It looks like a tedious in a very first place. It looks like overwhelming in a very first place. But believe me, this is the real knowledge. This is the real learning. Once you are going to do it, you will be able to understand it for a lifetime. And I have just used a very simple neural network over here. Now just imagine, so if your neural network size will increase, so how complex this entire calculation will be. So see, calculation is like just we are trying to do some sort of a basic arithmetic operation and then a derivation. The thing is that we have too many parameters, and all those parameters depends with respect to our losses. So with respect to loss, we are trying to decrease it. With respect to loss, we are trying to do a computation. Because of that, it became lengthy. Right? Because of that, it became lengthy. But hope all of you have enjoyed this entire lecture. And yeah, so please give me your comment. Please give me your feedback. if I have made some sort of a number mistake in between, which I think I haven't, because I have already prepared these numbers right before this lecture recording. But yeah, so if there is some mistake, so you can try to rectify it. I'm leaving this up to you. With that, thank you so much, everyone. Take care and see you again in my next lecture. Okay, so welcome to the lecture once again, guys. And in this lecture, I'll be talking about activation function. Activation function, which has been used in between a neural network, hidden layers. And first of all, I would like to talk about why we are going to use a activation function and what is the advantage that you all will be able to get if you are going to use an activation function. Because by default, you have to use an activation function. Without using activation function, you will not be able to do any kind of a training inside a neural network. So let me share my screen, and here is a activation function lecture. So let me write it down. Activation function. Now, so first of all, we have to understand that why we are using a activation function inside a neural network. For example, so if I'm going to draw a simple basic neural network, and here we have an input. Let's suppose we have x1 and we have a x2. And from here, so it is going inside a hidden layer, and then it is going inside the output layer. And yeah, so let me write it down. So we have a weight W1, we have a weight W2, we have a weight W3, we have a weight W4, we have a biases over here, B1, maybe I'm going to consider B1 over here, and then we have a B2. And then eventually I'm going to receive Y2. And here, so we have a W5, and here we have a W6. So let's suppose if I'm trying to consider this kind of a neural network, and there is no activation function, right? There is no activation function which I'm using over here. Again, there is no output function, let's suppose. So now if you are going to do a calculation, so here, right? So here, so what is the output that you are going to receive? So H1 and then H2 in a hidden layer. So what is the output of the hidden layer H1 and hidden layer H2? So hidden layer H1 is going to give you output, which is going to be equal to X1 into W1. So X1 into W1 plus X2 into W3, X2 into W3 plus B1. So this is the output that you will receive here if there is no activation function at all. I'm not using any function in between. And then similarly for H2, so what is the output that you are going to receive? So X2 and into W3, sorry, so for H2, right? So X2 in X, sorry, so let me write it down. X1 into W2 plus X2 into W4 plus bias B1, right? This is the output that you will receive from H1 and H2. So H1 and H2. And then what is the output that you will receive here? So output that you will receive here, let's suppose I'm not using any kind of output function as well. So here my Y hat is going to be H1 into W5 plus H2 into W6. Now just replace H1 and H2 with this equation and this equation. So it is going to be X1 W1 and then plus X2 W3 plus B1 into W5 plus H2. So which is X1 W2 plus X2 W4 plus B1 and then into W6. Now this is going to be my Y hat. Now just look into this equation, guys. Just look into this equation. So this equation is equivalent to Y is equals to mx plus c. So kind of a, so not kind of, I would say. So this is the equation of a linear, this is the equation of the line, by the way. So this is the linear equation. It simply means that if I have a linear equation, I'm not going to understand or I'm not going to learn anything which is non-linear inside my data set. Now, if I'm going to consider an example of an image, if I'm going to consider an example of any kind of a text information or sentences or maybe a paragraph, so obviously we'll be having a lot of non-linear, or not lot of, almost it will be a non-linear relation. I have to learn those non-linear relations. So I need someone who will help me out in terms of learning those non-linear equation or non-linear relationship between the data. And that is that, otherwise this entire equation, this entire neural network, doesn't matter how big my neural network is, this entire neural network is going to be a linear. So it will only be able to understand a linear pattern. It will not be able to understand a non-linear pattern. So to introduce a non-linearity into my neural network so that it will be able to adjust its weights and biases, which is a trainable parameter, based on the non-linearity into a data set. So to achieve that non-linearity, we need an activation function. And many people feel confused when we say and when we ask a question that why even we are using activation functions. Now here is the answer. This entire equation that we have written, so it's a linear equation, a complete y is equal to mx plus c kind of equation that we have written over here. So this is where activation function comes into a picture, where it will go and it will try to break a non-linearity into the entire learning pattern. Yeah, entire non-linearity it is going to activate. Now, so it is also going to activate a gradient based learning. Means, so as we are going to progress, as we will start changing the value of weight and biases, so with respect to loss, right, with respect to loss means with respect to a difference between y and y hat, it will allow me to change a value of a weight and the biases, which is responsible for building the entire relationship into a data. So non-linearity is one of the factor. Then enabling a gradient based learning is another factor, I would say. Plus it is going to increase a sparsity as well. Sparsity means what? So where I'm looking for some activation of a neural network, which I will talk eventually in a detailed way going forward. So these are the advantage of using an activation function, and without activation function, you will not be able to build any kind of a neural network. Now, the question is that what kind of a new activation function I should know, or what kind of activation function I'm supposed to use. So one by one, let's try to understand all kind of a activation function, a general common kind of activation function that we can try to use. Even you can try to do your own research and you can try to build your own activation function. The very famous and the first activation function that we all use to study is called as a sigmoid. So sigmoid activation function. So sigmoid function we can try to use as an activation function. So where for any input x, it is going to give you output 1 plus e to the power minus of x. So this is the output that you are going to receive. So the output range for this particular function is always going to be between 0 to 1. Doesn't matter what kind of an input you are going to give, but yeah, at the end of the day, you will end up receiving an output between 0 to 1 for any kind of an input that you are going to give over here. If I'm going to plot it with respect to a graph, so any kind of an input that we are going to give, any kind of input means minus infinity to a plus infinity, any kind of a x value we are going to give, it will always try to yield a result in between 0 to 1. Always it is going to give me a result between 0 to 1. So this is what sigmoid function is going to do. Now, a next function, a next famous activation function is basically called as tangent or hypertangent over here, which is called as tan h. Now, what is the formula for tan h? For any given input x, your output is going to be e to the power x minus e to the power minus of x divided by e to the power x plus e to the power minus of x. This is the formula of a hypertangent. Yeah, it will always try to give you output between minus 1 to 1. Doesn't matter what is going to be the input, right? What is going to be the input? It will always try to give you a output between minus 1 to 1. So if I'm supposed to draw a graph over here, so for any kind of an input between a minus infinity to positive infinity, any kind of an input that we are going to give, so it will always try to give me an output between minus 1 to 1. So this is basically a hypertangent activation function that I can try to use. Now, so there is another activation function, which is famous one, and frequently you all are going to use it, called as rectified linear unit. So ReLU, basically rectified linear unit. So for any kind of input inside this rectified linear unit, so what it will do is it will always try to give you an output between maximum of this to this. Means only on a positive side it is going to give you the output as a maximum. For example, So for any kind of a input that we are going to give, so if I'm going to give a negative output, it is going to be 0. Simple. For negative output, it is going to be 0. For any kind of a input, sorry, for negative input, the output is going to be 0. For any kind of a positive input between 0 to any number, it is going to give me a maximum. It is going to give me a maximum. This is what I have written. So it is going to give me a maximum. So this is how this graph looks like for any kind of a input. Now there is another function. There is here the output range is going to be 0 to infinity. So because it is giving me max, right? Whatever will be the maximum value between 0 to any input, right? So it is going to give me a max. So for any kind of a input, it is always going to give me that maximum value. Now there is something called as a leaky ReLU, which is again like trying to solve this vanishing gradient problem in a negative side. So leaky ReLU, leaky rectified linear unit, and this is going to basically give me an output as input x for x greater than 0, right? So the graph is going to be same for x greater than 0, and it is going to give me an output for x negative for any input value which is lesser than 0. So it is going to give me a value alpha of x. So alpha is a constant that we are going to consider, and usually the value of alpha will be 0.01 usually, right? So basically it is going to give me an activation even on a negative side. So whenever I'm going to input a negative data, it is going to give me some sort of a output. In case of a ReLU, for any kind of a data which is lesser than 0, means a negative data, it was trying to make my neurons absolute dead, means it is going to give me 0. So if I'm going to enter minus 10, obviously it is going to be 0. If I'm going to enter minus 10 million, it is going to give me a 0. So there was a problem. There was a problem of a dead neuron with respect to a ReLU, and which is been solved by a leaky ReLU. So this is how this graph will look like. So for any positive value between 0 to like x or positive infinity, so it is going to give me the maximum. And then for any negative value, so it is going to give me some value at least. That some value is going to be alpha, which is 0.01, means it is not going to give you the maximum. It is just going to give you that value multiplied with 0.01, means it is going to give you the smaller value as compared to the input. So this is something that is going to happen with respect to a leaky ReLU. So this is again one of the another function that we can try to use it to achieve a non-linearity into the data. Then there is a function which is a famous function, I would say. So the famous function is called as a Swiss function. Swiss function. So this, for any value that you are going to enter into a Swiss function, so it is going to give you that value into a sigmoid of x. So technically it is going to be this into 1 by 1 plus e to the power minus of x, right? So this is something that Swiss is going to give you at the end of the day. So technically the ranges of this entire things is going to be in between negative of 0.28 to infinity for a Swiss function. And if I have to draw a graph of this Swiss, so this is how the graph of Swiss will look like. So let's suppose I have a coordinate over here 0.0. So for any kind of a negative input, so this is how this graph will look like, by the way. So for any kind of a positive, it is going to give you this value, and for any kind of a negative, so it is going to give you something like this value. So this is the graph of the Swiss function that you all will be able to find out. So these are the famous activation function, guys, that we all are going to use. Apart from that, so there is an activation function called as softplex, Gaussian error linear unit, or there is something called as even a exponential linear unit. Let me write it down, by the way. So ELU, which is nothing but exponential linear unit. ELU, exponential linear unit. So for any given x as an input, anything that you are going to enter as an input, so it is going to give you x, means the same value, if x is greater than equal to 0. And it is going to give you for negative of x, it is going to give you basically a value alpha e to the power x minus 1. So this is the value that you will be able to find out with respect to this one. So the final ranges where it is going to give you a value is negative of alpha to a positive infinity, negative of alpha by the way. So negative of alpha to a infinity is going to give you the value. So this is again another activation function that I can try to talk about. And as per the different use cases, we are going to use a different kind of activation function, whether it's a sigmoid, whether it's a tanh, whether it's a ReLU, whether it's a leaky ReLU, whether it's a ELU, whether it's a Swiss activation function. All of these functions will be used in a different context. It depends upon the problem that we are going to solve. So we are going to learn that part as well, right? We are going to even learn that where we are supposed to use which kind of a activation function, so that I will be able to get a maximum advantage. But the whole idea behind introducing an activation function to achieve a non-linearization into this entire neural network architecture or entire neural network equation. So hope it is going to make sense, and all of you will be able to remember couple of activation function, at least sigmoid, tanh, ReLU and leaky ReLU. This 4 you have to remember, and you have to use it again and again and again. And even I will be using it again and again and again as and when we are going to move into the section. So with that, guys, thank you so much. Take care and see you again in my next lecture. Okay, so welcome to the lecture, guys, and in this lecture I'll be talking about an optimizer. So optimizer is a major component in any neural network. Without that, obviously you can't build it. And why we are going to use an optimizer, what kind of an optimizer that exists, and what is the mathematical equation behind it. So I'll try to give you a demonstration of all the mathematical equation, but yeah, so don't try to mug up all those mathematical equation. It's going to be a little bit complex. But you all will be able to understand technically that why we are going to use an optimizer and what is the purpose that it is going to fulfill during a neural network training. Let me share my screen so that I can write it down something over here. So here, a neural network optimizer. Yeah. Now, the very first question which arises over here, that what is optimizer, by the way, and where we are going to use it. So if you remember, when I was talking about a neural network backward propagation, so I have written something like weight new is going to be a weight old minus eta, which is a learning rate, and then partial order derivative of a loss with respect to the weight, the old weight, obviously, right? Now, this is called as optimizer equation. This is technically called as optimizer equation. Now, there is a name to this particular equation that we are talking about. So optimizer is an algorithm, or technically it's a mathematical function which minimizes a loss, right? Which help me out in terms of minimizing a loss by adjusting a weights and a biases of a neural network during a training. And we have seen that yes, this particular equation, whether it's a weight equation or whether it's a biases equation, so where new bias is going to be old bias minus eta, partial order derivative of a loss with respect to a bias, old bias. So this was helping me out in terms of finding out a new weight and a new biases, and eventually, right? Eventually, when I'm able to find out a new weight and a new biases, so I'm able to decrease a loss. Simple, right? I was able to decrease a loss. So this entire optimizer is going to help me out in terms of decreasing a loss with respect to whatever learnable parameter that we are going to consider. Now, so in a generic manner, I can write this equation maybe in this way. So theta is equals to a theta minus eta, which is a learning rate, right? And then a delta. So then a delta of L with respect to a theta. So again, this equation is not different and not complex. I have just rewritten this one in a generic way, right? That anything new is going to be anything old minus eta, and then partial order derivative of a loss with respect to that, and technically this is what I have written even over here, and technically this is what I have used even before. So when I was trying to talk about a backward propagation, and where I have done a very lengthy calculation, a mathematical calculation to adjust my weight starting from weight 1, 2, 3, 4, 5 and 6, and then my biases B1 and B2. So this is actually called as optimizer. Now there is a name to this optimizer, by the way. So there is a name called as stochastic gradient descent. Let me write it down. The very first optimizer equation that we have already used, but we were not aware about it, right? So it's called as SGD. The full form is stochastic, STOCHASTIC gradient descent, CENT. So there is a name to this equation. In a generic way, theta is equals to old theta minus eta, partial or derivative of a loss with respect to the theta. In a generic way, we can write it down this one. But yeah, it's nothing different. Don't get afraid about it that we are trying to learn something new. We are not trying to learn something new. It's the exact same thing that we have already learned. Now we are just like trying to find out that, okay, this is what it called. So it's called as stochastic gradient descent. And what is the what is the benefit of using a stochastic gradient descent, or what is the special thing about a stochastic gradient descent, SGD? So basically it try to update your weights with a single sample or maybe a small batch of the data, means maybe 2 or 3 records. Based on that, it will try to update your weight. So this is the reason. So we have passed one iteration. So one row, X1 and X2 we have passed. And then in a backward propagation, so we were trying to update it. So this is called as stochastic gradient descent. So where it will try to update my weight or any parameter, maybe a weight and the biases based on the single sample or maybe 2 or 3 sample, which is called as mini batch, right? Mini batch. So it's very simple equation. It's a very fast equation. And again, it works very well with respect to a large data set. So you can feel free to use a stochastic gradient descent, right? You can feel free to use a stochastic gradient descent, but there is some drawback. There is some drawback of this stochastic gradient descent. So generally it gets stuck with respect to a local minima. Local minima means what? So we are trying to achieve a local minima where loss is equal to 0. So we had some loss, then we are decreasing, then we are decreasing, then we are decreasing, and we are trying to fall here. Now let's suppose we are trying to pass a small batch of the data, or maybe after one data itself we are trying to pass, and we will be having so many losses. We'll be having a global minima, global maxima over here. So we have to achieve a global minima, means a loss which is minimized with respect to the whole data. Right, whole data. But what this stochastic gradient descent says that, okay, I will be able to apply this equation, means I will try to change a weight and the biases, whatever learning parameter that you have, even with one data or even with a couple of data, not whole data, right? Even with a single data or maybe even with the mini batch of the data. And that is going to cause for this one to stuck on a local minima. Local minima means like just trying to maintain a loss, just trying to decrease a loss based on couple of data input, right? And that is a problem. That is a big problem that you will be able to find out with respect to a stochastic gradient descent. The second problem is that it never adapts a learning rate, the constant that we are going to use, the eta that we are going to use. Now, so there is a new optimizer people have introduced, scientists have introduced, saying that okay, let's try to use this one, and here, so I'll try to maybe mitigate the issue that you have been facing, right? You have been facing. So at the end of the day, I have to update, I have to find out a new value of some parameter, maybe a weight, right? With respect to old value minus this whole term over here, which is helping me out to change the value. I can write it down maybe as a VT, right? Maybe as a VT, I can try to write it down. Now, what is this VT? So they say that okay, so this parameter, this one that you are trying to use, so maybe we can try to make it momentum based, right? So maybe it is going to take a accumulated gradient and then it will try to change it, just the way we try to see a momentum in a physics, right? We can try to see a momentum in a physics. So on the same principle, they said that okay, I can try to derive one momentum based optimizer. So what is this momentum based optimizer? What is the formula for this momentum based optimizer? So obviously theta is going to be, new theta is going to be old theta minus VT. And this VT is what? What is this component? So this VT is nothing but a gamma V t minus 1, means the previous one, plus eta into a partial order derivative of a loss function, right? So they have technically introduced this particular term. They said that next one, momentum is what? So obviously momentum depends upon the previous instances. So in the similar manner, they said that okay, so whatever changes that you are trying to make, now just replace this entire things with this entire equation. So you will be able to see that this is the new component which has been added. Yeah, this is the new component which has been added, and this component talk about basically a past one, right? They said that okay, so I'm going to try to use a momentum over here, so which is going to help me out to even adopt something from the past. Something from the past, because in a case of stochastic gradient descent, there was no past. It was trying to do some sort of a changes based on the current calculation, based on the current data which is available to me. So this momentum is something that they have introduced. And then based on this one, again, there are like a new equation which people have kept on introducing. But at the end of the day, the philosophy was simple: how to change a weight and the biases, or how to change a learnable parameter, because that is very much important for any kind of a neural network. So keeping that in a mind, the third equation that we are going to talk about is called as NAG. It's called as Nesterov, Nesterov, Nesterov accelerated gradient. Accelerated. Now objective is same, right? Objective is same. Again, this is my objective. At the end of the day, I'll keep on playing with the VT, by the way, right? I'll keep on changing the value of the VT. So objective was same. So new theta is going to be old theta. Old theta means old value, and then a VT. And then I'll try to play with the VT. Maybe I can try to change the equation of the VT. So here in case of Nesterov, so they have given a new equation, this particular part, this particular component. They said that okay, so this gamma Vt minus 1, which was same as a momentum before, plus eta, partial order derivative of this one, but not just with respect to the theta, means not just with respect to W or B, but with respect to theta minus even gamma V of t minus 1. So this time I'll try to find out the partial order derivative, not just with the weight or the biases, but with respect to the the previous value as well. Plus here we have a component. This was the changes which was made, right? This was the changes which was made. And here, so what it does is, so it will always try to look ahead before computing the gradient, which leads to more accurate update. So this is where this Nesterov comes into a picture. Then people came up with another equation. So again, people are playing with the VT. At the end of the day, everyone is playing with the VT, right? So there is something called as ADA grade, ADA GRAD, ADA grade basically. So it's called as adaptive gradient algorithm. Adaptive gradient algorithm. So where again theta is equal to, new theta is equal to theta minus, I can say, minus VT. Now what is this VT here now, right? Which is the value responsible for changing things. So here it's nothing but eta divided by root of capital GT plus epsilon into partial order derivative of loss with respect to theta, means with respect to the input value. So here, what is this GT and what is this like the epsilon that has been introduced? Because eta we know it's a learning rate, and this we already know. So it's a partial derivative of loss with respect to the input, with respect to weight and biases. So what is this GT, by the way? So GT over here is nothing but sum of the square of the gradient. So basically GT represents sum of a square of the gradient up to timestamp t, till t, right? So till we are trying to find out the value. And epsilon is nothing but it's a constant, so a small value basically to avoid a division by 0. So if this is going to be 0, let's suppose for the first time, so if we have a 0 value, so in that case, we don't want divided by 0. So that's the reason. So people have introduced basically epsilon over here. So it's nothing but a small value small value to avoid division by 0. Yeah. So this is called as ADA grade, by the way. Now, so there is another optimizer which again scientists have introduced, and that is called as RMS prop. RMS prop. Yeah. So it's called as root mean squared propagation. So again, objective was same. New value is equals to old value minus some VT, right? So now here, if you are going to like find out the value of VT, right? So here the VT is nothing but here it is going to be eta divided by root of E of, I can say, G square at time t plus epsilon into GT. So this is going to be the value. So this is going to be the value of a VT. Now here, so we are able to find out a lot of new terms. So E of G of square T and GT. So this is the new value that we are able to find out. Now what is the value? What is the meaning of this E of G of square? So the value says that E of G of square at time T is equal to beta. So beta is basically a decay rate. For example, like a 0.9, 0.8, we can try to consider E of G of square at t minus 1 plus 1 minus beta, again decay rate, into GT square. So this is the value of this particular component, right? So this is called as RMS prop. Now moving ahead, so there is another activation function that you will be able to find out called as Adam optimizer, one of the best one that you all will be able to find out. So I think it's a fifth one. Yeah, it's a sixth one. So there is a optimizer called as Adam optimizer, one of the widely used optimizer, which is called as adaptive moment estimation. Adaptive moment estimation. Now, how does this looks like? So here again, theta philosophy is same. Old theta, old value is equal to, new value is equal to old value minus, and here they have introduced eta divided by root of V of t delta plus epsilon into M of t delta, right? So delta. Now, what is this VT and MT, which is the new term which has been introduced over here? So let's try to talk about that. So here your MT is nothing but beta 1, which is again like a decay, or we can say a momentum. So beta 1 M of t minus 1 plus 1 minus beta 1 G of t, and VT is basically beta 2 Vt minus 1 plus 1 minus beta 2 GT square. So this is the meaning of VT and like MT that you all will be able to find out. So what is the value of M hat T? Because we are using M hat T and VT over here. So M hat T is nothing but MT divided by minus, not plus. So 1 minus beta 1 T, and VT hat is nothing but VT divided by 1 minus beta 2 T. So MT and VT, where beta 1, if I'll talk about, so beta 1 is nothing but, let's suppose, a 0.9, which represents a momentum. Or what is this beta 2? So beta 2 is nothing but 0.999, which represents basically adaptive scaling. So this is one of the best optimizer, which is a combination of momentum and the RMS prop that we have discussed. So it's this Adam optimizer is adaptive momentum estimation, right? So it's a combination of basically a momentum optimizer that we have already discussed and a RMS prop. And again, most of the places you are going to use a Adam optimizer It's one of the lethal optimizer that you will be able to find out. So where it combines two things, momentum plus RMS prop capabilities. But at the end of the day, when someone is going to ask you that, try to explain me an optimizer. So if you have to explain the optimizer part to anyone, right, to anyone in this entire world, you will simply say that a kind of an equation, a kind of an algorithm, so which is helping me out to find out a new value of a trainable parameter, and eventually new value of trainable parameter. Why we are trying to find? So that we can decrease a loss. So optimizer is an algorithm which is helping me out in terms of decreasing a loss by finding a new value of a trainable parameter in a backward propagation. That's the whole idea. That's the whole meaning of a optimizer. And we are going to use an optimizer throughout our neural network, throughout our deep learning or computer vision or NLP or generative AI journey. So when we are going to write something, when we are going to write a code, obviously we will be talking about all of these things again and again and again. Almost every time we'll be talking about that when we'll write the code. So hope this idea is pretty much clear. No need to mug up anything. So we are going to use all of these things so many times during the entire lecture that you will be able to remember for the lifetime, right? Lifetime. As of now, try to understand the intention, that why we are going to use it, what we are going to use it. Then it will help you out to understand things in a much better way. With that, thank you so much everyone. Take care and see you again in my next lecture. Okay everyone, so welcome to the lecture, and in this lecture guys, I'm going to talk about autoencoder. So basically this autoencoder is one kind of a neural network that you all will be able to find out, and which has been used for a very specific purpose. Now I'll try to give you a layman example, by the way. So let's suppose you are an artist, right? You are an artist, or maybe you are not an artist, that's also fine. And you have seen maybe some person. Yeah, you have seen some person, maybe like today, tomorrow, or maybe like a month back, you have seen some of the person, or maybe you have seen some object, right? Maybe you have seen some animal, something like that. And if after a month, after a day, or maybe after a week, if I'm going to ask you to describe, right, to describe that object that you have seen, so you will try to recall, right? You will try to recall each and everything that you have seen. So what you will try to recall? You will try to recall all the major feature. So maybe you have seen the person. So you will try to talk about maybe eyes, that his or her eyes was this, her nose was this, like this, forehead was like this, hair was like this. So you will try to reconstruct the image of a person, right? You will try to reconstruct an image of the person once again, or maybe the object that you have seen, by remembering some of the important feature that you have observed, maybe unconsciously. But yeah, so just by recalling those unconscious mind, so you will try to talk about a major feature that your unconscious mind is able to remember, and then you will try to reconstruct that person or reconstruct that entire object in your mind, and then same thing you will try to describe to anyone, right? You will not be able to remember in-depth pixel to pixel detail about that object or person or that instance. And this is what we as a human being does. Now, to achieve the exact same goal, there is a neural network which has been designed, and that neural network is called as autoencoder. What it does? So it tries to learn how to reconstruct something by remembering maybe some of the feature, or maybe like a major feature. So this is what autoencoder does. So now let me share my screen, and let's start talking about a concept of autoencoder in little bit depth by taking some of the technical term. So here I'm going to talk about a autoencoder. Now, so when we talk about autoencoder, it's a combination of encoder neural network, a kind of or a special kind of a neural network which is been responsible for encoding, and then there is a neural network called as decoder. So autoencoder, whenever I'm going to talk about autoencoder, it's a combination of encoder plus decoder. Now you will ask me a question that what is this encoder then? What is this decoder then? Okay, let's try to understand. So here, what encoder will do? So here, what encoder will do? So encoder will try to take a input. So encoder will try to take what? It will try to take a input. This will be responsibility of encoder. I'll try to explain to you in a very short without taking like a lot of like a technical terms over here. Now, as an output, what this encoder will do? So let's suppose you are a person. You are, as of now, you are behaving as an encoder. You are a person basically, and you are behaving as an encoder. So you have observed something, you have seen something. Yeah, you have observed something and you have seen something. Now, whenever you are trying to observe, so your unconscious mind is going to observe some of the major feature. Maybe you are observing some of the scenic view. Maybe you are observing some person, some object, like anything. You will not be able to, like I said, you will not be able to remember a pixel perfect detail about anything as a human being, right? Your neural network has not been trained for that. And this is how the human being works. So as of now, you are behaving as an encoder. What you will do is you will try to remember only a major feature, maybe about the eyes, maybe about a nose, maybe about a hair color here, then color or something like that, right? You will try to remember all of these things. And then, so this is what encoder will do. So encoder will try to filter out. So what I'm trying to say, what I'm trying to make a point over here is that encoder is a neural network, a type of the neural network which will just try to filter out a important information, right? So as of now, you are behaving as an encoder, right? Now, so when I will try to ask you a question that, can you please explain me that event, or can you please try to explain me about that person that you have seen or object that you have seen? So now you will behave like a decoder, right? Now what you remember? So you remember just this important feature, right? Important feature, or maybe important points you remember about this particular event, or maybe person, or maybe object. So now you will behave like a decoder, and then you will try to reconstruct the entire event, or maybe a person, or maybe a place, right? So you will try to reconstruct. From where you will try to reconstruct? So whatever important feature that you have learned, so from that you will try to reconstruct. Let me draw the straight line, it will look more beautiful. Yeah, so you will try to reconstruct, and you are behaving like whom now? You are behaving like a decoder now. So now if I have to summarize, so what encoder is trying to do? Encoder is trying to extract the major feature. Yes, and what decoder is trying to do? So decoder is trying to take those major features, and then it is trying to reconstruct the same situation by using a major feature, not by using a whole data, because technically it's impossible to remember the whole data, right? Technically it's impossible to remember the whole data. Now, the important feature that I'm talking about over here, so in a technical term, right? In a technical term, it's basically called as a latent representation. Yes, it's called as basically what? It's called as latent representation. Means I'm not representing the whole data, but I'm trying to represent a partial amount of information, or just a major information, a major feature I'm trying to represent. So in a technical term, it's called as latent space, L-A-T-E-N-T, latent space, or a latent representation. So majority of time, whenever we are going to talk about an encoder decoder, you will be able to get this kind of a things. In a other word, you can say that this latent space or this latent representation is nothing but a summary of some event, a major feature of some event, which will be passed to my decoder, and which will help out my decoder to reconstruct any kind of a event at any point of a time. So hope this is making sense to all of us, right? Hope this is making sense to all of us. Now, so where we are going to use this autoencoder or this encoder decoder kind of architecture, where we are going to use it? So we are going to use this entire encoder decoder architecture in terms of a image compression. So where we have to reduce the size of the images, but we have to maintain the whole idea inside the images, means the nature of the images, so that anyone who is looking to the images, they will be able to understand that, okay, this is the representation of the image. This image is all about a human being or cat or dog or maybe a scenery, but compression, right? Compression means we are trying to hold just a major feature. So in case of image compression, you can try to use what? You can try to use an autoencoder, image compression. A denoising. So whenever you have a photo, maybe you have a old photos, right? Old photos, and there are like a lot of patches over there, right? Now, those patches are not representing the actual feature. Those are just a noise. So whenever you have to do a denoising of your image, in that case, you can try to use a denoise, not just about the image. Image is also a data, right? So whenever we have any kind of a data and we have to denoise the data, we have to like remove all kind of a outlier out of it, right? All kind of like exceptional things out of it. So maybe we can try to use a autoencoder. So usability wise, we can try to use it for image compression. Second is, so wherever we have to remove unwanted information, just we have to retain the important feature, because this is what encoder is doing. This is what is called as latent space or latent representation. So wherever you have to do a denoising, whenever you have to basically do a machine translation. So whenever you have to do a machine translation, means so one language to another language, maybe English to Spanish, English to French, whenever we are trying to like translate. For example, whenever we are trying to convert English to French, then what we are going to do? So we are going to basically encode English. English means we are trying to extract only a major feature from this English language. And then out of this major feature, we are going to decode into French. So by using those major feature, because everything you can't convert as it is. So by decoding it, so we'll be able to convert that into a different language, right? Different language. So again, inside a chatbot, I can try to use. So the fourth example I can try to give you is a chatbot, basically chatbot. So where it is going to understand your input, encoder, right? Encoder is going to understand your input. Now from your input, it will try to extract what? A major information, a major feature from your input. And then it will try to reconstruct something new, which is eventually the output. So which is called as decoder. So this is where again, autoencoder, you are going to use it. Now the another place where you can try to use encoder decoder architecture is called as video captioning, right? So where you have to generate a sentence, captioning means you are trying to like translate those videos into some of the sentences, some of the languages. So here it will try to take like a video frame one by one. It will try to understand the major feature, and then it will try to decode that as a sentence. So again, autoencoder. So autoencoder is a combination of encoder plus decoder, as I have mentioned over here, encoder plus decoder. Now what encoder does, encoder will always try to extract a major feature, which is called as latent representation. And then decoder from that feature, the important feature, it will try to reconstruct something, right? It will try to reconstruct something. And this entire architecture, this kind of a neural network architecture is called as encoder and decoder architecture, which I am going to explain you in a detail. So there are different kind of encoder decoder architecture you will be able to find out. So there is something called as VAE. So variational autoencoder. Variational auto encoder. The second kind of architecture, denoising, which has been used for denoising a data. Denoising auto encoder. The third one is sparse auto encoder. I'm going to give you an example. I'm going to give you even a practical example. So where we are going to build this entire auto. So there are other kind of autoencoder. I just mentioned 3 over here. So I'll be talking about all of these autoencoder concept inside that. So the example of the autoencoder, but the major part is to understand that what autoencoder does, what we are trying to build. So that when I'm going to give you a practical example, all of you will be able to understand it, and accordingly, you all will be able to build your own example. So in the next chapter, I will be giving you an example, guys, with respect to a autoencoder and its component, by the way. So with that, thank you so much, everyone. Hope all of you are able to understand. And with that, see you again in my next lecture. Welcome to lecture, everyone. Now, in this lecture, I'll be talking about a small but very, very effective project with all of you. So where I'm going to use a multiple technology, multiple stacks over here. So first of all, we are going to build a project called as customer churn analysis. And we are going to build a model, not a machine learning model, but we are going to build a neural network. We are going to build a deep learning model. So where this model is going to predict that whether customer is going to leave or customer is going to stay based on the record, based on the model that we have. And not just that, so we are going to even deploy this particular project. We are going to even Dockerize this particular project. We are going to build a project in such a way that our backend will be separate and our frontend will be separate. So backend, we are going to build it with the help of FastAPI, and frontend we are going to build with the help of Streamlit. So without any delay, so let me share my screen and let's try to open up a VS Code so that in a step-by-step manner, so we can try to build this entire project. So I believe my screen is visible to all of you, and let's get started. So first of all, I'm going to create a folder over here. So here I'm going to give a name as customer churn. Okay. Now, once this folder is done, so first of all, we are supposed to do what? So we are supposed to do a environment setup. Now, let me write it down in my Scribble ink that what we are going to do in a step-by-step manner. So whenever I'm talking about this particular project, so in a very first place, I'll try to write all the steps, plus I have already built a README file. So README file will be available inside a code base where I have already mentioned each and every step starting from building till productionization. So here, customer churn. Yeah. So for this, we are going to build the model. Now, step number one that we are supposed to do is create an environment. Environment creation. So let's try to do it. So let's try to create an environment in a very first place. So here, let me open up this one. So our folder is ready. Let's try to open up a terminal. And if I have to create a new environment, so I can try to do like a conda create -n. I can try to give an environment name. So customer_churn. And then I can try to give a Python is equals to 3.10, a safest version, by the way, and install everything. Yeah. So now this is going to create an environment for me called as customer churn in a couple of minutes, I would say. Okay. So this environment creation is done. I'm going to activate this particular environment, by the way. Yeah. So I'm going to activate this environment. So as you can see, my environment is been activated. Now, once I'm able to create this environment, I'll try to create a folder structure inside this particular project. So a very first folder which I would like to create over here is a data folder. So I have created a data folder over here. Then I'm going to create a folder called as API folder. Then I'm going to create a folder called as you can say model folder. And yeah, so model folder is there, data folder is there. And then I'm going to create a folder called as app folder. So these are the 4 folder I have to create, and I will be using all of this folder in a step-by-step manner as per the requirement. And above all, so I have to create a file called as requirement, requirements, requirements.txt. Yeah, requirement.txt. So where I'm going to keep all the things which is required for me to install in a particular environment. So I have to install a TensorFlow, Keras, FastAPI, UVCon to run that FastAPI, Streamlit, Pandas, and scikit-learn. So these are the installation which I'm looking for inside my environment. So what I will do, my environment is already activated. So I can just try to do a pip install. So pip install -r requirements.txt. And yeah, so one by one, it will end up doing all the installation inside a particular location, as you can see. So just wait for a couple of minutes and all my installation will be done. Okay, so it looks like all the installation is done inside a particular environment which I have created, which is a customer churn. Now close it and close this requirement.txt file. Okay, now, so let's talk about data. So I have a data available with me, and let me open up this data into some of the Excel sheet. So here inside my D drive, customer churn, inside my data folder. So I have this data, and let's try to open up this data into Excel sheet so that it will be visible clearly to all of us. Now inside this data, so I have basically a customer ID, I have a surname, I have a credit score, I have a geography, technically a country name. I have a gender over here, I have a age, I have a tenure, I have balance, I have a number of products which person has purchased, and has credit card. So 1010, 1 means yes and 0 means no. Is active member, again 1010. Estimated salary column we have, so this is the column, and then finally we have two classes. So one is a one class and one is a zero class. So one means exited, means churned, and zero means not churned, or you can say not exited. Now based on this we have to build a model basically. So we have to build a model in such a way that model should be able to predict if I'm going to pass all of these data, or maybe some of this data, depends how I'm going to build the model, which I'm going to show you very soon. So based on this, it should predict that, okay, so this customer is going to leave or this customer is not going to leave. So if this customer is going to leave, maybe I can try to bring some sort of a retention policy in between, right? So something like that I can try to do. So this is all about the data, guys, and this data set is already available over here. It's a small data, not a very big one, so it is not going to consume much of your space and memory, as well as it is not going to take much of your time in terms of training a model. Now, so we will try to build a model one by one, step by step. So first of all, what we can do, so we can try to create we have a model folder. So we can try to create train underscore artificial neural network .py file. And here, so we can try to keep all the required imports. So I'm just trying to import a pandas, numpy, scikit-learn, and then TensorFlow. And out of that, so I'm trying to import each and everything, which I'm going to use eventually during my entire process. So first of all, what we have to do, we have to load our data. Now, where is my data? So my data is available inside a data directory. So what I can do, I can try to call over here that pandas dot read CSV, as my data set is available into a CSV format. So read CSV. And here, so I can try to give a path that dot slash data, and inside this data folder, so I have bank underscore churn underscore data dot CSV. So dot CSV. So it will be able to technically read my data set. So whatever data which I am keeping over here, it will be able to read it out. And let's try to store it as a data frame. Now, once I will be able to read a data, so after reading a data, we have to decide that which column I'm supposed to use and which column I'm not supposed to use. So here, if I'll talk about this particular data, so obviously this customer ID is not going to contribute in terms of deciding that whether customer is going to leave or customer is not going to leave. Surname is not a factor which is going to give me any kind of a help in terms of customer is going to leave or in terms of customer is not going to leave. Yeah. So obviously customer ID and surname I should not consider, means I should drop these two columns out of the data set. Simple, right? I should drop these two columns out of the data set. And yeah, so we have a column called as exited. Now this exited column is going to behave as a Y column, means basically it's going to behave as a label of my data set 101010. Okay, fine. So I'm going to create my X and I'm going to create my Y. Now to create my X and to create my Y, so I'm going to drop a customer ID, surname, which is not required because it's not contributing, and exited I'm trying to drop because exited is technically a Y, right? It's basically a label for all of us across the axis 1. So fine, I'm going to create my X over here. I'm going to create my Y over here. So Y is nothing but my exited. So 010101. So 1 for like exited and 0 for not exited. Now, once I'm able to create my X and once I'm able to create my Y, again, go back to the data because data requires a little bit of processing over here. Now, if you will look into this geography column, and if you will look into this gender column, so geography column is available as a categorical data, right? And even a gender column is available as a categorical data. So maybe we have to give some sort of a label, 1 0 1 2 3 4 5 6 kind of a label. So maybe for a gender, for a male 1, female 0, something like that. And for a geography, so again we can try to find out a unique country which is available over here, and then we can try to give a certain label to this particular geography, so that I will be able to convert this data into a numerical equivalent data set. Now to do that, right? So to do that, for a geography data and for a gender data, right? So for a geography data and for a gender data, so we are trying to call a label encoder, so that it will be able to convert it into 0, 1, 2, 3 and so on. In this way, it will be able to convert it. Okay, that's cool. So we will be able to convert this data. Now, so this data set will be available in a complete, right? So this data set will be available in a complete numerical format. Now here, so maybe I can try to create one test.ipynb file for this particular project. And here, so maybe I can try to show you each and everything. So customer churn. So this was the environment. Now, so maybe one by one. So because some of you will be interested in terms of looking into the final result. So maybe I can try to show you that particular part. Let me install a Jupyter, which was not a part of my requirement.txt file. Okay, so here now I can try to show you my X data. So how my X data execute and execute. Yeah. So how my data set looks like. So here you must be able to see that I have converted my geography into a numerical equivalent. I have converted my gender even into a numerical equivalent. So all of my data set is available into a numerical format. But if we will try to check the scale of this data, so the scale of this data set is still very much scattered. So what we can do, we can try to call maybe a standard scaler on top of this data, so that I will be able to bring down this entire data into a standard scaling format, which is again like a something that we try to perform all the time. So if I'm going to show you this particular part, standard scaling part. So after scaling the data, if I'm going to show you my X scaled over here, so you must be able to find out that in between a certain range or in between a certain scale, all of this data is been represented. And this is what scaling does. I believe we all are aware about the standard scaling. Now, once we are able to do this, we can try to split our data into a train data and test data. So all this standard approach we are trying to follow, nothing much, right? Nothing much, because we have done these things hundreds of times. Now, once we are able to split the data, so we can try to build a model. Now, so here I'm going to build a simple artificial neural network. Now, if I'm going to show you model.summary, and we have discussed about even a summary a lot of times, right? Many times. So if we are going to talk about this particular summary, so we have a dense layer, then we have a dense one, we have a dense 2, and here, so you must be able to see that we have basically 16 neuron out there, we have a 8 neuron out there, and we have 1 neuron out there, and there are total 321 number of learning parameter, right? 321 number of learning parameter. So this is technically a small neural network that we are trying to create over here, which will be easy for us to train, right? And everywhere, so we are trying to give a ReLU function in between the hidden layers. And in an outer layer, as we have only 2 output, it's a binary classification, right? So basically we are looking for 0 or 1. And that is the reason. So we are taking only 1 neuron on an outer layer, and then we are trying to take the sigmoid function over here. Okay. Then we can try to call basically a model.compile. So where we are going to define what? So we are going to define the optimizer. So Adam optimizer we are going to use. Binary cross entropy we are trying to use because we have a 2 classes, 1 and 0, exited and non-exited, and then accuracy matrix is equals to accuracy we are going to choose. And then we are going to call a fit over here. And I believe we all are aware about all of these parameters. So X train, Y train, epoch is equal to 30. So 30 times we are going to pass the data. And we are going to do the weight update after 16 batches, batch size. So after 16 data, we are going to pass 16 like a set we are going to pass, then we are going to update the weight. And the validation is split wise. So 10% we are keeping for a validation, and then 90% we are keeping for the training purposes. Verbose is equals to 1, so that it will be able to show me the final output. Once it will be done, so we are going to save the model. So save the physical file of the model inside a model folder. So we have already created a model folder. So here we are going to save it as a .h5. We can try to save it even in other format. So pandas.pickle, and even into a pickle format, we are going to save the model. But which one? So we are going to save basically a scalar model. Yeah, because even at the time of testing of this model, so we need this one. So we need basically a standard scalar object. And this object, I am trying to save it as a physical file. These two things will be required. So whenever you are going to do some sort of a prediction. Yeah, whenever you are going to do some sort of a prediction. So, okay, that's cool. Let's save it. And let's try to run a training. So CLS, clear the screen. And after clearing the screen, so we can try to get into a model, and then here, so Python train nn.py, and if everything works well, so it will end up creating a model for me. Otherwise, so it is telling me that no such file or directory called as data bank churn data.csv. Okay, so data bank churn data.csv. Okay, so let me do cd dot dot. It is not able to find the file location, which it should be. So let me put one more dot over here. Control S. It is available here because it was working fine with respect to my Jupyter notebook. But yeah, so cd model and then Python train nn.py file. Okay, so now it is able to find out the file, and you must be able to see that it has created a directory called as model inside this model directory. So we have a bank churn h5, and we have basically scalar.pickle file. Yeah. So inside model, again, there is another directory which has been created. I can avoid that part if I'm going to remove this one. Yeah. If I'm going to remove this one, so it will end up creating not creating the new folder. So it will end up creating a file over here itself. But yeah, so we are able to create this h5 file, and we are able to create this scalar.pickle file. So this pickle file is for standard scalar, and this h5 is basically for my ANN model that I have created. Now, if I would like to see that how my model looks like, so I can try to check that out as well. So if you remember, I talked about an app called as Neutron app. So you can try to call a Neutron app, and then you can try to load your model, your h5 file over here, and it is going to show you the model that you have, or the model that you have ended up creating, each and everything. So we have an input layer, right? We have an input layer, and then we have a dense layer, which is nothing but a hidden layer. So inside a first hidden layer, so we have a 16 unit, then 8 unit, and then 1 unit, and then finally we are going to get the prediction, right? Finally, we are going to get the prediction. So this is basically a model that we have ended up creating. Now, once model creation is done for my artificial neural network as well as for my scalar, now what we can do? So now we are good to go ahead with the testing part, basically, right? We are good to go ahead with the testing part. So here we can try to close all of this folder. We can go to API folder, and then we can try to create main.py file. So let me come back in this place. So environment creation was done, right? Then the second step was, and everything is available even inside your readme file, readme.md file. So environment creation is done. Then data understanding. Then training, pipeline. Then the fourth part is API creation. So see guys, I have a model file available over here, right? I have a model file available over here. So I can try to test it in my local, in this particular environment. That's an easy part. But what I wanted to do is that I would like to expose this entire model as an API, so that anyone and everyone who is having an access of that URL, they will be able to test it. This is what I want, and that is something which I'm going to write down inside a main.py file. It's a very, very easy one. FastAPI provides you the entire framework by which you will be able to convert anything into an API, any function into an API in no time. Yeah. So here, the very first part you have to do is you have to create a FastAPI object. So this is the FastAPI object. This is the main entry point, and FastAPI, I believe we all are aware about it. Now, so we can try to load our model. So let's try to load our model. So our model is available inside a /model/model directory. So we are trying to load two models. One is a neural network based model and one is a scalar model we are trying to read, so that whenever I'm going to pass the data, so first of all, I'll try to standardize those data into a standard scalar format, and then we are going to do some sort of a prediction. Okay, that's cool. Now, so there is something called as pydantic data validation we are going to create. So we are trying to create our own class called as customer feature. We are trying to inherit basically a base model, and here, so we are trying to say that, okay, so credit score will be available into an integer format, geography will be available into a string format, gender will be available into a string format. So whenever user is going to pass an input, it will be available in this particular format. So this is just a pydantic for my data validation. Yeah, data validation. Okay. So whenever person is going to enter geography and gender, so we know that it will be available into a string format. Yeah, it is going to be available into a string format. And we have done basically a label encoding. Label encoding means 0, 1, 2. Yeah, so 0, 1, 2. So what we can do, so we can try to copy the same thing, that France, wherever you get France, label it as 0. Wherever you get Spain, label it as 1. Wherever you get Germany, label it as 2. Gender wise, so wherever you get female, label it as a 1, and wherever you get wherever you get female, label it as a 0, and wherever you get a male, label it as a 1. So geographical mapping and gender mapping. So wherever we will get this string, so we are going to convert it into an integer. But yeah, input wise, it is going to be string and a string. Simple, right? Simple. Okay, so we have basically a function called as predict churn. So it is going to take the features. So whatever feature that we are going to pass, it is going to basically take those feature, and type of those feature will be validated with this pydantic class that we have written. Yeah. So all this input should come in this particular format. Okay. And then whatever data that I will get, we are just trying to encode those data with the help of this one. So wherever for a map, geographical map, and for a gender, that's it, right? So for geography and for a gender, we are going to map it. Otherwise, it's completely fine. And then we are going to convert that into a data, like a data frame. And then we are trying to call a standard scalar, this particular model, right? A scalar model we are trying to call. And then finally, we are trying to call model.predict. Yeah. So this is the model that we have loaded, and we are just trying to call model.predict over here. And we are trying to pass the scaled data. Now it is going to give you a prediction, right? So it is going to give you a prediction. So here we have kept a threshold that, okay, so wherever we will be having more than like a 0.5, so it is supposed to be 1. And if we have otherwise, so it is going to be 0. Simple. So this is going to return me as a prediction value. Now, what we can do, so we have to expose this as an API. So how I will be able to expose? See, here I have created a FastAPI, right? I have just created a FastAPI, basically object. If I have to expose anything as an API with the help of FastAPI, nothing we have to do much. So we can directly call this decorator. So app dot and then post, and we can try to give an URL that, okay, so anyone is going to hit this particular URL, they will be able to pass the data, and they will be able to basically execute this particular method. So app.post and then predict. So in this way, whoever will be having an access of this URL at a local host, they will be able to call, execute this one. They will be able to pass a data. This is what it means. And in this way, I have just exposed this one with this API. This is how it is, right? This is how it is. So Control S, And now we can try to go and we can try to basically test this entire thing. So how I will be able to test this one? How I will be able to test this particular one? So let's try to understand this part. So first of all, this file is available, main.py is available inside my API. So cd dot dot, and I can try to get into basically cd API. And now what I have to do, so I have to basically call this one, uvicorn API main and then app. Yeah. So just try to call this particular file, and if I'm going to hit enter, and if everything is going to be fine, then it is going to execute it. Otherwise, it is not going to execute it. So no model name API. Okay, good. Let me fix this part. cd dot dot, and then now execute API main app. So it will try to first of all locate API folder. Inside that, it will try to locate a main folder, and then it is going to execute it. So yeah, it has executed. Now I can go ahead and I can try to test it. So file not found error, so unable to synchronize open file name. Okay, so it is telling me that it is not able to find out this particular file. So model. So it is able to execute it. That's cool, but it is not able to find out the file, by the way. So here model, let me remove one dot from here. Let me remove one dot from here, Control S, and then let me check. Yeah, so trying to execute once again. Okay, so now it is telling me that application is startup complete, and I can go and I can try to check. So I can try to check it at this particular location. So maybe I can try to hit this particular location on 8000 port. So basically it's a 127.0.0.1 8000. It's running over there. Detail not found. Detail not found. Okay. So let me check what is the issue. 404 not found. It is not able to reach out here. CLS. Uvicorn app reload. /docs docs. Okay, so just try to like go to this particular location, and there is a function called as predict predict, so which is available over here, but you will not be able to hit that one. You will be able to hit that with the help of post, which is nothing but a Postman or maybe some other application or maybe a web interface. You will be able to hit that. So here just try to like call a docs. So inside a docs, you will be able to find out this function. This is the predict function, right? And if you remember, so this is something that you have done. So basically you have exposed this function, so which is going to do a prediction at this URL, at the /predict URL. Okay, that's cool. So now if you are going to click over here, right? If you are going to click over here, so this is the schema, right? This is the schema. So credit score 0, geography, string, gender string, age, and all those things. This is something that you have done. Maybe you can try to call, try this out. And here, so if you are going to call execute, so it is going to give you some churn probability, and churned is equals to 1. This is something that it is trying to give it to you. With technically this data, which is not a correct data, I would say. So here we are trying to pass geography is equals to string, gender is equal to string, and all of these things are technically a 0. So maybe I can try to pass a proper data, but yeah, so even in this way, we are able to test it, right? So we are basically able to test it. So, and this is basically a schema that you all will be able to find out. This is basically a HTTP error validation. So for this schema that we have given, so you will be able to find out, which is not of our use, by the way. Now here, so I can try to change all of these values. So whatever value which I want, I can try to change it manually. So geography, maybe I can try to give France over here. Gender is equals to, let's suppose, a male over here. And then with this, I can try to execute it. Yeah, with this, I can try to execute it. And you will be able to see a churn probability. So technically we are able to do a small testing, right? Small testing with respect to a fast API. This is something that we have done, nothing much. And it's working. It's working simply means that our backend is working. Yeah, our backend is technically working. So if our backend is working, so maybe I can try to integrate this backend with my front end. And a very simple function, only one function we are trying to call, which is a predict function, right? Which is basically a predict function. So I'm able to test my backend. Now let's go ahead and let's try to create a front end for the same operation. Front end for the same operation. So here, let me close this API and all the other things. And here, so inside this app folder, so I'm going to create an app for a Streamlit. So new file Streamlit Streamlit underscore app.py file. So this is something which I'm going to create, and inside this I'm going to keep my entire front end. So where I'm going to take a input, I'm going to take an input field wise from a front end, and then I'm going to pass those data inside the API. The way I was trying to pass it inside a fast API in this way. So I'm going to pass the data, simple, and it should be able to do the prediction. So here, to create a Streamlit app, it's a very simple one. We are going to create a drop down, right? So credit score, geography, gender, age, tenure, balance, number of product, has credit card, is active member, and then estimated salary. So all of these things is going to give me a drop down or input field, by the way, right? So input field somewhere, selection box or a number input field, it is going to give it to me. I will be sending a data. Now, once I will be able to select a data, or once I will be able to send a data, then what we are going to do? So then we are going to pass those data inside my API. Yeah. So by calling this API, so I can try to pass my data. So here we are trying to say that Streamlit.button. So button name is going to be predict churn. And once you are going to click this one, it is going to collect all the data. So whatever data will be available in this variable inside this field, whatever data that you are going to select. So this data will come over here. And then here, so we are trying to call request.post, and we are trying to call this URL. Why we are calling this URL? Simple, right? So at this URL, I have this function, and this function is going to take all the data, right? All this data. So we are trying to call this particular URL, and we are trying to pass this data, the data that we are trying to prepare by taking a data from the input field. So we are going to pass this data, and we are trying to say that if response status code is 200, so just collect the response from the JSON and then try to show that particular response, whether it is going to be churned or it is not going to be churned. Else, just try to give me a prediction field. So we are trying to call just this particular URL. We are not loading any kind of a model. And yeah, one more thing. So keep your backend up and running. If your backend is not up and running, so you will not be able to test it. Now, if I have to test it, leave my backend as it is. Yeah, do not interrupt or do not do anything with respect to the backend. Just do one thing. So activate one new environment. So customer churn environment. So here, conda activate customer underscore churn. Yeah, CONDA. Conda activate customer churn, CLS, and then DIR. So yeah, all of these things are available over here. Now what we are going to do, so we are going to call Streamlit and then run. And I have this Streamlit app inside the app folder, right? So app folder, and then Streamlit, STREAMLIT underscore app.py file. So this is the file that we have to execute. Now this is going to give you this particular page, and here, so you can try to give all of your data. You can try to increase or decrease your age, your tenure, your balance, whatever you want. You can try to change it from here, and then you can try to call predict churn. And if everything is going to be correct, right? So basically we are trying to pass this data, and in a simple meaning, so this data set will come over here in these field. We are trying to extract a data from these fields because these fields are attached to the front end, right? UI. We are just trying to pass this data inside this particular API, and this API is going to give me the prediction the way it was giving me prediction before. right? The way it was giving me a prediction. So I just have to pass this particular data set and my work will be done. And yeah, so I'm able to do a prediction even with the help of this front end, right? Even with the help of this particular front end. So I believe this looks amazing. So we have a front end separate and we have a backend in a complete separate manner. We are able to test a backend, we are able to test a front end, and we are able to pass a data. Finally, we are able to see a result over here that no, with this data, you will not be able to churn it. We are able to build a artificial neural network model. So now API creation, and then fifth, fast API testing, UI with Streamlit, right? And then calling API with Streamlit. Simple, right? Simple. So calling API with Streamlit, and I will be able to get the final output. It's a very simple one, right? It's a very simple one. So now we are able to do all of this testing. And if we have to deploy this entire model on any cloud platform, for example, if we have to deploy this model on a Streamlit cloud itself, I don't need all of these files. So first of all, I don't need a data file. Yeah. Then obviously I don't need this model, this train in .py file. I just need these models, these two models. I just need this Streamlit. I just need this API main.py file, and I will be able to productionize it, right? I will be able to productionize it. And this is something which I'm going to show you in my upcoming lecture, that how I will be able to productionize it, how I will be able to make it global. But so far, I believe we all are able to understand. It's a very simple job that we have done. It's a very small project that we have done, but obviously an amazing one. Yeah, obviously an amazing one. So with that, thank you so much, everyone. Take care, and see you again in my next lecture. Okay, so welcome back to lecture once again, guys. Now, in my previous lecture, I was talking about a customer churn project, and we were able to do each and everything in my local system. Plus, we were able to test our front end as well as in like our backend in my local system. Now, in this particular lecture, so I'll be talking about how to convert any of your project as a Docker, so that you will be able to deploy as a Docker image, and it is going to be a platform independent, because Docker is nothing but a kind of a mini operating system in which you are going to bundle up your entire code and you will be able to productionize it on any platform. So that is something that we are going to see in this lecture. So we are going to convert our project as a Docker project, and then in my next lecture, so we will try to deploy it. So first of all, we'll try to deploy a backend, and then we are going to deploy a front end. So let me share my screen. So here, what we are going to do is that we are going to convert, first of all, our project as a Docker file or as a Docker image, you can say. And once we'll be able to convert our entire file as a Docker image or entire code base as a Docker image, then we can try to productionize it on any given platform that we want. So maybe a render, maybe a Streamlit. So for sure, I'm going to show you those deployments. But yeah. So here, first of all, we have two components. So we have a very first component called as backend, which will be having our model file, and we will be having a second component as a front end, right? Front end. So which will be having a Streamlit application, a front end application. So now what we are going to do, so we are going to convert this backend as a Docker, right? And then we are going to deploy this Docker image on a platform called as render. So which is going to give you a free access. So without even adding your card, you all will be able to deploy your application with the minimalistic configuration in a easiest possible way if your entire file is available as a Docker. So now let me open up a VS Code, and we are going to copy each and everything inside our new directory. So here, first of all, try to open up one folder. So I'm going to open up a new folder over here, and CUST/CHURN deploy final. Yeah. So this is the directory which I'm going to create. Now inside this directory, so we are going to create our backend and frontend folder. Same thing, right? So whatever model that we have built, so we are going to keep all of this model, all of this file inside this directory. So first is going to be backend, BACKEND, backend. And then a second folder which I am going to create is called as frontend. Fine. Now inside this backend directory, so we are going to keep our model. So this was my model that I have built. So let me keep a model over here, H5 file, and then we are going to keep our scalar file. So because this is also a model for converting our entire data set, input data set into a standard scalar format. Same thing, right? So these two models we have already saved in my previous lecture. So we are going to use the exact same thing. Then we are going to place a main.py file. So where we have basically this backend, and we are trying to expose that as a fast API. Same thing, right? So no changes at all in our code. Then we are going to copy basically a requirement.txt file, because this is something that system will try to deploy. So now let's try to reiterate all of these files once again. So these two, so pickle file, scalar.pickle file is required because whenever I'm going to input the data, so it should be able to convert our data set into a standard scalar format, because this is what we have done even at the time of training, right? And even at the time of testing. Now, second file, this is a model file. H5 file is basically a model file, which is going to predict a customer churn 1 or 0. And this is my code file, and this code file is exactly same as before. So I have just changed this model path and a scalar path because I'm trying to deploy something in a global environment. So it should be able to recognize these two files, and keeping that in mind. So these two things I have written in this particular manner. Rest of the things is completely fine. So we are trying to do a prediction on this particular URL, right? This particular URL is going to help me out in terms of doing a prediction. In my local system, so it was localhost and port number. Now in a global, so there will be a URL, a global URL I will be able to get. Rest is exactly same. There is no changes, means no changes at all. Okay, so here is a backend that we are able to keep. Now inside our front end, so we can try to keep basically our Streamlit app. And obviously we can try to keep over here a requirement.txt file. So now inside this requirement.txt file, I just need stremlit, Streamlit, and requests, request. So these are the only two installation which is required. Apart from that, there is no other installation which is required. And I'm going to deploy a front end and a backend separately, because this is how we work, or this is what we do even in a production grade environment. So my backend file and my frontend file is ready. Now, if you will look into my Streamlit app.py file, so as of now, there is a localhost/predict. I'm not going to use this localhost because once my app will be global, so this is not going to work, right? This is not going to work. Obviously, so we have to get a new URL. So when I'm going to deploy a backend, and I have to change this URL with the new URL after doing a deployment. Okay. Now, so moving along with this first line. So first of all, we have a backend code. Now I'll try to convert my backend code into a Docker file, and we are going to test it in a local, that whether this is working in my local or not. Once it is working in a local, then we can try to push it in a global environment, which is a render environment, or maybe in some other environment, we can try to push it. Simple. So first of all, we have a backend. How we can convert this backend file or this backend as a Docker. So here I'm going to create a new file, and I'm going to name it as a DOCKER and FILE. So D capital. So D capital, and you should not miss the file name. So it should be same as it is. Now inside this, we are going to keep a couple of lines, and these lines are going to help me out in terms of doing a deployment. Now, what is the meaning of these lines? Let's try to understand that particular part. So meaning of these lines are very simple. The very first line which I have written, so it is trying to say that, okay, so whenever you are trying to create a container, a kind of a box, you can say, right? As a beginner, you can say that this is a box that we are creating, in which we are going to install a Python 3.10 with a image which is a lightest possible image, and technically it is going to use a Debian based image, or you can say operating system in a layman way, right? Operating system in a layman way. So it is going to commence an operating system. Inside that, it is going to install a Python 3.10 for me. Now inside that, it is going to create a working directory called as app. And inside that, it is going to copy all the code that I'm trying to keep inside a backend directory. Simple, right? And then in that environment, it is going to install this requirement.txt. So whatever I have mentioned for this particular project, if your project is going to change, so obviously your requirement.txt component or content is going to change. So this is what I'm trying to say, that, okay, so try to upgrade it and then try to install it. And once it will be done, right? Once it will be done. So the way we are trying to make our app up and running in our local system. So wherever I'm trying to use it, do the same thing. So uecon main.app. So inside a main, we have an app, and then we have given this 0.0.0.0 universal port number. And here take this particular universal IP address, by the way, and take this 10,000 port number, and then try to make my app up and running. So only this much is required to convert my entire application as a Docker file. Okay, that's cool. Now, how we are going to test it? How we are going to test it in my local environment? Let's try to talk about that particular part as well. So if you have to test it in your local environment, so what you have to do, go to Google and then try to search for Docker download. Yeah, Docker download. And it is going to give you multiple links. Now try to go to one of the link, a very first one. And then from here, so you will be able to download a Docker desktop so that you will be able to test it. Doesn't matter which operating system you are trying to use. So for Mac, for Windows, as well as for a Linux, it's already available. So let's suppose I'm going ahead with the Windows system. Then I will try to click over here, and in some time, so it is going to download it. Click, and I will be able to do the installation. Yeah, I will be able to do the installation. And then if you are going to search a Docker, so if you are going to search a Docker, you will be able to see a Docker desktop, just the way I am able to see it. So installation is not at all tough, and this is the particular link that you have to go ahead with. Let me copy this link, and let me keep this link in some of the files. So maybe inside this main file, I'm going to keep this Docker link over here. Fine. So you can just go over there, try to download it, and then try to make it up and running. So here is my Docker. Here is my Docker desktop. So you have to do a sign up. So just try to go to like a sign up option, try to log in, and then try to do the sign up, and it will be done. Now, once this part is done, once your Docker is up and running, so there will be nothing inside your Docker, by the way. So you will be able to see a same kind of a screen the way I'm able to see it. There is nothing inside a Docker as of now. Now I have to test my application. So how I will be able to test my application? Let me show you that particular part. So we are currently into this particular directory. Yeah, we are currently into this particular directory. If I have to test my Docker, right? If I have to test my Docker, so what I have to do, first of all, I have to call a Docker build command. So this Docker build -t churn backend test. So you can try to give your like a container name over here, whatever container name that you want. But before that, so you have to get into a folder. So where you have a Docker file. So my Docker file is available inside a backend folder. Here is a Docker file, right? So here is a Docker file. So I'll first of all go inside the backend directory, wherever you have a Docker file, simple. And then try to build this Docker. Sorry, not this one. So let me copy and then Docker build. So just try to call this Docker build -t, and this name can be anything of your choice. You can try to give. So it will try to commence this entire Docker, means it will try to download the operating system. After downloading the operating system, so it is going to do all the installation, whatever I have mentioned inside my Docker file, and then we can try to run the Docker. As simple as that. So this is going to take not more than 60 to 90 seconds of time, depends upon your system and your internet speed, because it is trying to download the operating system, and then it is trying to build the entire Docker image for you. And once it will be able to build it, you will be able to see even over here, right? Even over here. So just wait for a couple of seconds, guys, and then once our Docker will be up and running, so we are going to test it. Okay, so looks like it is able to build each and everything. As you can see that it has installed a Linux version, one of the Linux version for me. And here is a location where I can go and I can try to check my Docker is up and running. And if you will closely look into all the commands, so it has executed all of these commands. It has installed a requirement.txt, everything, right? Everything. So Docker image is done. Now, if we will come over here and if you will try to check your image, so yes, there is a image which is available and with the same name, the name that I have given over here, right? Churn backend test, and it is available over here. And this is the size that it is going to occupy. So 3.26 GB is the size. Now, so once this is available, once this image is available, then we can try to run the container. So we are going to write a command called as, sorry, not this one. So docker run -p, and this is the port number, the port forwarding that we are trying to do, and then churn backend test. This was the image name, right? This was the image name for me. So hit enter, and very soon this entire things will be up and running and we will be able to test it. So UVCon run, and it looks like it is running at this particular location, and I can try to go inside the Docker and I will be able to see the exact same thing inside the container. So we had an image, yeah, and now I'm trying to execute that image, and this is running at this particular port number. So I can try to check this one. I can try to write /docs as a fast API, and here is a prediction that I will be able to get on /predict. So I can test it the way I have tested before. So try it out, and maybe I can try to send this dummy data. I can try to click on execute, and after execution, so yes, I'm able to see the churn is equal to 0. Whatever data which I have passed, which was a dummy data. So we are not supposed to pass a string or a string over here, or everywhere we are passing 0, 0, 0. But yeah, we are just trying to do a testing, and yes, testing is successful. And as of now, it's running on my Docker. Yeah, it's running basically on my Docker. So this is the place where it is up and running for me. Now, so once it is up and running for me, once this Docker file is up and running for me, so now we are good to go ahead with the deployment. And as you can see, 200, right? So 200 means it's a successful request and we are able to get some sort of a response. So everything is up and running in my local system as a Docker image. Now I'm going to use the exact same thing to deploy a backend. So in a very first place, I'm going to deploy a backend, right, on a render. Basically, I have already converted till this point, and then I'm going to deploy a front end in a step-by-step manner. So in my next lecture, we are going to deploy this Docker file. So with that, thank you so much, everyone. Take care and see you again in my next lecture. Okay, so in my previous lecture, I was able to convert my local setup in a Docker, and we were able to do it successfully. We were able to test it successfully. Now, in this particular lecture, we are going to talk about that how we can productionize this entire Docker things on a render platform. So render is a platform which is going to give you a free resources, and with the help of that, you will be able to deploy your Docker file or any other application. You all will be able to deploy with a ease without even adding your credit card. So let me share my screen, and step by step, let's talk about that one. So here, what I will do is that I'll go to Google and I'll try to search for render. Now, so once you are going to see this link, render.com, click over here. Now, after clicking over here, so it is going to ask for a sign in. So sign in step is very simple. You can try to do a sign in and then you can go into a dashboard. Now, once you will be inside a dashboard, right? Once you will be inside a dashboard, you can try to click on new. You can try to click on new. But before that, right? Before that, you have to push your entire project. You have to push your entire project, whether it's a front end or whether it's a back end, inside a GitHub repository. So first of all, let's try to see that how we can try to push this entire project inside a GitHub repository. The step is very simple again for a GitHub repository. So here I'll try to go to Git, and then I'll try to create a new repository. So new. And then I can try to give a repository name, customer customer _churn churn deploy. So this is the repository name which I'm going to give, and then I can try to click on create a repository. So once I'm going to do that, it is going to give me a couple of commands. I'm going to use this command, and then I will try to push this entire code which is available in my local system inside this GitHub repository. So first of all, git init, you have to initialize a git. So open up your terminal and maybe command prompt. I can try to close this one. So Control C, because as I don't need this one. Fine. And here, so CMD, now git init. So first of all, initialize, and then git add dot. So add each and everything. So whatever is available in my directory, just try to add each and everything. Now the next step is that git commit, and you can try to write any kind of a messages that you want. So this message you can try to change. So it's my customer churn Docker, anything, any kind of a messages which I want, I can try to write it down. So I'm just going to do the commit operation over here. Now all of these files are committed, by the way. Now, so once commit is done, the next step is, okay, let me close this part. So once this part is done, so next step is, so git branch hyphen main for the very first time, not for the second time, but yeah, for the very first time you have to do this one. So git branch main. So fine. And then you have to add this branch because system is going to push all the code inside this particular branch. So just try to do this one and hit enter. So once we are going to hit enter, so it is going to add this particular URL. So where I'm going to push my entire code. And then the next step is git push origin main. So just try to push this entire code, and in some time, so I will end up pushing the entire code, as you can see. And now if I will come over here, so I will be able to see my code. So I have a backend code and I have a front-end code. Yeah. So first of all, I'll try to deploy a backend, and then I will try to deploy a front end. So only backend first, right? Only backend first. And then obviously I have to make some sort of a changes in a front end in terms of a URL, because even now, if you will go and check, so URL wise, we have a local host URL, which is not going to work. So obviously I'm going to update this particular file. I'm going to push it once again, and then I'm going to deploy this one. So first of all, I have to deploy basically a backend. So now go to a render dashboard, step number 1, click on new, just follow along with my mouse. Yeah. So click on new and click on web service. Yeah. Web service. Now, once you are going to click on web service, so for the very first time, it is going to ask you to connect with the GitHub. So just try to log in with the GitHub, connect your render with the GitHub. Once you are able to do it, it is going to show you all the repository. So this is the repository in which I have pushed my code just 1 minute back. So customer churn deploy. Now click over here. Okay. And a very less configuration you have to do with the Docker. So here name customer churn deploy. That's completely fine. I'm not going to change this name. Language, leave it as it is, Docker, because we are trying to deploy a Docker, not a Python file directly over here. Branch is main. And a root directory. So here inside my main branch, customer churn deploy. So I have basically a backend as well as I have a front end. Currently I have to deploy only a backend. I don't want to deploy my front end. Front end I'll deploy separately, and backend I'm going to deploy separately. So here I can try to write that, okay, so just try to basically use a backend as a root directory. So this is important. You have to mention that, and then click free, because I'm not supposed to, like, I'm not going to pay for it basically. And then you don't have to do anything. Anything means literally you don't have to do anything. Just click on deploy a web service, and it is going to take some time. Some time means it is going to take maybe a 4 to 5 minute of time for you to build the entire Docker images. And finally, you will be able to see this particular link, and we are going to even test this particular link in our system. Yeah. So just wait for 4 to 5 minutes of time, guys. And then once it will be deployed, we are going to test the link. Okay, so now we are able to see that our service is live, and yeah, so this is live at this particular URL. Just follow along with my mouse cursor, and the service is live at this particular location. So just click over here, and here, so just try to say DOCS so that you will be able to access the FastAPI. And I'm able to see this entire URL, and at this URL I'm able to see a FastAPI. So I can try to click on try this out, execute, and yeah, so it is going to execute, and it is going to give me some of the response. Now this is my global URL, right? This is my global URL, and at this URL I will be able to do a prediction basically. So this is the URL which I have to update in my front end, so that system will be able to hit this particular URL, and successfully we are able to deploy our backend services, right? Successfully we are able to deploy our backend services. This is just a backend, not a front end. So I'm trying to show you a standard approach. So where we try to deploy a backend separately and a front end separately. That's a standard approach we always try to follow across all the organizations, so that we will be able to control a backend separately, and we will be able to control a front end separately. So with that, thank you so much everyone. Take care. And in my next lecture, I'm going to show you a front end deployment. Okay, everyone. So now we were able to deploy a backend and we have a URL for a backend. So what you have to do, so you have to do a small thing over here. So just go to your Streamlit app.py file and try to update your URL, a same backend URL / predict, because predict is a route at which we have a predict function so that it will be able to call it. And our backend is already up and running on a render.com. We are going to deploy this front end on a Streamlit cloud. So two separate cloud, one cloud for a front end and one cloud for a backend. So as per my diagram, so we were able to deploy each and everything on for a backend. We have converted into a Docker file and then we have deployed that on a render.com. Now for our front end, so I'm going to use a Streamlit cloud. Now, so what you have to do is that go to Google once again and try to search for a Streamlit. Now, once you are going to search for the Streamlit, you will be able to get a very first link. It's a free one. You don't have to do anything. You don't have to add any kind of a card payment over here. So just click and then try to click on free. And once you are going to click on free, so it is going to ask you for a sign up. I have already done the sign up because I keep on deploying a lot of application on a Streamlit. Once you are going to do a sign up, it will ask you to connect your GitHub repository. So you have to connect your same GitHub repository in which you are going to keep a code, just like a render.com. Yeah. And once you are able to do that, just click on create an app. So deploy a public app from a GitHub. So this is the very first option for me. And then here I can try to select my GitHub repository. So my GitHub repository was customer churn deploy. Yeah. So this was my repository, customer churn deploy. So I have selected that repository. Branch is going to be main, and where is my Streamlit app.py file? So basically that is available inside frontend / Streamlit app.py file. So I'm going to select this one and then I can try to click on deploy. Advanced setting wise, so you can try to select a Python version. So let's suppose if you have built your entire app in Python 3.10, so you can try to select Python 3.10. Otherwise, you can try to leave it. If you have to give some sort of a secret, you can try to keep your secret over here. But as of now, I'm not trying to use any kind of a secret. So that's again completely fine for me. So click on save and then click on deploy. It is going to take a couple of minutes of time and then your app, which is technically your front end, will be up and running. So this is how easy it is, guys, in terms of doing a deployment. So whether it's a backend, whether it's a front end, in no time, right? In a no time, I will be able to deploy it. And technically I have used a two separate platform. I could have used just a render. I could have even Dockerized my front end and deploy on a render. That's completely fine. Vice versa, I could have deployed even my backend by finding out some sort of a workaround even on a Streamlit, but I'm not doing that. Yeah, I'm not doing that. So here, bank churn prediction. As you can see, my app is live. My backend is live over here, and even my Streamlit app is live. Now, just try to click on predict churn with the default value, whatever default value that we have. So let's try to click on predict churn. And prediction API failed. Just please check the API. And if I'm going to come over here, so it is working, by the way. DOCS. Okay, so it may take some time to give me a response. Okay, so application shutdown complete. So finishing a server process. Okay, fine. So basically, I have to click on restart the service because it's a free platform. So if it is a free platform, so they are going to shut down your services because obviously you are going to take their resources. So for some time, so you just have to restart the service. So I have just restarted the service and then I'm going to test it. And that was the only reason why it was failing. Yeah. So let's restart the service because application shutdown complete. It has shut down my application, by the way. So just wait for some time, guys. So still it is trying to spin my server, my backend server basically. And if I'm going ahead with a paid one, then in that case, it's just up to me. They are not going to shut down the system. So whether it's a front end, whether it's a backend or any other deployment which I have done, so obviously they will not try to shut it down. So just wait for some time, guys. Just wait. Okay, so successfully I'm able to restart my server. And now let's try to see so whether I'm able to see something on our docs or not. Still it's taking time for me. My backend is not up and running as of now. Now available at your primary URL. It is telling me that yeah, it's available. And when I'm trying to hit this URL, so it is trying to tell me that this service is currently unavailable. Please try again in few minutes. So maybe it will take some time. It will take some time to like keep it up and running. Although it is showing me a message that available at your primary like URL, your service is live. Application startup complete. So I can see a very clear message over here. But still I have to wait, I believe, for a couple of minutes at least. This is like a very much normal because we are using a free server, and with respect to our free shared instances, obviously this is going to be the issue. It's not a dedicated one for me. Okay, so my backend is up and running. Now I can try to refresh and then I can try to test it. So my backend seems to be up and running, and now I can come to my Streamlit app and then try to click on predict churn. If my backend is up and running, and yeah, so if it is up and running, I will be able to get some sort of a output, which I'm able to see, which I'm able to get. And here, so yes, there is 200, right? So 200 simply means that the request was successful for me for this particular app. So finally, guys, we are able to deploy this entire app front-end on a Streamlit cloud and backend on a render cloud platform. And we are able to communicate on this two separate platform with the help of an API that we have created with the help of FastAPI framework. So hope all of you have liked it. All of you have enjoyed it, and please try to implement it. If you're going to face any kind of a issue, please try to ping me in a group or maybe inside a chat box. Obviously, I'm going to respond back and I'm going to help you out with this one. So with that, thank you so much, everyone. Take care and see you again in my upcoming lecture. Okay, so fine, everyone. So we were able to create an API. Now I'm going to talk about how we can test an API with a Postman. So we all know that we have already created an API for a backend with the help of FastAPI, and it's up and running, right? It's up and running. And how I will be able to test it with the help of Postman. So those who are not aware about Postman, so Postman is a tool which is going to help you out in terms of testing your API, any kind of a API that you are going to create, and many more things it does. But yeah, the primary objective of the Postman tool is API testing. And across our industry, we all are using it. So first of all, what you have to do is that you can try to go to Google and try to search for a Postman, basically. So Postman, Postman, and then you can try to search for Postman download. You can try to download a Postman, or maybe in a BIV version itself, you can try to log in and you can try to test it. But yeah, I'll recommend you to download it. It's available for all the operating system that you can that you are going to use it. So once you are going to download it, just try to do a login. You don't have to do any kind of a payment if you are not going to use it inside your company or maybe for a team, right? And again, the paid feature. So Postman, just try to download it, and I have just downloaded a Postman. Now here you will be able to see a plus link. So just try to click on this plus. And now I'm going to do a API testing. So first of all, to do an API testing, so you have to understand that what kind of a request you are trying to send. So I'm trying to send basically a post kind of a request. So inside a body, I'm going to send the data. So I'm going to select a post over here, enter the URL. So which URL I'm supposed to enter? The URL which is live. So this is the URL which is live. So I'm going to paste this one /predict, PREDICT, because as per my code, so at predict, my prediction function is available, right? My prediction function is technically available. And then come to a header. Now inside a header, so it is going to ask for the key and a value. So as a key, you can try to mention a content type, and as a value, so you can try to mention that, okay, so it's basically a application, JSON application. And then you have to pass a data, right? You have to pass basically a data the way you are trying to pass a data over here. So in the similar manner, you have to pass a data. So to pass a data inside this one, so you have to come to a raw, and then from here select a JSON, because you are going to pass basically a JSON data. So what kind of a data? There is a data I have prepared. So where credit score, geography, gender, age, all of these things I have mentioned. So once you are going to do this, once you are going to fill the data, so just make sure, right? So this URL at which your app is live, you can try to paste even a local URL. That's completely fine. /predict. Method should be post because this is how I have created the API. Then there is a body raw and then JSON, and before that header. So step by step, just try to follow, nothing much, right? And then try to click on send. So once you are going to click on send, so it is going to send this entire body, and it is going to send basically at this particular URL, at this particular location. And now if everything is going to work fine for me, so whatever output the system is giving you, whatever output your API is giving you, you will be able to see that output over here. Simple, right? You will be able to see that particular output over here. And yeah, so this is a request successful message, and code is 200. So request successful message, I am able to get it. So with the help of this, you will be able to test your API. Not just this API, you will be able to test any kind of a API that you want. But yeah, so nature of the API, or which method it is trying to use, and what kind of a data we are trying to pass, all of these things you must be aware about. Then only you will be able to test it. So hope all of you are able to understand that how we can try to test an API with the help of Postman. So keep on doing it, try it, and then let me know if you're having any kind of a confusion, concern, or any kind of a doubt. I'll try to resolve your doubt for sure. So with that, thank you so much everyone. Take care, and see you again in my upcoming lectures. Okay everyone, so welcome to lecture, and in this lecture guys, I'm going to talk about evaluation matrices, a very first matrix for a classification problem. So as we all know, and we have seen a classification problem. So for a classification problem, very first matrix that we try to consider for an evaluation is a confusion matrices, and we have named it as a confusion matrix, but it's not that confusing. So I'm going to clarify that part in this particular lecture itself. So let's talk about a confusion matrix in a very first place, that how confusion matrix works and what confusion matrix actually looks like. So here, let's suppose if I'm going to draw a table. Okay, so here let's suppose if I'm going to draw a table, and here, so we have basically these rows, and let's suppose over here I'm going to write actually positive, yeah. So let's suppose I'm labeling it as a 1. I'm talking about a binary class classification. And actually negative, I'm labeling it as a 0. So obviously in a binary class classification, so there will be two classes. I'm considering that two class as 1 and 0. So 1 will be a positive class, I'm labeling it as a 1, and negative class I'm labeling it as a 0. And then you will be able to get a prediction, right? So prediction, predicted positive 1, predicted negative 0, yeah. So this is the matrix, and this matrix is technically called as confusion matrices. It's not that confusing, by the way, and all the other parameter for an evaluation we try to calculate based on this matrices itself. So here, let's suppose I'm expecting a actual positive, and if I have received even as a prediction as a positive, I'm expecting what? I'm expecting basically a positive, and I have received a positive outcome from a model. So model has even done a prediction as a positive. So in that situation, it's called as true positive, and we label that as a TP, true positive. Let's suppose I'm expecting a negative value, right? The actual value was a negative value, and prediction was basically a positive. So this is basically a wrong prediction we are talking about, right? So I was expecting a negative, and system has done a prediction about the positive one. So this is called as false positive, yeah. So we try to label that as a FP. Now, so let's suppose I'm expecting a positive, right? And model has given me a negative. So here, falsely, model has given me a negative value. So we try to label that as a false negative. So false negative. Now let's suppose I'm expecting a negative, and even system has predicted as a negative. So here I can label that as a true true, negative. So TN. Now, these are the parameter which we are going to use, a true positive, false negative, and true negative, to evaluate a model. With the help of this confusion matrices, we will get to know that how my prediction is, or how accurate my prediction is at the end of the day. So here, just to do a calculation, so what I'm going to do, I'm going to take one kind of a data over here. So let me take a data set in this particular place. And inside this particular data set, let's suppose I have actual value, and I have a predicted value. So the actual value was 1 and prediction was 1. Let's suppose actual value was 0, prediction was 0. Actual value was 1, prediction was 0. Actual value was 0, prediction is also 0. Actual value is 1, prediction is 1. Actual value is 1, again prediction is 1. Actual value is 0, prediction is 1. Actual value is 1 and prediction is basically 0. Actual value is 0 and prediction is 0. And actual value is 1 and prediction is also 1. So now this is the reading that I'm able to get. Now, based on this, I have to do a calculation that how accurate my model is. So I have an actual value which is given to me. You can say that as a y, and prediction value, maybe I can try to label that as a y hat. That okay, fine, system has given me a prediction of this one, and I was expecting basically these values, right? These values. Now, if we have to fill up these values based on the a data that we are able to read out inside this confusion matrices, how we are going to fill up these values, how we will be able to find out that yes, how many values are true positive, how many values are false positive, how many values are true negative, how many values are basically false negative. And then only I will be able to identify that how accurate my model is. And I can say that okay, fine, this is the confusion matrices that I'm able to draw based on the data, based on the reading which I'm able to get from the model. So here, if I'll talk about basically a very first one, which is a true positive one, what true positive says that the data was actually positive and even I have received a positive. So I was expecting a positive and I have basically received a positive value. So here I was expecting a positive, I have received a positive value. Then here I have like a actual value was positive and I have received a positive value. Again here, so I had a positive value, I have received a positive value. And then over here, so I had a positive value and I have received basically a positive value. So as per this one, we have 4 total true positive reading. Now, if I'll have to talk about a true negative means what? So true negative simply means that the actually it was negative and even I have received a prediction as a negative. So here I had, let me change my pen color. So I had basically a negative value, which is 0. And yes, I have received a negative value. Then again, I had a negative value. I have received a negative value. And here, so I had a negative value and then I have received a negative value. So true negative reading is equals to 3, right? True negative value is equals to 3. Now we can try to find out a false negative. What is the meaning of false negative? So actually I was expecting 1 and I have received basically 0. That is basically a false negative. So how many false negative that I had? So I was expecting basically 1 and I have received 0. So I was expecting 1 and received 0. I was expecting 1 and received basically a 0. So total false negative that we have is equals to 2. And then we have a false positive, means I was expecting 0 and I have received 1. This kind of a situation. So false positive. So how many false positive do we have? So false positive means I was expecting basically negative, means I was expecting basically 0 and I have received basically 1. So in total, I have 1 value from this particular table. Now these are the total number of values. Now if I'm going to fill up, these values inside this particular table, I will be able to get my confusion matrices. So true positive, I can fill up as a 4 over here as per this particular data. And true negative, I can try to fill up as a 3 over here. False negative, I can try to fill up as 2 over here. And false positive, I can try to fill up 1 over here. Now, this is going to create a confusion matrix. confusion matrix for me. So this is the confusion matrix for this particular data. So now whenever we are going to solve a classification problem, so this is the very first matrix that we try to draw, and based on this particular matrix we try to estimate that how my model outcome looks like. Basically this is something called as confusion matrices, and everywhere in case of a classification problem, so whether it's a binary class classification, whether it's a multi-class classification, you will end up using this kind of a confusion matrices all the time. So if model is 100% accurate, then you won't be having any false negative value, or you won't be having any kind of a false positive value. So this false element will be 0 and 0, false positive and false negative both will be 0 if model is 100% accurate. If model is not 100% accurate, if model is not performing well on each kind of a data set that you are going to pass, in that case you will end up getting some sort of a false negative or maybe some sort of a false positive values over here. As simple as that. So with that, thank you so much everyone, take care, and in the next section, so I'm going to talk about more evaluation parameter. So as I was talking about a confusion matrices, the next one which comes into a picture is called as accuracy. So how we are going to calculate an accuracy, that what is the percentage that my model is accurate, or what is a percentage that model is not accurate. Now, so formula for accuracy. Formula for accuracy is basically true positive plus, true negative divided by true positive plus true negative plus false positive plus false negative. Yeah. So this is basically going to give you a accuracy of a model. Now, with respect to the previous example, which I have already shown it to you. So here we have a true positive is equal to 4. True negative is equals to 3. So 4 plus 3 divided by the total number of the data. So you can say true positive plus true negative plus false positive plus a false negative. So here, if I'm going to put up the value, so I can try to say that 4 plus 3 divided by 4 plus 3 plus false positive we have, right? So false positive value is basically 1 plus 2. So false positive is 1 and false negative is basically 2. So eventually it is going to give me 0.70. So if I'm trying to use a model, and if this is the prediction my model is going to give, so in that situation we can say that my model is 70% accurate at a time. So whenever I'm going to use a model on a particular data set which model has not seen, so in that situation my model is 70% accurate. 70% I can say like correct. So 70% of the time my model is going to give me a correct prediction, and 30% of the time my model is going to fail. Now there is a space of an improvement for my model basically, right? So my model can try to improvise itself, and based on that maybe we can try to make a better and better model. But yeah, this is something called as accuracy, and every time you are going to use this particular parameter. As simple as that. And again, it's getting derived from your confusion matrices itself. Confusion matrix is basically a base for all of these things. So with that, thank you so much everyone, take care, and see you again in my next chapter. So in this model evaluation parameter for a classification, so all of these things I'm trying to discuss with respect to the classification problem statement. So we all know that what is the meaning of the classification. Now there is a parameter which all of you will be able to find out, and that parameter is called as precision. Precision. Again, so this is a evaluation parameter for a particular model. So what is the formula for a precision? So precision formula says that it is basically a true positive divided by a true positive plus a false positive. So here, if you will look into the confusion matrices, so true positive divided by true positive plus a false positive. Now what it says, right? So whenever we are trying to use this precision, whenever we are going to evaluate a model, so what it is going to measure? So technically it measures so how many of the predicted positive values are actually positive. So this is what precision is going to talk about, that whatever positive value that we are predicting, so whether it's a true positive, whether it's a wrong, which is a false positive value, out of that, what is a percentage that my model is trying to predict as a positive, which is actually positive, right? This is what this precision says. Now, so if I have to do a math with respect to this particular data set which is given to me, so here my true positive value is 4 and my false positive value is equals to 1. So here I can say that if someone is going to ask me that what is the precision of my model, so true positive is 4, so actual positive divided by actual positive plus falsely, right? So I was expecting basically a negative, but model has done a prediction as a positive. So precision of my model is basically 0.80, or you can say 80% of the time, or my model precision is basically 80%. So 80% of the time, my model is able to do a prediction for a positive when it is actually positive. And 20% of the time, my model is not able to do a positive value, or my model is not able to predict a positive value when it is actually positive. So this is what precision says all the time. So again, this is one of the evaluation parameter for a classification algorithm that you all will be able to find out. So hope this works for all of us, and we all are able to understand that how do we calculate a precision at the end of the day. So with that, thank you so much everyone. Take care and see you again in my next immediate lecture. Now there is another parameter, guys, so which is basically called as a recall. So let's try to understand what is the recall again with respect to my previous example. So I'm going to talk about a recall. So let's see. So how we can try to do a calculation, how we can try to do a math for a recall. So RECALL, a recall. Now in other word, it's also called as sensitivity. Sensitivity, or it's also called as true positive rate. Now, what is this like a recall all about is? Let's try to understand. So recall is equals to true positive divided by true positive plus false negative. So this is what a formula for a recall is. So true positive, as we can see, and divided by true positive plus false negative. And it's also called as, like I said, a sensitivity. So it is going to measure that how many of the actual positive, right? How many of the actual positive was correctly identified as a positive, because some of these value it is going to identify even as a negative, right? So it was actually a positive one, but system has done a prediction as a negative one. So it's basically talk about a sensitivity towards a positive value at the end of the day, and technically it's called as a recall. So let me write down my statement over here so that you all will be able to remember for a very long time. So basically it is going to measure that how many times actual positive were correctly identified. Now, with respect to my example, so if I'm going to do a math, so my true positive value was 4, right? So 4 times my value was positive, and yes, I was able to identify as a positive, but 2 times my value was not my value was actually positive, but I was not able to recognize that as a positive as per this particular confusion matrices. So here, if I have to do a math, so I can simply write down that 4 divided by 4 plus 2 is approximately, I can say, 0.6667. So this is the percentage. So recall or sensitivity of my model is basically a 66.67%. This is what I can try to say, that 66.67% my model was actually able to identify a positive value as a positive value. So this is all about a recall, guys. Hope all of us are able to understand that what is the meaning of a recall and how we can try to do a math, how we can try to do a calculation with respect to a recall. Okay. So there is another matrix, guys, that you all will be able to find out with respect to a classification algorithm, and that is something called as F1 score. F1 score. Now, whenever inside my data set, my classes are imbalanced, means one class is available in a majority and other classes are available in a minority. So at that point of a time, we are going to use basically a F1 score. So what F1 score says? What F1 score says? So it says that 2 into basically precision that we have already calculated, precision into recall divided by precision plus recall. See guys, so whenever your classes are balanced, so at that point of a time, the best parameter or best matrices is going to be the accuracy, right? So when classes are balanced means it's available in a almost same amount, right? 50-50 ratio or maybe 49-51 kind of a ratio. So when class are balanced, in that case, just try to go ahead with the accuracy matrices. So we have already talked about the accuracy matrices in my previous lecture, right? So just go ahead with the accuracy matrices. But when your classes are imbalanced, one classes are available in a majority and another classes are available in a minority, at that point of a time, always try to go ahead with the F1 score. Now, so if I'll talk about my current example, so here we have 1, 2, 3, 4, 5, 6. So 6 class positive, 1, 2, 3, 4. So 4 class negative. So almost my classes is available in a 60-40 ratio, which is like with respect to this small data, it's kind of a balanced one, but still we can try to calculate a F1 score, although accuracy is going to be the best parameter for me, but still I can try to go ahead with this one. So here what I can do, if someone is going to ask me that what is the accuracy of your model, so I can try to use a F1 score over here if classes are imbalanced, only in that situation, right? So if classes are imbalanced, in that case I can try to go ahead with the F1 score. So here my precision was, I believe, 0.80. So 0.80 plus my recall was basically 0. Sorry, it should not be plus, it should be multiplication. So my recall was basically 0.6667, I believe, and then divided by, right? So divided by precision plus recall, so 0.80 plus 0.667, and eventually it is going to give me 0.727. So basically my accuracy of the model is 72%, I can say, if my classes are imbalanced. Only in that situation you should use a F1 score. Otherwise, you are good to go with respect to an accuracy matrices. So true positive, true negative divided by all the data set, right? Total number of the data set, or true positive, true negative, false positive, false negative. As simple as that. But yeah, so you are supposed to use a F1 score when classes are imbalanced. And many people are going to ask you a question in an interview that when you are supposed to use a F1 score, when you are supposed to use a accuracy matrices, when you are supposed to use a precision. So you are supposed to talk about a precision as a accuracy matrices. So when your false positive values are costly, so when you can't afford a false positive values, maybe in terms of a healthcare test, right? And you are supposed to use a recall. So when false negatives are costly, so maybe in a judiciary, so when you are trying to like give some sort of a verdict, so over there you can't allow a false negative value. So in that particular place you are supposed to use a recall. So let me write it down over here as a summary. So false positive, so whenever your false positive are costly, so in that case your accuracy parameter is going to be precision, and this is something that you have to decide. And when your false negative are costly, so in that case you are supposed to go ahead with the recall. As simple as that. So this is the summary of the entire evaluation of the matrices that we have discussed so far, so forth. So we have already talked about a confusion matrices, and from a confusion matrices, this everything is getting derived, right? Everything is getting derived. So whether it's an accuracy that we are talking about, whether it's a precision that we are talking about, whether it's a recall that we are talking about, whether it's a F1 that we are talking about. And now we even know that which one I'm supposed to use when. So F1 is score when classes are imbalanced, when classes are balanced. So in that case, go ahead with the accuracy calculation. When you can't afford a false positive value, so for example, a healthcare checkup. So in that case, go ahead with the precision. When you can't afford a false negative, for example, a judiciary. So in that case, just try to go ahead with the recall. As simple as that. And confusion matrices are not very much confusing, by the way. So hope all of us are able to understand that how we can try to do a calculation or how we will be able to find out the accuracy of each and every model. So with that, thank you so much, everyone. Take care and see you again in my upcoming lectures. Okay, so welcome back to lecture once again, guys. Now in this lecture, we'll be talking about what is the accuracy matrices for a regression problem. So there is something called as mean absolute error. There is something called as mean squared error, and there is something called as root mean squared error. And with the help of that, so we will be able to calculate what is the accuracy of a regression model. So let's try to understand with respect to a calculation with respect to the example. So here, I'm going to write down a regression matrix. Yeah. So now the very first matrices which I will be talking about is basically a mean absolute error. So here I'm going to take some of the data. So for example, I was having a actual data. So technically it's a Y, and then let's suppose we have a predicted. So technically I can try to label that as a Y hat. So this is the data set. Let's suppose I'm going to take. So actually I was expecting 100. Now model has given me 90. Actually I was expecting 150. Model has given me 160. Actually I was having 200 and model has given me 210. Actually I was having a 250 and model has given me 240. Actually I was having, let's suppose, a 300 and model has given me basically 310. So now this is the data set which has been given to me. So where I have a actual value and the predicted value from a model. So we have a Y value and we have a Y hat value over here. Now the very first matrix in general we try to talk about is called as MAE. So MAE, and full form of this one is basically called as mean absolute error. Yeah. So how we can try to calculate a mean absolute error? So it's nothing but 1 by total number of the data that we have, a summation of Y minus, I can say, Y hat. Yeah, summation of modulo of Y minus Y hat. So basically it is going to give you an average of absolute difference. So this is going to calculate the absolute. That's the reason so I have used a pipe over here. So absolute difference between the actual and the predicted value. This is what it is going to do. This is what it is going to perform. Now, with respect to this particular data, if someone is going to ask me a question that what is going to be a mean absolute error, I can simply say that mean absolute error is nothing but 100 minus 90 plus 150 minus 160 plus 200 minus 210, 250 minus 240, and absolute, everywhere absolute. So means it is going to give me always a positive divided by total number of the data set that we have. So here we can simply say that okay, so this is going to be 100 minus 90 plus 150 minus 160 plus 200 minus 210 plus 250 minus 240 plus 300 minus 310. Yeah. And now just try to divide it by 5, a total number of the data set, which is nothing but a n. Now, if I'm going to do a math, I will be able to find out that mean absolute error is equals to 10. As simple as that. So this is going to tell me that what is the average, on an average, what was the difference between the predicted value and the expected value. It should not be very, very big, by the way. And here I'm able to find out that mean absolute error is not very big at all. So this is one of the parameters that you can try to use, and this is how we can try to calculate a mean absolute error. Now there is something called as a mean squared error. So MSE. So again, this is one of the parameter by which you will be able to judge the accuracy of the matrices. It's a very simple one. So mean squared error, yeah, for a regression, by the way. So formula of MSE is again very simple, as it suggests mean squared error. So average of the square, by the way. So here 1 by n, total number of the data, summation of I is equal to 1 till n, and y minus y hat means actual minus predicted square. So this is going to give you a mean squared error. Now with respect to the previous data, if I have to do a math, if I have to do a calculation that what is a mean squared error, so I can do it. So 100 minus 90, 150 minus 160. So 100 minus 90 of a square, 150 minus 160 of a square, 200, 210, 200, 210 of a square, and then 250, 240. So 250 minus 240 of a square plus 300, 310. So 300, 310 of a square divided by 5. Now if I am going to do a math, so it is going to be, so mean squared is going to be 10 of a square plus I can say like negative of 10 of a square plus negative of 10 of a square plus 10 of a square plus negative of 10 of a square divided by 5 So it is going to be 100. So my mean squared error is going to be 100, by the way. And based on that, we try to calculate RMSE. So root mean squared error. So it is nothing but root of mean squared error. So if I have to calculate a root mean squared, so 100. So technically root mean squared error is going to be 10 at the end of the day. Yeah, 10 at the end of the day. So these are the matrices. So mean absolute error, mean squared error, root mean squared error. So these are the evaluation parameter. You are going to use it for evaluating any kind of a regression model at the end of the day. Simple, right? Simple. So here, if I'll have to talk about maybe a mean squared error, root mean squared error, or mean absolute error, in general, the ideal value is supposed to be 0. So as we have received a 10, then 100, and then 10, but ideally it is supposed to be 0 if my model is 100% accurate. If my model is not 100% accurate, so obviously it is going to fluctuate in a positive direction. So it is never going to be a negative. It is always going to fluctuate in a positive direction. It simply means that I have some sort of a error inside my model. My model is not able to do a correct prediction at all. This is what it means. So hope we all are able to understand mean absolute error calculation, mean squared error calculation, and root mean squared error calculation. And in my machine learning chapter, so anyhow, I'm going to talk about all of these things in a very, very detail. I have already discussed about these things in a very, very detail with respect to a complete derivation. But yeah, so this is just a recap of each and everything that we have already done. So with that, thank you so much, everyone. Take care and see you again in my next chapter. Okay, so welcome back to lecture once again, guys. Now in this lecture, I'll be talking about how to find out a best parameter. So we have already built a classification model. Now for that classification model, how I will be able to find out a best possible parameter so that I can try to build a best neural network. So how I will be able to find out a best layers, how I will be able to find out a best learning rate, how I will be able to find out all the other parameter that we try to use during a training. So there is a library called as Keras Tuner, and that is going to help you out in terms of tuning the entire model. So what it does, randomly it is trying to take a values and then it is trying to train the model, is trying to test the model validation accuracy. It is going to calculate the validation accuracy of the model, and then it is going to decide that okay, so which one is giving me, or which trial or which combination is giving me technically a best outcome, and it is going to suggest you that one, that okay, so when you are going to create a model, try to use this. So this is the number of the layer that you have to create. This is the total number of the neuron inside the layer you have to create, or maybe this is the activation function you should use. This is basically a learning rate that you are supposed to use. Each and everything you will be able to tune it. So let's get into it and let's try to see the practical. But before that, so you have to install a Keras tuner. So you can try to come over here. Let me do a CLS. We are using a UV environment. So I can try to do UV pip install and Keras hyphen tuner. That only it is going to work. Otherwise, it is not going to work at all. So just try to do UV pip install Keras tuner and it will be able to execute. It will be able to add it inside the environment. Now I'm going to use the same thing. I'm not going to use anything different over here. So I'm going to use the same X test and Y test from the iris dataset that I have been talking about with respect to the neural network. So first of all, just try to import. So import Keras tuner as KT. Yeah. So just try to import it. And if I'm able to import it, it simply means that this Keras tuner is available inside my environment. So once it is available inside my environment, one by one. So let's try to do it. So here I have created a very simple like a function. So where inside this function, you can try to pass a hyperparameter, right? You can try to pass a hyperparameter. So inside this, we are trying to create a model. So we are trying to create a sequential model, a same model that I have created before. So it's nothing new for me. And here, so I'm trying to add a input layer. Input layer is equals to 4 as we have like a 4 column. So sepal length, sepal width, petal length and petal width. And here, so one by one. So I'm trying to get into layers, right? I'm trying to get into a layer. So maybe I can try to talk about layer number 1, layer number 2, layer number 3. So it will try to like get a combination that, okay, fine. So if there is a 1 layer, if there is a 2 layer, if there is a 3 layer, right? So it is going to add those layers, as simple as that. So here, so basically I'm just trying to say that, okay, fine. So try to do a trial from this to this particular range. This is the only thing which I'm trying to say over here. I'm not saying anything different over here. So I'm trying to say that, okay, fine. So just try to use this one. And here, so I'm trying to say that okay, fine. So in every layer, so always try this out with a minimum number of like a neuron inside a particular layer is equal to 4 and a maximum number of a neuron is equals to 32. This is what I'm trying to say. So here I'm trying to say that minimum number of neuron in one layer that you can try this out with a 4 and the maximum value is equal to 32 and then step is equals to 4. It simply means that when I'm saying a step is equal to 4, right? So try with this combination. So try with 4 neurons, 8 neurons, 12 neurons, 16 neurons, 20 neurons, 24 neuron, 28 neuron and 32 neuron. So this is what I'm trying to say over here. Nothing much, right? Nothing much over here. And every layer, so we are trying to use activation function is equals to ReLU. And do these things for 1 till 3. So this may number of the layers. So try to do this particular experiment. So this is what you will be able to find out. Now, so what is next that we are trying to do over here? So the next thing that we are trying to perform in this particular place is basically, so we are trying to add a final layer. Our output layer, you can say. So output is 3 because our classes are 3 and that is going to be the constant. Okay. Now here, so even for a learning rate, I'm trying to give a choice 0.002, 0.01, 0.001 and 0.0001. So these are the 3 combinations I'm trying to do. And I'm saying that okay, fine. So try to even test it with respect to the learning rate. And then I'm trying to call a model.compile and here, so it is going to call Adam Optimizer. I have already used it even in my previous lecture, if you remember. And rest of the things is completely same. So this is just a simple, like a small function that I have created, nothing much. And based on this particular function, so I will be doing a Keras tuning. Yeah. So Keras hyperparameter tuning. So here for a tuner, so I'm going to call a tuner over here. And I'm going to say that Keras tuner dot random search. And I'm trying to call a build model function. So this is going to build a model with all those combinations which I have already taken over here. And then objective is basically a validation accuracy. Matrix trial is equals to 5. So do the trial for the 5 times. This is what I'm trying to say over here. Execution per trial means in one trial, try to do execution twice and try to take the average. This is what I'm trying to say. Directory is equals to Keras tuner log. So try to create a Keras tuner log directory and try to store all of those log inside this one. Project name is equal to iris tuning. So it is going to create a iris tuning folder inside this KT logs, basically Keras tuner log. So once I am going to execute it, so this is going to work for me and then I can try to call a final hyperparameter tuning. So how I will be able to call this final hyperparameter tuning? So to call this tuner.search and I have to provide my X train data, Y train data. I'm going with the epoch of 20 and validation split is equals to 20%, right? We have already done that. So these are the old thing basically. So tuner.search. So randomly it is going to take all these combination which I have already given inside my function, right? For a layer, for a number of neurons, for number of layers, for a number of neurons inside the layer, for a learning rate. I can try to take any other parameters as well, and that is going to work. I can try to take as many parameters as possible and then just try to execute it, and it will start tuning, it will start testing my model as soon as I'm going to execute. So let's execute, and you will be able to see unable to synchronize open file kt logs. Okay, trial for checkpoints. So I have already executed it, and because of that it is giving me an issue. So let me delete my kt log permanently from here. Let me refresh my environment. Now I don't have a kt log. Okay, so just because of this, guys, it is giving me an issue. So let me fix that issue, by the way. Okay, so just to fix this issue, maybe I can change my directory name. So ktt log, I can say this one, because this directory is not available. Now, once I'm going to execute it, so you must be able to see that it has started training, and it has started taking a trial, a different trial, a different combination where it is trying to experiment with the number of layers, unit in a particular layer, and learning rate I'm able to see. And with respect to this, it will try to do a evaluation. So this is what Keras tuner does. It's doing nothing. So basically it is trying to take all the combinations, and based on the combination it is trying to find out the best value. So Keras tuner is one of the best hyperparameter tuner that you can try to use it. And yeah, so if your range is going to be big, then obviously you are going to see it is going to take a lot of time. So you will see that it is like taking a lot of time. Otherwise, if my range is small, so in that case, it is not going to take much of time. Now here, tuner is done. Now I can try to call a tuner.summary, by the way. So result summary I can try to call. And here, so you will be able to find out that from a KTT log, right, the folder that I have created, so showing the best 10 trials over here. The best trial score was 89 point something, 89.58. So the learning rate it is suggesting me is equal to 0.01. Number of layer it is suggesting me is equals to 2, by the way, and unit is equals to 4 in a layer 1. So in a unit 1, number of neurons is equal to 4, unit 2, number of neurons is equals to 4. This is the suggestion that I have received. Trial 4 summary. So yeah, it is trying to give me like a summary of each and everything, and based on this, I can try to select. So a score for this one is 0.75, so not a preferred one. I'll go ahead with this one, by the way. So I'll try to create a number of layer 2, and there will be 4 unit in a first layer, and there is another 4 unit I will be taking in a next layer. So this is the 2 number of hidden layers I will end up creating. And at the end of the day, so I'm supposed to take a learning rate is equals to 0.01, as simple as that. Maybe if I'm going to execute it once again, so it is going to give me some different result. There is a possibility, right? There is a possibility. So I have already mentioned that always try to do a experiment with a 5 maximum trial. If I'm going to say that try to do this experiment with a 10 maximum trial, then maybe it is going to do an experiment with the 10 maximum trial, means 10 different kind of a combination. So if I'm going to increase the number of combination, there is a very high chance. There is a very high chance that my final result is going to change, and a number of layer that it is going to suggest, a number of neurons inside a particular layer that it is going to suggest, and a learning rate that it is going to suggest is not going to be same. So just you can try to play ahead with this parameter. So I have just created maximum trial is equal to 10. Previously it was just 5. So it has taken 5 trials, means 5 random combination from the range which I have given, it has taken, right? Now I have said that, okay, fine. So try to take a 10 maximum number of a trial. So it is going to create a 10 maximum combination. All of these combination you will be able to observe, right? All of these combination. Now I think it has done. Now if I'm going to plot a summary, so now you will be able to find out that this is telling me that, okay, score is equals to 0.91, which is better than before, obviously. Previously I was getting 89 point something. And for this one, so number of layer suggestion is basically 2, and there should be a 32 unit in layer, first hidden layer, by the way. So anyhow, your input layer is going to be 4, your output layer is going to be 3. In between, there will be a hidden layer. So first hidden layer should have a 32 unit of a neuron. Second, so learning rate is equals to 2. So unit 1 is equals to 12 and unit 2 is equals to 4. It is trying to suggest. Now here you must be able to find out like a third layer which it is talking about. So basically it is suggesting me only two number of layers. So it is just trying to do a sample that, okay, so if you're going ahead with the third layer, so in that case, probably you should keep 4 neuron over there. That's it. This is just a suggestion from the Keras tuner that you are able to get. Apart from that, nothing else. Now the second best one is again this one. Maybe we can try to go ahead with the number of 2 layers. First layer will be having, and again, I'm not calculating input and the output layer. I'm not considering input and output layer. It's just a hidden layer which we are talking about. So here unit is equal to 20, learning rate is equal to 0.1, and then second layer is this one, and this is just like a prediction or probability. It is trying to give that if you're going ahead with the third layer, then go ahead with this one, right? So it is just trying to give or it is just trying to do a sampling of the third layer as well. So if you would like to add, but suggestion wise, it should be 2 layer that you should always take. And if you are doing this, in that case, there is a chance that you will be able to get this as a model accuracy, as simple as that. So with the help of this Keras tuner, guys, you all will be able to find out all the hyperparameter, a best one with respect to your data set, and you will be able to create a network architecture accordingly. So you can try to like create 2 layers, and then this is the number of neurons. So hope your confusion is now gone, that what should be the ideal number of neurons, what should be the ideal number of layers, what should be the ideal learning rate that I'm supposed to consider. Again, you can try to increase a number of experiments over here, number of trials. So in that case, it is going to give you a best of best result. So if I'm going to go ahead with a 50 number of combinations, so in that case, obviously there is a chance that maybe I'll end up getting a better one, right? I will end up getting the better one. But again, so all of these things are proportional to the resources which is available inside your system. As simple as that. So with that, thank you so much, everyone. Take care, and hope we are able to learn a hyperparameter tuning with respect to a Keras tuner. With that, thank you so much. Take care and see you again. Okay, so welcome back once again, guys. Now in this lecture, I'll be talking about how to create a virtual environment or how to create a new environment with the help of a new kind of a package manager called as UV, which has been managed by Astral. So UV is a lightning fast package manager, so which is 8x faster than a pip, and you will be able to do installation, all the library dependencies installation with the help of UV. And the beautiful part about UV is that it resolves our dependencies automatically. For example, if I'm trying to install a X library, and that X library requires something called as X, Y, G, A, B, C, D kind of a dependencies, means it requires all those libraries to be installed beforehand. So in that case, UV will be able to resolve all of these dependencies automatically. You don't have to worry about it. Not just that. So I'm even going to show you that how you can try to create that environment, and then how you will be able to use that environment inside a Jupyter notebook. All of these things in a step-by-step fashion I'm going to talk about. Plus, I'm going to attach a documentation which is going to help you out to run this entire things in a quickest possible manner. So let me share my screen. And first of all, try to open up your PowerShell. So I'm trying to use basically a Windows machine. Otherwise, you can try to use your command prompt. That's completely fine. CMD or console. Now, so inside this one, the very first thing that you have to do is install UV. Yeah, PowerShell. So install UV inside your global environment, and this command from Astral is going to do an installation inside your PowerShell UV. So it is going to install UV inside with the help of your PowerShell. So just try to hit enter, and it will take a couple of seconds of time, not more than that. And yeah, so it is able to install each and everything inside this particular location. So user, school, and then local bin. Okay. So it is trying to add each and everything inside my global environment. Now, I just have to do a check. I just have to do a confirmation that whether UV is installed or not. So yes, UV is installed. So current version of UV is 0.7.21. So this is the environment which is ready. So UV is installed. Now this package manager is installed. Now I can try to open up a VS Code, and inside a VS Code, I'll try to create a directory. Maybe I can try to create a test underscore UV kind of a directory. And then I will try to do a setup. I'll try to do a installation one by one. How? Let's try to see. Let's try to understand about that. So here, first of all, try to open up a terminal. Now inside a terminal, okay, so inside a terminal, let's suppose I have to do an installation of a Python. Yeah, I have to do an installation of the Python. And then I have to do an installation of a TensorFlow inside a Python. I have to do an installation even of a Jupyter notebook inside this particular environment. So how in a step-by-step manner I will be able to do it. So here I can try to call UV VENV, right? VENV and then dot VENV. So the virtual environment name which I'm trying to give, you can try to give any other name, that's completely fine. Hyphen Python Python, and I'm looking for this particular version of a Python. So if I'm not going to give a version, in that case it is going to install a latest version by default. But let's suppose for my project I don't want a latest one, I want maybe a 3.10, which is little bit older, not that old, but yeah, little bit older. Now if I'm going to hit enter, one by one, it will be able to install a Python, and here you will be able to see that it has created a folder with the name called as .venv, virtual environment. Inside that I have a library, inside that I have a script which you will be able to find out all these things, right? So by default it is going to create this particular directory for all of you. Now if I have to activate this environment, let's suppose if I have to use this environment, so how I will be able to use this environment? So first of all, I'll go inside this directory. Now inside that I'll go inside the scripts directory, and inside that there is a activate command. So I'll try to call a activate command, and with the help of this I will be able to activate this environment. Let me do that. Like I said, so first of all I'll go inside this directory .venv, right? And then I will try to go inside a directory called as capital SCRIPT. Step by step I'm doing it, guys, right, for the very first time, so that from the next time onwards you will be able to do it automatically. Now inside that we have a activate, right? Inside that we have a activate. So just try to call ACTIVAT. No need to remember anything. So activate. Now, so system could not find the path specified, so it should be scripts S. So S, okay. So here you will be able to see that it has activated my virtual environment, and whatever I'm going to install inside this environment, it will be able to use it. It will be able to use it automatically. Now, so let's suppose we have to install a Jupyter notebook. Yeah, Jupyter notebook inside this environment. So I can try to call UV pip and then install, and then NOTEBOOK notebook, and then IPYNB kernel if I have to install. So IPYKRNEL kernel. Okay. So one by one, it will keep on installing all the dependencies. I don't have to worry about anything by the way. And here is the installation that it has done. Whatever supporting files are required, whatever dependencies are required, everything has been resolved. I'm not doing anything, right? Everything is being managed by my UV. And here, so you will be able to, like, for example, so let's suppose if I'm going ahead with the TensorFlow installation. So let's go ahead and do the TensorFlow installation. So here, again, I'll try to call UV pip install TensorFlow, TensorFlow. Sorry, spelling mistake, TensorFlow, TensorFlow. Yeah. So now it has started installing TensorFlow inside my environment. And again, I don't have to worry about anything. So based on my Python package, based on the existing things, and based on the dependencies which is required for a TensorFlow, it will do all the installation for me. So I don't have to worry about anything, by the way, right? So yeah, all of these installations are done. Yeah, all of these installations are done. I can even come and check that whether TensorFlow is installed or not. I can even try to launch a Jupyter notebook. Let's suppose I have to install other libraries. For example, I have to install a Pandas, I have to install a NumPy, I have to install a Matplotlib. Okay, so UV and then pip install install. I can try to give a library name. Let's suppose a NumPy I have to install, right? Then Matplotlib I have to install, and then I have to install Pandas. So just try to give all of these library name, and it will end up installing each and everything inside this particular environment. So this is the beauty. This is the beauty of a UV. Okay, there is one more thing. So now let's suppose we have to migrate this entire file, and we have to keep all the installation that we are trying to do inside a particular file. So where it will be able to manage, it will be able to retain all the libraries which I have installed. So what I can do, I can try to call uvinit, uvinit. And by doing this, you will be able to find out that it has created a file called as project.toml. Yeah, project.toml file it has created. And inside this, if you will go and check, so it has created a environment name. So this is the environment name. This is the version. I can try to add a description. I can try to like I can't basically. So here you will be able to find out that it has given me a version that, okay, so version which I am trying to use is basically greater than or equal to 3.10. So this is the Python version which I am trying to use. And dependencies. So dependencies means a library which I would like to maybe migrate, or maybe which I would like to like use it in my another environment, same kind of environment if I have to replicate. So if I have to add some sort of a dependency, so I can try to use uv add ten sor flow TensorFlow. UV add and TensorFlow. So yes, it should work, by the way. TensorFlow. So distribution, this doesn't have a source distribution wheel. Okay, so let me try to call an installation of a TensorFlow once again. Added one package, audited one package, and then UV add. It should be able to add, by the way. UV add and then ten TensorFlow. I'm just trying to show you that whether it's adding something inside my environment or not. Let me call UV add pn ds pandas. So yeah, it has added pandas inside this dependencies, and then UV add matplotlib matplotlib. So it is adding matplotlib. UV add numpy, so it's adding numpy inside this one. UV add Jupyter. So adding Jupyter notebook inside this one. So here with the help of add, what I'm trying to do, so inside this project.toml file, so I'm trying to add all the dependencies. And same thing you will be able to find out even inside a uv.log. So whatever dependencies that it has installed, each and everything it is trying to maintain inside this uv.log, so that you will be able to replicate the exact same environment whenever you want inside your production system, just like a requirement.txt file, guys. That's it. Yeah, that's it. Okay. So all of these things are done. Now let's try to create a Jupyter notebook file. So here I'm going to create test.ipynb Jupyter notebook file. Now inside this Jupyter notebook file, I have to use this environment. Yeah, I have to use this environment. So select kernel, Python environment, and here, so this is the environment name which I had given. So I can try to use this environment. Now I can try to test it, that whether things are working inside this one or not. So maybe what I can do, I can try to test it with the TensorFlow. I can try to test it with the pandas or maybe a NumPy, because even pandas, NumPy I have already installed. So here I can try to write that import TensorFlow, TenSOR, TensorFlow as TF and execute. So looks like it is trying to identify a TensorFlow. And yes, I'm able to see a TensorFlow. So maybe I can go ahead and I can try to check. So what is a version of a TensorFlow? So TF__ version. And version of my TensorFlow is 2.119. So this is installed. I can try to even call import pandas as PD or PF. Anything is fine. So even pandas is available. Import NumPy as NP. So even NumPy is available. Import matplotlib as PLT. So yeah, even matplotlib is installed. So with the help of UV in a easiest possible manner, I am able to do all of these installation. That's the very first part. And now I'm able to import it. So going forward, I will be using this particular environment to do a coding. So again, UV is lightning fast, simple, right? UV is lightning fast, plus it resolves all the dependencies automatically. So you don't have to worry much about each and everything or anything, I would say, right? So maybe going forward, you are going to use a UV, and let me know if you are going to face any kind of a issue. So I'm here to resolve your issues. I will be trying, I'll try to answer all of your questions. So if you're going to have any. So with that, thank you so much, everyone. Take care and see you again in my next lecture. Okay, so in my previous lecture, I was able to create a virtual environment with the help of UV. Now we have to see that how we can create a neural network, how we can try to train a basic neural network, maybe for a classification problem, maybe for a regression problem. So obviously we can try to use a classification algorithm or regression algorithm from a machine learning. But even with the help of neural network, you will be able to solve the same thing, exact same thing. Yeah. So I'm going to show you that, but in this lecture, I'll be talking about a data set first of all. So let's try to load a small, simple inbuilt data set, which is going to be a iris data set. It's basically a flower data set. So where there is a column name called as sepal length, sepal width, petal width, and there is a target name or Y value name is called as setosa, virginica, and versicolor. And that data set you can download from internet, or maybe you can try to use a inbuilt library, and from an inbuilt library you can try to load that data set. So let me share my screen, and let's start talking about this data set loading first of all. Only a data set loading in this particular lecture. So here what I will do, I'll try to import couple of libraries so that I can use these libraries even going forward. So first of all, import TensorFlow because I'm going to use a TensorFlow to create a neural network. Yeah. So as a TF. Okay. Now from scikit-learn, sklearn, so which is going to help me out in terms of providing a data as well as in terms of splitting a data into a train and test, in terms of pre-processing a data with the help of one hot encoder and a standard scaler. Yeah. So I'm going to use a scikit-learn for that one. So here data set, and then from this one try to import iris. So load iris. Okay. Now from sklearn dot model selection. So just try to import train and test split. Then from sklearn dot pre-processing. So try to import one hot encoder and a standard scaler. Okay. And yeah, so keep this numpy as well. So numpy as np, and keep this date time as well, date time. So date time, and keep this OS package as well. So if it is required. So yeah, successfully I am able to import all of these libraries. So if you are not able to import some of the libraries, not an issue at all. If it is going to give you a library issue, not an issue at all. So just try to do uv pip install and that library name, and it will be able to install it. Okay, so all of this thing is done. Now let's try to load a data set. So I'm going to load a data set from a scikit-learn. You can try to load a data set even from a CSV file, which is available over the internet. That's completely fine. So here I'm going to call load iris, and it is going to give me a data set, as you can see. So there are four columns. Right? So throughout this one, and there is something called as sepal length, sepal width, petal length, petal width. Sepal length is not visible because of this like a length of this data, but yeah, sepal length is available. So sepal length, sepal width, petal length, and petal width. This is the column name, or this is the feature name, you can say, or X values name, you can say, whatever suits you. That's completely fine, up to you. Yeah. Now let's try to save this data inside a variable iris. Fine. Now, so here let's try to do some sort of a postmortem of the data. So iris dot data. So this is going to give you a data set. Okay, that's cool. Now I would like to see that what is the Y value name, or what is a target name. So again iris dot target target. So target is labeled as a 0, 1, and 2 basically. Now what is the meaning of 0? What is the meaning of 1? And what is the meaning of a 2? What is the technical name of this one? So you can try to check even that part. So iris dot, I can try to call target and names. So wherever we have a 0, actually it's setosa. Its name is setosa. Flower category is setosa. Wherever we have 1, actually its name is versicolor. Wherever we have 2, actually its name is virginica. Fine. So these are just a label which has been given. Actual name is setosa, versicolor and virginica for 0, 1 and 2. Simple. Okay. Now, so what is the column name? Although column name was visible over here, right? Column name was visible when I have called this iris data. But let's suppose if I have to check, if I have to see that what are the column name which is available. So I can try to call feature names, and this is the column name: sepal length, sepal width, petal length and a petal width. So 1, 2, 3, 4. Now let's suppose I have to see this data as a data frame in a structured way. I have to see this data. Yeah, I have to see this data. So how I can do that? So maybe I can try to call pandas. I think I have already done the import. Okay, import is not done for pandas. Installation is done. So I can try to import, basically import pandas as PD. Okay, pandas as PD. Pandas dot data frame, and here I can try to pass my iris dot data column and then column name. So columns column name. So iris dot feature name is going to be the column name. So this is the actual data set that I have. This is the X value that I have. Yeah, this is the X value: sepal length, sepal width, petal length, petal width. Now let me save this data, iris underscore df data frame. Now this iris data frame, inside that I have to add even a target value. Yeah, target value 0, 1, 2, 3, 4, right? So target is the new column I can try to create, and value of this one is iris dot target target. So now if I'm going to show you my data frame, right, you will be able to see even a y value, that this is been classified as 0, this is been classified as 0, this is been classified as 2, and in between, so we have 1 as well. So 0, 1 and 2. Now this data set is a perfect data set for me to solve a classification problem, because we have a 3 classes over here. A multi-class classification problem we can try to solve with the help of this data set. So we have a 3 classes, a class 0, class 1 and we have class 2. And one more thing you have to observe, that we have a sepal length, sepal width, petal length, petal width, and scatterness of this data, a range of sepal length, sepal width, petal length and petal width is like not normalized. So maybe we can try to normalize this entire value, because that is going to help me out in terms of preventing, right? In terms of preventing the overfitting of the model. So whenever I'm going to create the model, this is what we do even in case of a machine learning. I believe we have discussed about that multiple times, so many times, right? Okay, so to do that, maybe we can try to call a standard scalar over here. So a standard scalar object, let's try to create it, and scalar scalar. Now scalar dot scalar scalar dot fit transform I can try to call, and here, so I can try to pass, basically I can try to pass iris dot data. Yeah, I can try to pass iris dot data, and I can try to store it as x underscore scaled 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 scaled. Okay, fine. Now if I'm going to show you my x data, this is how my data set looks like. Sorry, x scaled. So here now you will be able to find out that the range of my data set has changed, because I have called a standard scalar. And what it does, so standardize a feature by removing the mean and scaling unit and variance. So here it is going to standardize the entire data set with the help of this one. So data minus average divided by a standard deviation, right? Divided by the standard deviation. So it is going to basically perform the standard scaling operation, and now my data set is in between a particular range, Okay, so this is done, right? This particular part is done. So now I'm able to create my x. Now what about my y? So do I need to do any kind of a treatment with respect to a y? Let's try to understand even that particular part. Okay, so let's try to do a treatment with the y. So how does my y looks like? So this is how my y looks like. So 0, 1 and 2, and as you can see that we have a one dimensional array over here. Now, so we can try to convert this entire data into a one hot encoding so that I can try to pass the same thing, exact same thing inside my neural network. So, and what one hot encoding is going to do? Let's try to do it one by one. So here, first of all, one hot encoding requires a 2D array, not just 1D array, which is available to me. So to convert my data into a 2D array, I can try to call iris dot target. This is going to give me this above data dot reshape. I can try to call, and here, so I have to convert this data into 150 is to 1. Yeah, so 150 is to 1, or maybe I can try to give -1. It will be able to take a shape automatically. So now if I'm going to show you my data, so this is how my data set looks like. Yeah, this is how my data set looks like. Now it's been converted into a 2D array. I have not done anything, so just converted into a 2D array. So 150 cross 1. Simple, 150 rows and 1 columns. Now I can try to pass this data to perform the one hot encoding. So just try to call one hot encoder, and sparse output is equals to, let's keep it false, so that I will not be able to get a sparse matrices, means a 0 matrices. So here I can try to label it as a encoder. So this is the variable, and now I can try to call encoder dot fit transform. Yeah, and then I'm going to pass my data over here. So let's suppose if I'm going to pass my y, and then it is going to return me y underscore encoded encoded. Now y encoded, how does my y encoded looks like, by the way? So this is how my y encoded looks like. Now this is called as one hot encoding, and if you remember, which I have already discussed multiple times in my class as well, that what is one hot encoding. So one hot encoding is nothing but, let's suppose, let me explain you this part. So let's suppose we have data, we have x and we have y, right? So x is, let's suppose, 2, 4, 8, 10, and for that we have a class is equals to 1, 0, 2, 1, something like this. So how many total number of y do we have? Total number of distinct y that we have is 1, 0, 1 and 2. Okay, so 0, 1 and 2. Now, so if I have to convert this with the help of one hot encoding, so this with the help of one hot encoding, so what I will do, I'll try to write 0, 1, 0. So wherever we have this data, we'll write 1, and in the rest of the places, I'm going to write 0. So if I have to convert this one into one hot encoding, so I'll write 1, 0, 0. If I have to convert this one into one hot encoding, then 0, 0, 1. Now if I have to convert this one into one hot encoding, so I can write 0, 1, 0. Means wherever we have this data, so I'm just trying to convert into one hot encoding. So now this is basically one hot encoding, where this one is representing class 1, this one is representing class 0, this one is representing class 2, this one is representing what? Class 1. Class 1. Yeah. So this is something called as one hot encoding, and this is a nature of the y, or this is the type of the y. We are going to use it for our neural network training. So yeah, successfully we are able to convert our data set into one hot encoding. So 0, 0, 0, so 1, 1, 1 you must be able to find out. Then if you'll come down, so wherever we had 2, so at second place, so 1, 1, 1 in rest of the places, so there is a 0, 0, 0, 0. So we are able to do a one hot encoding of the data set. Now once this part is done, data set is ready. So now we can try to call maybe our train and test split, and we can try to split our data set. So I can try to pass x scaled over here, y encoded over here, and then I can try to say that test size is equals to 20% and the training size is going to be eventually 80%, right? 80%. Okay, that's cool. So this is going to return me, x underscore train, x underscore test, y underscore train, y underscore test. So this is something it is going to return. Now I will be using this x train, x test, y train and y test for my model. Yeah. So data set is ready, guys, so far. we are able to prepare our entire data set. Now, once my data set is ready, what I will do, so I'll try to prepare a neural network so that I will be able to pass this data inside my neural network, and then I will be able to eventually train my neural network, save a final model, and then finally we are going to test it. So we'll try to see that in my next upcoming lecture. With that, thank you so much everyone. Take care and see you again in my next lecture. Okay, so welcome back once again, guys. Now in this lecture, I'll be talking about how to create a neural network based on the example that we have, a data set that we have. So here, if I'll talk about my data set, so inside my data set, I have 4 column X train. If I'm going to show you, so inside my X train, I have a 4 column, 1, 2, 3, 4. This is the column that we have, right? So we have to pass this particular data inside a neural network. So how I'm going to create a neural network, or what kind of a neural network I will end up creating? Let's try to talk about that. So here, what I can do is that I can try to create a input layer. So where I can try to place 4 neurons, right? And then eventually I can try to create a hidden layer where I can try to give maybe a n number of neurons. Then again, I can try to create maybe like a hidden layer. So where I can try to give again n number of neurons. And then I can try to provide the output layer. So output layer will be having, let's suppose, 3 neurons, because we are trying to do a classification and we have a 3 different kind of a classes. So maybe this kind of a neural network I can try to create. Now inside a hidden layer, right? Inside a hidden layer, so I can try to give a activation function. That's completely fine. So maybe I can try to give a ReLU activation function, rectified linear unit. I can try to go ahead with the Swiss function. I can try to go ahead with the leaky ReLU, but ReLU is like a moderated one. So I think I can try to use that one. Again, here I will be having a hidden layer. So I can try to use a ReLU. And then here, so we have to do a multi-class classification. So maybe I can try to go ahead with the softmax, right? Softmax as an output function. So in this way, I will be able to create an entire neural network structure, entire neural network diagram. Not just that. So I'm going to even show you like after creating this neural network. So I'm going to show you even how to visualize this entire neural network. Even I'm going to show you that it is going to define a random weights, right? It is going to define a random weights, maybe weight 1, weight 2, weight 3, and so on weight n. So what will be the value of the weight? Plus it is going to attach a biases, right? So what will be a value of biases? Each and everything I'm going to show you. Each and everything from the scratch, one by one, step by step, video by video, I'm going to show it to you. So let's start doing it. It's not very difficult, but yeah, so we are going to do a lot of postmortem with respect to this entire neural network, so that once and for all, this fundamental of the neural network will be very much clear. You will be able to visualize it, even if it is going to be a complex neural network for all of us. So here, first of all, to create a neural network, let's start writing a code. And I'm going to use a TensorFlow Keras library, because Keras is a high level APIs, and with the help of that, you will be able to create this entire neural network in a easiest possible way. So here, TensorFlow dot Keras, you can try to call, and then dot, first of all, I have to create a input layer, right? Input layer, for example, this one. So input layer I have to create. So where inside the input layer, so I have a 4 neurons. So here I can try to create a input layers, and then I can try to define a shape. So what is the shape of this input layer? So shape of this input layer is 4. This is something which I have given. Now let me like store it inside a variable called as inputs inputs. Okay, so this is my input layer. I'll show you visually as well, so don't worry about that. So input, and then I have to create a next layer, which is going to be the hidden layer. So I can try to call TensorFlow.keras.layers. I can try to call basically something called as dense. So which is nothing but a hidden layer. And inside this hidden layer, I would like to place 10 neurons. I can try to even change it. That's completely fine. Yeah, I can try to even change it. And there is no harm, right? There is no harm. And even if you will go to Google, let me show you one more example. So let's suppose if I'm going to Google, and if I'm going to call TensorBoard. So here, TensorBoard play, let's call that. Yeah. So here, as you can see, we can try to create input. We can try to create n number of neurons inside a first hidden layer, and then we can try to add a couple of more hidden layers, right? We can try to add a neuron, and then we can try to create the output layer. So exact same thing I'm going to create. Exact same thing I will be creating. So let's suppose here I have to create maybe 10 neurons. Here I have to keep maybe 8 neurons. I can do each and everything. And plus you must be able to see a value of weights. You must be able to see the value of biases. I'm going to show each and everything in a depth and in a detail. So here layer name dense and 10 neuron I'm going to create. So inside this one, inside the very first dense layer or hidden layer, so I'm going to keep a 10 neurons. Now inside this particular one, I have to keep activation function as well. So activation is equals to, let's suppose I'm going to keep RELU, yeah, RELU function, rectified linear unit. And this is going to take an input from the previous one. So whatever output this one layer is going to give, it will be attached as a input over here. Okay, so inputs, that's cool. So this is going to be my, let's suppose I'm going to name it as a X. Yeah, I'm going to name it as a X. Now if I have to create a next hidden layer, so maybe this next hidden layer, or as per my this diagram, so this is the layer, let's suppose I have to create. Yeah, this is the layer I have to create. So how I will be able to create it? So again, TensorFlow dot Keras, I can try to call dot layers, I can try to call dot dense dense, I can try to call, I can try to give a number of neurons. So maybe I can try to keep 8 over here. I can change this value. I can change this value. Activation is equals to, again, I'm going to give a ReLU, right? And input inside this one will be the output of the previous layer. So the previous X I'm trying to provide here. Simple, layer by layer, I'm trying to connect each and everything. So here, let's suppose I'm going to save it as a X over here. And then I can try to create a next layer, which is going to be the final layer or output layer, where I will be having 3 neurons, and the function is going to be softmax, so that it will be able to give me probability for each and every classes. So TensorFlow dot Keras and dot layers dot dense, I can try to call, and here, so I have 3 neurons because I have 3 classes, Setosa, Virginica and Versicolor, and activation is equals to, this time I'm going to keep as a SOFT-MAX, so that it will be able to give me a output based on the probability. So soft max, okay, and the previous output will go inside this as a input, and I'm going to name this layer as a OUT-PUT output. Okay, so this is something which I have created. Now I have to build the final model. So to build a model, I can create a variable called as model. I can try to call TensorFlow dot Keras dot model, TensorFlow dot Keras dot model, and here, so model input is going to be inputs that I have created in the very first line, this one, and model output is going to be output. So it should be INPUTS, that's the variable name, and outputs which I have created. Yeah. So this is going to be my model, by the way. This is going to create my model, and this model is a very, very simple model that I have created. So where in a very first input layer, I have 4 neurons, right? So 4 neurons, as I have a 4 column. Then inside a next layer, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 neuron. Then in a next layer, I have 1, 2, 3, 4, 5, 6, 7, 8 neuron. And in the output layer, 1, 2, and 3 neuron I have. So this is basically my input. This is my input. This is basically my output. This is my hidden layer 1, and this is my hidden layer 2. And all of this neuron will be connected to each other, right? All of this neuron will be connected to each other. Again, all of this neuron will be connected to each other. And here there will be a weight. So I'm going to show you each and everything, that what kind of a weight it is going to initialize with layer wise, right? Layer by layer. So what kind of a weight it is going to be initialized with. And here, so we have an activation function as a ReLU. Here we have an activation throughout the layer. And here we have an activation function as a ReLU. And here basically we have a soft max, right? We have a soft max over here. So this is a very plain, simple and a basic neural network that we have ended up creating. Okay, that's cool. Now layer by layer, if I have to show you, so model.summary, I can try to call, and it is going to show you the layer by layer information that, okay, so there is an input layer, and there was a 4 neuron parameter, trainable parameter is equal to 0. There is a next layer, basically a dense layer, so where neurons was 10, and parameter is 50 that you have to train. Now there is another dense layer, parameter neurons is 8, parameter is 88, then there is a final layer, and here so neurons is 3, and then parameter is 27. So in total the size of the model is 660 byte. This is the size, and a trainable parameter that we have is equal to 165. Now going forward, in my immediately next lecture, I'm going to show you that how we can try to visualize it. Yeah, how we can try to visualize it as a image, the same model that we have. So how I will be able to visualize this particular one. So with that, thank you so much everyone. Take care, and see you again in my next lecture where I'm going to show you the visualization. Okay, so welcome back once again, guys. Now in this lecture, I'll be showing you a visualization. So that in a beautiful manner, you all will be able to see that how this entire neural network actually looks like. So here to do the visualization, I have to call from TensorFlow, dot Keras dot I can try to call utils basically, and import plot model. Yeah, so this is the library which I'm going to import, a plot model library. Now plot model I can try to call over here, and inside that I can try to pass my model, the model that I have already created in the previous lecture, right? This is the model which I have already created in a sorted way. Now so here I can try to say that show shape, and let's try to make it as a true. Yeah, so we are going to see the shape and show basically a layer name. So yes, true I can try to make, then show data type I can try to make it as a true, and then show layer activation is equals to, I'm going to make it as a true, and then show trainable I'm going to make it as a true. So all this show things which was available, whatever show was available, so I have made it as a true. Now if I'm going to execute it, right, if I'm going to execute it, you will be able to see a beautiful this entire layer by layer things, right? So this is the information, you will be able to see it. Now again, let's try to analyze it. This is nothing different, by the way. So whatever I have shown you over here, so I'm just trying to show you in an image format. So input layer 1, so output shape is basically 4, output data type is basically float 32, and then there is a dense layer. We have used activation function is equal to ReLU over there, right? Now input inside this this particular layer is going to be 4, output is basically 10, and this parameter, the parameter in this layer is basically a trainable parameter. This is the reason, so it's showing me in a green that yeah, it's a trainable parameter. Then we have a next layer, input is 10, previous layer output was 10, right? So input is 10, output shape is equal to 8, this is the data type, again parameter is trainable. Then there is a next one, so basically activation is softmax. This is the third layer, a final layer or output layer you can say, where input is equal to 8 and then output shape is equal to 3, and then even parameter is equal to trainable. So even in this amazing way, you will be able to visualize it, and this is possible with the help of plot model. So pi dot we are trying to use it. So initially system is going to give you an issue that pi dot is not available. So please try to install that pi dot. You can try to call uv pip install pi dot, and just try to restart your kernel, because sometimes it is not going to work. So restart your kernel and then try to call this one and make all of this true. So whatever show is given, so parameter is given inside this plot model, make everything true, and it is going to show you this particular one. Very simple, right? Very simple. And it's an amazing way to look into the model layer by layer, that how my neural network actually looks like. Yeah. There is another library called as Visual Keras. Let me show you that. This is not like going to give you lot of detail, but yeah, some detail it is going to give you. So Visual Keras, and here, so Visual Keras dot, you can try to call layered view, and then inside that you can try to keep a model, and then you can try to legend is equals to true. Yeah, so like there are a lot of parameter that you will be able to find out inside a Visual Keras. It's possible, and you can try to, like, check each and everything. You can try to call each and everything, and it is going to show you like in detail. But yeah, let me execute this part, And here, so it is trying to tell you that there is an input layer and there are like a 3 dense layer that we have created. So the pink one is trying to represent a dense, and this one is yellow one is trying to represent the input one. There are other parameters as well, right? As you can see, there are other parameters. So you can try to call all of these parameters if you want. So some values are inbuilt, some values are default. But yeah, you can try to call other parameters, and maybe you can try to like see all of these things, right? See all of these things. It's up to you. But yeah, so I think we are able to get a sense of it. Now let's suppose I have a model, right? So okay, so I believe visually we are able to see each and everything. Now in my next lecture, I'm going to show you that how you will be able to see a weight of a layer 1, weight of the layer 2, weight of the layer 3, and so on, how you will be able to see that. Okay, so welcome back to lecture once again, guys. Now we'll try to do a little bit of postmortem in this lecture of a neural network, and we'll try to show you that how the weight and the biases looks like layer by layer, layer by layer. Let's try to understand that. So in a previous example, so I was talking about this, and I have already shown you a layer by layer this diagram, or you can say a layer by layer details. Now, so let's suppose I have this model which I have already created, and obviously if this is the neural network, right? This is the neural network. So if I have a input layer and then if I have a hidden layer, so we know that input layer will be connected, or one neuron will be connected to all the neuron available inside this hidden layer. And there will be a weight, right? There will be a weight W1, W2, and so on. Plus there will be a biases that we try to attach, right? We try to attach a biases. Now, randomly it is going to initialize a weight, right? If we are not going to initialize from our side, so randomly it is going to initialize the weight. So how we will be able to check that what is the weight? And even like in every layer, so we try to train the model. So in every layer also you will be able to see the weight after the training. That is also possible, right? That is also possible. So let me show you how to check a weight. So here I can try to call model that I have created dot. There is something called as layers, right? So first of all, get layer, and let's see what it is going to yield. Get layer, yeah. So this is going to give me just an object, and here I'm not going to call get layer, by the way. I'm going to call layers, let's suppose. So this is the layer that we have: input layer, and then dense layer, and then dense layer, and then dense layer. Fine. Now, so let's try to call only a layer 1. Fine. Let's try to call only a layer 1 over here. Now I can try to check what is a weight, right? I can try to check what is the weight. I can even try to like set the weight. I can try to even call a trainable weight. Each and everything I will be able to plot, and I will be able to print. So first of all, let me call basically a WEIGHTS weights. So here you must be able to see the weights, right? You must be able to see the weights. Now if you are going to look closely, so we have 4 such weights, or 4 such array we have over here. So 1 will be connected to 10. So here in the very first one, if you will check the number of values, so 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9 we have. Then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It should be 10. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Maybe, okay, on this side, sorry. Okay, that's the reason I was just assuming that why it is showing me 9, because it should show me 10. So yeah, it is showing me 10, right? So it is showing me 10. So 10, 10, 10, and 10. So here, so this 10 we are able to see for this one, for this one, for this one, and for this one. So this is the weight, W1 to all. Now for this, W1 to all. For this, W1 to all, and for this, W1 to all. So weights we are able to see very clearly, right? Very clearly that this is the weight which has been initialized internally, right? Now, similarly, so for layer 1, I am able to see the weights. I can show you a weight even for a layer 2. So for a layer 2, I can show you the weight. So here 10 is to 8, right? So 10 is to 8. So here we have a 10, and everywhere you will be able to find 8. 1, 2, 3, 4, 5, 6, 7, 8. So 10 neuron connected to the 8 neurons. Simple. 10 neurons connected to the 8 neuron. So now if I'm going to draw this entire neural network in a clean way, so 1, 2, 3, and 4, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2, 3, right? And now this one is connected to all of this one, and we are able to see a weights. We are able to see a weights. Now this one is connected to all of this one. Yeah, all of this one. Now this one is connected to again all of this one. So what I'm trying to show you over here is that it's not a black box that we are talking about. We are talking about something which you can visualize. So now this one is connected to all of this one. Yeah. So this is how the first layer looks like. And we were able to see all the weights for the first layer. So there will be an input. Let's suppose we have x1, we have x2, we have x3, and we have x4. Technically, it's a sepal length, sepal width, petal length, and petal width as per our data set. Now, this 10 will be connected to rest of the 8. Yeah, this 10 will be connected to rest of the 8. So we are able to see even a weight for that one. Everything which we have studied, we can try to visualize it. Everything means literally everything. And we will be able to get the exact data as well. So it's technically not a black box that I'm talking about. Yeah. I think now it looks pretty much colorful to all of us. Okay, so many lines, so many lines. Yeah. So, and finally, like, this one, right? And finally, I will be able to get the output. So this is like a kind of a neural network that we are creating over here. So now we can visualize even this layer weight. So this is my layer 1, this is my layer 2, and this is my layer 3. Now for each and every layer, I'm able to show you a weight. So for layer 2, I'm able to show you a weight. Similarly, so in layer 3, so we have 8 cross 3, right? 8 cross 3. So we have 8 cross 3. So we have like 8 neurons over here, and then it is trying to go towards 3 neurons. So here 8 cross 3, and you can see the weight, right? You can see the weight. So we have basically 8, and then to all 3 it is connected, and we have a weight over here. Now similarly, you can try to even check a trainable weight. So trainable weights you will be able to see. So as of now, my weights and the trainable weights is completely same, right? So this is the weight it is going to eventually change. So once it will start learning the relationship, very simple, right? It will start learning the relationship. So here trainable variable, if I'm going to call, so these are the trainable variable, trainable weight, parameter variable, all these things are exactly going to be same. So you will not be able to find out any kind of a differences. Now let's suppose if I have to like show you a bias. Yeah. So bias. So bias is what? So 3 biases, 0, 0, 0 for third layer. Now for a second layer, if I have to show you the biases, so what is the bias which is initialized? So there are 8 biases, right? And then if I have to show you maybe for a layer 1, so there will be 10 biases, and value of those biases is what? Value of those biases is actually 0. So for weight, we are able to get the value. For biases, we are able to get the value. So now this neural network parameters are not at all unknown to me. I know my input, I know my initial weight, I know my activation function, I know my biases over here, I know my output, I know each and everything technically. Yeah. And even I'm able to visualize my model layer by layer, layer by layer. Very simple, right? Very simple. So hope this makes sense, and this is going to give you a lot of clarity that what happens inside a neural network whenever you are going to create it. And hopefully we are able to decode a neural network, right? We are able to decode a neural network, that what is a weight and what we are going to change, what we are going to change, and layer by layer, even inside a backward propagation. So whenever you are going to change the weight, just call the layer dot weight and you will be able to see the latest value of the weight, right? So everything is a mathematics, by the way. Everything is mathematics, and everything you will be able to see it. So with that, thank you so much, everyone. Take care and see you again in my next chapter. Okay, everyone. So one interesting question everyone try to ask, that how you will be able to calculate a trainable parameter inside a neural network, right? For example, so here it is trying to show me that total number of trainable parameter is basically 165 in like a layer 0. So basically, like before input we have 0, but again in layer 1, so we have 50, layer 2 we have 88, and layer 3, so we have basically 27. Now how this math is going to happen, how we are going to do a calculation. So let me show you in a step by step manner that how I will be able to do a calculation. It's actually very easy. It's not tough, by the way, but yeah. So let's do a math and let's try to do a calculation with the help of maybe pen and pencil. So for this neural network, how and what is going to be the total number of the trainable parameter? Let me show you that part. So we have basically a layer 1, right? We have basically a layer 1, as you can see, and we have 4 neuron over here, and we have 10 neuron over here, right? So let's suppose I'm going to consider only x1 as an input. So this 1 is going into 10, right? So 1 is going into 10. Then x2 is going into 10. So 10 is a weight, 10 is a line, you can say, as a layman, right? So line you can say. Then x3 is going into again 10. So just try to write 10 over here. x4 is again going into 10. So just try to write again 10 over here, right? And then we have 10 hidden neuron, right, on this particular dense layer. And everyone will be having a biases. Biases is also a trainable parameter. So weight and biases is a trainable parameter. Just write 10. Now, if you are going to do the calculation, it's going to be 50, right? It's going to be 50. And that's a region. So if you will check over here, you will be able to see a 50. Yeah, you will be able to see a 50. So the formula is very simple, right? Even manually you can try to calculate it. That's not an issue at all. So here you can try to maybe like do this math. So trainable parameter is nothing but a number of input, you can say, or dense unit into maybe a input neuron plus a biases. So technically this is nothing but a weight I'm going to talk about. Weight plus bias. Yeah, weight plus B-I-A-S-E, bias. Yeah, so weight plus bias. So if I'll talk about maybe layer 1, so the simple mathematics is going to be 4 is our input, and then it is going with a 10 neuron plus a 10 biases. So it's going to be 50. Now, if I have to do a math for a layer number 2, so for layer number 2, it's basically like a 10 into going into 8, right? So basically here it's 10, then here we have like a 8. So 10 into 8, 80 plus 8 is equals to what? 88. Simple. And for layer 3, so there is a 8 and going into 3 plus 3 biases. So 8 into 3, 24 plus 3 is equals to 27. Now if you are going to do 50 plus 88, 50 plus 88 plus 27, so eventually it is going to be how much? It is going to be 165. Yeah, 165. And this is what you are able to see as a trainable parameter. So you can try to do a math, you can try to do a calculation even in a manual way. And again, if you are going to call a summary, model summary, so it is going to show you trainable parameter anyhow. So with that, thank you so much everyone. Take care and hope we are able to learn how to do a math and how to calculate a trainable parameter with respect to a neural network. It's not tough at all. So with that, thank you so much. Take care and see you again. Okay, so now we are able to create a model. We are able to create a neural network. Now we have to compile it. Now we have to execute it. Now to compile a neural network, so we can try to call a very simple one called as model.compile, model.compile, compile. And then inside that, so we can try to pass our parameter. So we have to pass our optimizer, which will help me out to do a backward propagation. And in the backward propagation, so obviously it is supposed to do a changes. So maybe I can try to use a Adam optimizer over here. Then we have to define a loss function. So loss is nothing but I can try to use a categorical cross entropy. So categorical cross entropy over here. And then we can try to use basically a matrices. So matrices is going to be our accuracy matrices. Okay, that's cool. Now, the main part which I'm going to discuss in this lecture is that how we can control a learning rate, or how we can try to set a learning rate while doing this. As of now, we are not starting a training. So unless and until we are not going to fit the model, so we are not going to fit a model with the data, it will not start the training. But let's suppose this is a compile, and here I'm trying to use an optimizer. So how I will be able to use a learning rate, eta basically, right? Eta is a learning rate, and which is constant, right? We can try to even vary it. So how I will be able to use that part, let's try to understand. So here, if we have to define a learning rate exclusively, right? So we can try to call what? So we can try to call basically this function. So TensorFlow Keras optimizer add-on. And then learning rate is basically 0.1. We can try to give learning rate is equals to like anything that I want. That's completely fine, right? I can try to pass learning rate as anything. But yeah, so I can try to pass optimizer. So here I'm trying to pass optimizer is equals to Adam by default. So it is going to take a default learning rate. But here I can try to set maybe 0.001. I can try to set it over here. So in this way, and then I can try to change this one. So instead of passing a Adam, right, instead of passing an Adam over here, so I can try to pass what? I can try to pass my optimizer, where I have customized my learning rate. Very simple, right? Where I have customized my learning rate, and whatever learning rate which I'm trying to pass over here, so it is going to consider only that particular learning rate. As simple as that. So this is an intuition behind a learning rate, and this is how I will be able to change, or I will be able to control my learning rate. Fine guys, so with that, thank you so much everyone. Take care and see you again in my next chapter. Okay, so welcome back once again. Now, most of the thing we are able to do it. We were able to like call a model.compile. So now we have to fit data into a model. So that model will be able to like start doing a training, and we have to set basically a epoch. We have to set basically a batch size. We have to set a validation split. All these things we are supposed to set. So to start a training, I can simply call model.fit over here, and then I can try to pass my x train data, and then y train data. So x and y data I'm going to pass for the training. There is a parameter called as epoch I can try to set. So epoch simply means that how many times we are like sending a same data to the model, right? Sending a data to the model. So we are sending a same data 10 times to the model. Now there is something called as batch size is equals to 8. Let's suppose I'll talk about that. So what is the meaning of a epoch separately, and what is the meaning of a batch size separately? I will be talking about that, so that you will be having a clear understanding, because epoch and batch size, all of these things are like something which you are going to encounter again and again and again. So I believe this is important. So here there is a validation split. So let's suppose I'm going to give 20% for a testing validation split, and then I would like to visualize this entire training scenario, right? I would like to visualize this entire training scenario. Now to visualize this entire training scenario, like how my weight is increasing, how my weight is decreasing, how this is going to train, what was the accuracy, how it is changing things. So if I have to visualize it, I can just call it and it will start training the model. Simple, right? It will start training the model. It's a very small data set, so it will be able to finish it quickly. But I would like to visualize each and everything, that how it is changing the, like at which epoch, at which batch size, how it is trying to change the law, what is the loss that we have, what is the other value that it is trying to change. So to visualize these things, there is a dashboard you will be able to find out called as TensorBoard dashboard. And you can try to create a TensorBoard dashboard for your own training. How you can create it? So it's a very simple. Whatever will happen during a training, so I'm going to log it. I'm going to log it with the date time. Yeah, I'm going to log each and everything. So here I'm going to create a log directory, and then inside that fit directory I'm going to create. So this will just try to create a directory for me, and then I'm trying to call TensorFlow Keras callback TensorBoard log directory, and histogram frequency is equals to 1. Now once I'm going to execute this part, so you will be able to like not now. So yeah, let me call this part. So here inside this model.fit, right, inside this model.fit itself, what you have to do, so you have to basically add one more parameter called as callbacks basically. So just these two lines. So this is not doing nothing. So this is trying to create basically like a folder, right, directory structure log inside that fit. And then we are trying to call a logging directory, and then histogram frequency is equals to 1. That's it. And this is this TensorFlow callback you have to attach with respect to a model.fit. So that now if I'm going to call the training, right, so it will log each and everything. It will log each and everything. Yeah. So now if I'll go and check, it has created a folder called as logs. Now inside that, inside this fit, it has created this directory name, and inside that train and for validation, it has created a event, right? It has created the event. So this is the event file, a detailed log, which you will not be able to read out because it's available into a binary format. So it has created each and everything. Now this is going to help me out, this log and inside that fit. So this is going to help me out to visualize each and everything that what has happened during a training. And accordingly, so maybe I can try to like change my things if I want. So how I will be able to see this logs, how I will be able to see this logs. So here I have used a TensorBoard, right? TensorBoard. So what we can do, so we can try to go to a terminal, right? And we can try to do a dir. Inside this, we have a logs, right? We have a log which is available. So now if I have to check that what is available inside a log, so I have to call simply a TensorBoard and make sure that this logs is available over here, because this is the folder it is trying to fetch. And inside that we have a fit folder inside this log folder. So it is trying to fetch that. So simple command is TensorBoard - log directory. Yeah. And then your folder name, whatever folder name that you have given, you can just try to give it. And it will take maybe a couple of seconds of time. And then it is going to give you a web page. So where web page at this particular URL, localhost 600000006. So Control C and then try to do a Control V over here, right? Control C and then try to do a Control V over here. And here, so you will be able to see a very detailed observation about your training and your validation. So I can try to check this one. Maybe I can try to check just a training. I can try to check just a validation, that what has happened during a training and what has happened during a validation. Everything you will be able to find out, right? Everything. So for example, if I'm going to click on a scalar, so you will be able to see that as my epoch is increasing. So I have run these things for a 10 epoch, so 0 to 9. So as my epoch is increasing, so for a training, so training is been shown by orange color, and like a validation is been shown by a blue color, right? So this is the color map. Now how this is like increasing, so whether it is increasing, so yes, I can see that during a training, which is an orange line for me, right? So during a training, so yes, I can see that there is a accuracy which was increasing, and even during a validation, yes, there is a accuracy which is increasing. So this shows me that yeah, model is trying to do some sort of an improvement, right? Model is trying to do an improvement for me. Very simple, right? So all this detail. Now if we'll come down, so epoch learning rate. So learning rate was like a constant. It's a 0.001. If you remember, I have set inside my Adam optimizer. I can try to even make it parameterized so that, you know, keep on changing the learning rate. Don't try to like use a same learning rate. But as of now, I have used a constant learning rate. So it is trying to do in this way. You will be able to see a flat graph, and here you will be able to see a value, right? Now epoch loss. So here I'm able to see that, yeah, during a training and during a validation, my loss is decreasing, which is again a good news for me, right? Which is again a good news for me. Now, so like evaluation accuracy versus iteration. So as my iteration is increasing, means as I'm trying to pass more and more data inside this one, so obviously my accuracy is increasing. My accuracy is increasing. and evaluation loss versus iteration. So yeah, loss is decreasing. So this is the good news, and this TensorBoard is giving you a amazing, like a complete visualization that what is happening inside a model during a training in a very, very amazing way. And the code is very simple, right? So we have not done much, by the way. So we have just created a directory, and we have just created this callback, right? Callback we have just created. And when I'm trying to call a model.fit, I have just attached it. I have just attached it so that it will be able to create a logs and whenever I want. And if I'm going to do a training multiple times, let's suppose if I'm going to execute it one more times, so you will be able to see that it is going to create basically another log, right? It is going to create another log. So every time it is going to basically create a log for me. Now, so see, again, it has created. So yeah, so again, it has basically created a log for me. So now we are able to see a multiple graphs over here, right? Multiple graphs over here. We are able to see it in everywhere. Now, so here you will be able to see basically a graph. So here, Keras, anyhow, model, we are able to see it. So not a issue at all. Now here, so you will be able to see a bias distribution, that how the bias distribution is going to vary in all of these epoch. So in epoch number 1, 2, 3, 4, and 10. Plus how my weights, I have trained my model 2 times. Let me do one thing. So I'll just go over here and delete this file. Continue and delete this file. And again, delete this file. Yeah. And again, I'll try to go ahead and do a training. So I will call a model.fit once again, so that I will be having only one version of the file. Maybe I can try to refresh it over here. It is going to fetch from the log. Yeah. So here you will be able to see that how my weight is changing inside this distribution and how my biases is changing in each and every iteration, and whether it's like a normally distributed or not. Then here you will be able to see a bias and weights histogram. Yeah, bias and weights histogram you will be able to see. So kernel is nothing but the weight we are talking about. This is basically called as kernel over here. So this is going to like help you out in terms of visualizing the entire training procedure and what has happened during a training, what system is trying to do, what model is trying to do. Everything you will be able to visualize it with respect to any given neural network. Very simple, right? So a pretty amazing one, right? And pretty much easy to use it at any point of a time. It's not at all a rocket science to use this entire TensorBoard. So hope all of you are able to understand the this particular TensorBoard, and hope all of you are going to use it to see that what happens inside a network during a learning procedure. And then you will be able to observe that, okay, fine, so we are going into a good direction or we are going into a bad direction. Everything you will be able to observe epoch by epoch, data by data. So thank you so much, everyone. With that, take care and see you again in my next chapter. Okay, so in this chapter, guys, I'll try to explain you that what is a epoch and what is a batch size, and how the actual calculation is going to happen if someone is going to ask you a question that how many time this weight and bias update happens inside a neural network. So I believe you all will be able to answer right after this particular chapter. So question is very simple. How many times we are updating a weight if my epoch is equal to 10 and my batch size is equal to 8, right? So how many times we are basically updating a weight? That's something that we have to do the math. We have to do the calculation. So here, let me do the math. So for epoch, plus batch size. Yeah. So as of now, we have given epoch is equals to 10 and we have batch size is equals to 8. Now, first of all, let's try to understand that what is the meaning of a epoch and what is the meaning of a batch size. So epoch simply means, in a layman term, epoch simply means that number of times we are sending the whole training data, right? Number of times we are sending the whole training data. Now, what is the total number of data that we have? So total number of data that we have is equals to 150. How much data will be considered as a training data? So 80% data will be considered as a training data, and 20% data will be considered as a testing data, let's suppose, right? So 80% data will be considered as training data and 20% data will be considered as a testing data. So training data is basically 80% of this one. Yes. So 120 data will be a training data, let's suppose as of now. And then for a validation data, we have basically a 30. So this is something that we are able to like a get. Okay. Now, so this is the training sample and this is the validation sample. Now, how many epoch that we have? So number of epoch is equals to 10. And what is the batch size that we have? Batch size is equals to 8. Okay. So what is the meaning of a batch size? So basically, meaning of a batch size is that after these many number of sample you are going to send, then in a backward propagation, it is going to update the weight. So weight new is equals to weight old minus eta loss with respect to W. Yeah. So weight update is going to happen after every 8 sample. After every 8 sample. So weight update is going to basically happen. This is the meaning of a batch size basically. If I'm going to give batch size equal to 2, so after every second record we are going to pass, it is going to update the weight. So again, frequently we should not update the weight and it should not be even a delayed one. It should be basically a balanced one by the way, right? So now let's try to do a math over here. So training sample was basically 120, testing sample was basically a 30. Now this training sample X test, we are trying to send inside my neural network. And over there, so we have again 80-20. So validation is equals to what? Validation is equals to 80%. And then for our training purposes, it is trying to use basically 80% and validation, it is trying to use a 20%. So here out of this 120, so 120 of 80% is 96 technically. So it's 96 and 120 of 20%. So it's going to be 24. So 96 data it will be using for a training purpose and 24 data it will be using for a validation purpose during a training. Simple, right? So here in one single epoch means when I'm going to send one complete set of the data. So in one single epoch, let's divide by a batch size. So these many times it is going to update the weight. So 12 batch and that is called as basically batch. So 12 batch per epoch. So this is called as batch size. So how many batch? Batch size is 8. So 96 divided by 8 is equals to 12 batch. So in one single epoch, we will be having a 12 batches. So in 10 epoch, obviously we'll be having a 120 batches. 120 batches by the way. 120 batches. So 120 batches means 120 times it will update the trainable parameter. So weight and biases. So this is the answer guys that you all will be able to find out. Yeah. So 120 times basically my weight update is going to happen. You can try to validate it even manually. That's completely fine. But yeah. And this is the meaning of epoch. Epoch simply means that number of times we are trying to send the whole data. Batch size simply means that after this many data, I'm going to update my weight. As simple as that. If batch size is equal to 1, in that case, after every single data input, it is going to update the weight. As simple as that. So with that, thank you so much everyone. Take care and see you again in my next lecture. Okay, so as now we are able to train the model. So now we can try to save the model because as of now, this model is available in my main memory. And once I'm going to shut down my system, it will not be available. So I'll have to do an entire process once again. Although this is a simple model, but yeah. So let's suppose we are talking about a very huge model, which took almost a 10-20 hour of time for our training purposes. So in that case, I will be in a problem because I will end up losing a time and my compute both and resources and my energy. So how I will be able to save a model? Let's try to understand that particular part. Yeah, it's very simple and I can try to save it in a multiple file format. So model dot save you can try to call. And here, so you can try to like give a model name that model.h5. So in this format, you can try to save it. So h5 is nothing but SDF5 format. SDF file format. This is the binary format in which you will be able to save the model. So here my model.h5 is available. Now, so model.save And then again, I can try to save it in a different format. So model dot Keras. So even in a Keras format, you will be able to save your model. So H5 format, Keras format, and there are other formats as well in which you will be able to save your model. So now my model is available as a physical file. I can try to read this model and I can try to do a testing on top of that model, or I will be able to do a inferencing. Inferencing means a prediction of the model. I will be able to do it with respect to this one. But yeah, so in this way or in this way, I will be able to save it. There are hundreds, not 100 I would say, but yeah, tens of other way or other file format in which I can save it. But as of now, I think this is more than enough to know how to save the model as a physical file. Okay guys, so now we are able to create a model, and we'll try to see that how we can try to do a prediction. Now, so if you remember, so we have used a standard scaler in a beginning itself, right? So we have basically used the standard scaler so that I will be able to standardize my data. So whenever you are going to pass your testing data, so obviously you have to do a exact same thing. So maybe a unknown data, or maybe a data from the same like X test and Y test that you have like taken. So even from there you can try to pass the data. But yeah, you have to do a same kind of a standard scaling. In an ideal way, what we do is that we try to store this scalar as a physical file. How? So you can try to import a job lib, and as we have used a scikit-learn library for doing a scaling, this standard scaling. So job lib is a preferred way. So you can try to call a joblib.dump, and then you can try to dump your scalar object as a physical file. So here scalar object, just try to dump it as a scalar dot job lib. Yeah, job lib. Okay. So now just try to dump it, and here so you will be able to find out even a job lib file. So scalar.joblib. Now this is been used for finding out the standard scalar. So now whatever new data which I am going to input, I have to even convert that data into a standard scalar format. Forget about the data conversion that we have done before. Now, so let's try to do a prediction. So first of all, I'm going to load the model. So to load the model, tf.keras physical model I'm going to load. Anyhow, I can try to load a model which is available in my memory by default. But no, I wanted to do a prediction with respect to a physical model, because this is something that you are going to deploy going forward, right? Not the above one. Training is done already. So tf.keras.models.load model, and you can try to give your model name with a like a directory. So H5 model I'm going to load, and let's name it as a model over. Let's try to name it as a model over here. So insert tf, and yeah, so it is going to load the model. Maybe I can try to call model dot summary. I will be able to see the summary. Same thing, I will be able to see it over here. Okay. Now, so once I'm able to load a model from the physical file, then we have to load even a standard scalar. So job lib dot, you can try to call a load, and then you have to load scalar dot job lib. This is again a physical file for converting or standard scaling the data. So just try to load it as a scalar. So these two are important. Okay. Now let's suppose I have to do a prediction, right? So I have maybe a input data A, and inside this data I have a sepal length is equal to 6.2, sepal width is equals to 2.8, petal length is equals to 4.8, and petal width is equals to maybe 1.8. Now this is the data. Now for this data, this is the input data. For this data I have to do a prediction. So how I will be able to do a prediction? Let's try to understand. So here first of all, you have to convert this data with the help of a scalar into a standard scalar format. A scalar dot, you have to call a transform, and then you have to basically pass this A data. So now this data has been transformed. Now you have to use the same object that you have used at the time of using a data, because it is going to take a mean of the data. So you should not use the new one, right? That's the reason. So we are trying to call the transform over here. Now this is going to give you a new scaled data. Yeah, this is going to give you a new scaled data, by the way. So once I have a new scaled data, I can try to call my model dot, there is a function called as predict, and then this new scaled data, try to pass this one. inside this model.predict. Now this model.predict is going to give you a prediction for all three classes, class number 0, class number 1 and class number 2. And it looks like that it belongs to a class number 2, right? Because this is having the highest value, right? This is having the highest value. But let's suppose I would like to see the class name, right? See the class name. So how I will be able to do that? So maybe I can try to call argmax, argmax. I can try to pass this entire value and prediction, which is nothing but a prediction probability on axis 1. Now it is going to tell me that, okay, so its index is equals to 2, 0, 1, 2. So basically 2. So this is basically a class which is, it is trying to give it to me. Now if I have to print the class name, so what I can do, I can try to wrap it up, and then I can say that iris dot target names. So here we have 2. So it is going to give me the name, right? So iris name nd array. Okay, so target name, it should be array. Okay, so what is the name? What is the class name? So class name is basically Virginica. So the data set that I have passed over here, it belongs to which class? It belongs to basically a Virginica class. As simple as that. Maybe I can try to convert this entire things, as a function. That's completely fine. So maybe def iris underscore prediction. So I can try to convert that as a function. So you can try to pass a new data. So as soon as you are going to pass a new data, so it is going to scale the data. So it is going to scale the new data. Same thing I'm going to use. And then it is going to do a prediction, and finally it is going to show me the class name. And this is something which I'm going to, so class underscore label, class label, it is going to show it to me. And I'm going to call a return what? Class label. So this is the function which I have created. So where you are going to pass a new data, it will do a scaling, same thing, right? It will try to find out the prediction probability for all three classes. Then it is going to give you which class it belongs to, technically the array which is having the highest value, array index which is having the highest value, and then we are trying to fetch the target name out of this one. Yeah, target name out of this one. So now if I'm going to call iris underscore prediction, and if I'm going to pass my new data, so let's copy this data. If I'm going to pass my new data, it is telling me that it belongs to a Virginica, right? It belongs to a Virginica. Same thing, same output. So in this way, I will be able to do a prediction, and in whatever format I will be looking for my output, I can try to return it. So with that, thank you so much, everyone. Take care and see you again in my next lecture. Okay, so we have done a lot of work, and we have already created a .h5 file or Keras file. And let's suppose if I would like to see visually that how this entire model looks like once again. I have shown you already how to visualize it, but in a different way, if I would like to visualize it, how I can do it, let me show you that part as well. So there is a platform called as NET RON Neutron. Yeah, Neutron. Just try to go over there, right? Just try to go over there, and over here, try to drag and drop your model. Yeah, try to drag and drop your model. So I had basically test UV. Inside that there is a H5 model, right, that we have. So try to drag and drop this model, and here, so you will be able to see the model. We had the input layer, right? You will be able to see the detail over here. In total, we have 165 trainable parameter. We have a dense layer, which is a hidden layer. Again, what is the dimension of this one? So we have 10 unit of a neuron. I can try to even zoom in from here. So it's already maxed zoom in. So vertical. Yeah. So we had basically 10 units. So yeah, it is able to show it to me. You can see the value of the biases. This is the value of the biases after a training you are able to see. And you will be able to see a value of a kernel, which is nothing but a weight, right? Weight. So I have already shown you how to see a weights. So even after a training, you will be able to see a weight, so weight and biases value. And even over here, you can try to copy, you can try to observe it. Now, so here we have basically like a 8 biases. So I can see the value of the biases. Initially, it was 0, absolutely 0, right? Initially, it was absolute 0, but now I'm able to see a value. Now I'm able to see a value of these biases. And as well as I will be able to see the value of the weights, right? Value of the weights I'm able to see, as you can see, right? So for every layer, guys, for every layer, we are able to do a postmortem even after doing a training, right? Even after doing a training, everything is pretty much visible to me, right? Pretty much visible to me. So like I said, nothing is a black box. Everything you will be able to observe, everything you will be able to check, everything you will be able to see. So just try to dump your .h5 file over here, and then you will be able to see a model visually, layer by layer, layer by layer, layer by layer, and then you will be even able to do an investigation that what is a value, what kind of a things it has done, in what layer it has done what, everything, right? Everything. So it's a great, like a, you know, postmortem resource, you can say, or platform, which has been given to you on Neutron.app. So please go over there, try to load your model, and then layer by layer, try to do some sort of a investigation. So hope you all are liking this entire series. So with that, thank you so much, everyone. Take care, and see you again in my upcoming chapters. Okay, so welcome back once again, guys. Now in this lecture, I'll be talking about a new project with respect to a deep learning. So where we are going to build a neural network, and we will try to solve a regression problem, by the way. So where we will try to see that how my deep learning model will be able to learn, and it will be able to do a prediction. And if you have already done a previous project, then obviously it is going to give you an advantage. Not just that, so we are going to even productionize this particular project, and we are going to test an API end to end, right? End to end, we are going to test it. We are going to productionize it on a render after converting my project as a Docker. And then I'm going to even show you that how you will be able to test this API with the help of Postman. I have already done that in a previous project, but again, I'm going to show you the exact same step with respect to this particular project. So first of all, guys, let me share my screen, and let's go ahead and open up a VS Code, Visual Studio Code. And let's move ahead inside this project in a step-by-step manner. So here, what we are going to do. So basically, we are going to build a energy consumption project. So first of all, open up a new folder, a fresh folder, and then try to create a new folder. I'm going to give a name to this folder as a energy underscore consumption. So this is the project which I will be building. I will be doing in a step-by-step manner. Okay. So for any project that we are going to build, the very first step that we have to take is place a requirement.txt file. I believe we all are aware about it, right? Because this is something that we are doing again and again and again. So requirement.txt file I'm going to place. Now, once requirement.txt file is available over here, now let me build an environment. So how I will be able to build the environment? Simple, right? So here, I can try to do a conda create -n, and I can try to give an environment name energy cum, energy consumption. Yeah, energy eng I can try to give, and then Python is equals to 3.10, as you are going to use a TensorFlow. So obviously Python 3.10 is the stable one. Otherwise, it is not going to work. You can use a lower version as well. That's completely fine. So energy consumption, and let's see. So we'll try to build the project one by one. Okay, so this environment is created. Now just try to do conda activate. Fine, conda activate. Now CLS, clean the screen, and in this directory I have a requirement.txt file. So just try to do pip install, which is a standard approach, right? So pip install -r requirements.txt, and whatever I have mentioned inside my requirement.txt, it is going to install each and everything. Sorry, I think it has not activated my environment. Oh, I think I have not activated my environment, guys. So let me check. Command prompt conda activate eng underscore cum, and now I can do pip install -r requirements.txt. So now it's installing. Yeah, as you can see, because previously it has just given me like a requirement already satisfied within a fraction of a second. So I had a doubt that maybe it has not like installed all these new things that I have mentioned inside my requirement.txt file. Okay. Now, meanwhile, what we can do is that we can try to look into a data set, that how my data set actually looks like. And I'm going to place my data by creating a data folder. So let me create a data folder over here, and inside this data folder, so I'm going to keep my energy file. So this is the data file which I have created. My environment is ready, up and running, right? My environment is ready. So I'm going to close this part, and now let's try to talk about the data. Let me open up this data into a Excel sheet so that it will be more visible to all of us. Now, if you will look into this data, so we have a temperature, we have a humidity, we have a wind speed, we have hours of a day, we have a day of a week, and we have a energy consumption. So this is the small data set that we have prepared. The whole idea behind this data is to teach you that how to train a deep learning model for a regression. Means basically we have to predict energy consumption. At the end of the day, this is something that we have to technically do. Fine. So now let's talk about data set a little bit. So what this data set is all about and what it is talking about. So temperature, it's available in a degree centigrade, by the way. So temperature is a current temperature, you can say. Humidity is a current humidity percentage it is trying to showcase. Then wind is basically a mile per second, you can say. Wind speed is given to me. Hour of a date will vary in between 0 to 23, 0 hour till 23rd hour. Days of a week, so it simply means wherever 0 is mentioned, like 0 is mentioned, it simply means that I'm talking about a Monday. Wherever 1 is mentioned, I'm talking about a Tuesday. Wherever 2 is mentioned, I'm talking about a Wednesday. So this is how a day of a week is been labeled. And then energy consumption. So energy consumption is basically available into a kilowatt, right? In a kilowatt, this is available to me. So now what we have to do, so we have to consider these columns as a X column, right? And we have to consider this as a Y column, and we have to build a regression model. So where if I'm going to give these as an input, temperature, humidity, wind speed, hour of day and day of week, if I'm going to give that as an input, it should be able to predict energy consumption. It should be able to predict energy consumption for me, a very simple use case. Like I said, so data is not my focal point over here. My focal point is to show you that how I will be able to build a model, how I will be able to deploy it, and then how I will be able to test it. So that's my like a whole target over here. So fine, this is my data set. I'm keeping my data inside my data directory. Now let's close it. Yeah, let's try to close this particular data wala part. Now, so requirement.txt is done. This one is done. Now what I'm going to do is that I'm going to create a file called as train model.py file. So train underscore model.py file. So which is going to give me a model, right? Which is going to give me a model, and this model I'm going to use it to deploy somewhere, right? This is something which I'm going to use to deploy somewhere at some places. So to do that, let's do it quickly, guys. So here, right? So here, first of all, we are trying to do an import. So we are trying to import pandas, NumPy, scikit-learn, TensorFlow, and all those things. Parallelly, let's do one thing. So let's try to open up a test.ipynb for explanation purpose, by the way. Yeah. And try to select the same kernel. So energy consumption kernel, so that our environment is going to be intact and it is going to be same. So now let's try to import all of these things, and there is no issue except Jupyter notebook. So it is going to install a Jupyter notebook. Just wait for a couple of minutes, guys. It will be done. This is a regular process that we do all the time. Okay, so it's done. Now let's try to import. So import is successful. There is no issue at all. Now what we are going to do, so we have to load a data, we have to read a data. So simple, we are going to use this syntax. So this is my data directory, and I'm trying to call os.part exist if data part exists. So data is available inside this folder. Just try to like assign this particular variable and check it basically. And then if all is well, then try to call pandas.readCSV and try to pass a data path. You can remove this piece of the code. That's completely fine. This is just for the validation purposes. Now, once this part is done, so I have to create my X and I have to create my Y. My X is going to be these column and my Y is going to be energy consumption column. So let's try to create my X and Y. So here, what I'm trying to do, so I'm trying to use this one for my X and I'm trying to use this one for my Y. So I'm saying that okay, so try to select all the rows and just try to select all the column except minus one. Minus one means except the last one. So this is going to be my X and this is going to be my Y. If you would like to test it, you can try to test that as well. So here I can try to test it and maybe I can try to check that what is my X, by the way. So my X is all this first 1, 2, 3, 4, 5. So this 5 column till a day of a week, as you can see, like till a day of the week. And then if I'm going to test my Y, so my Y is going to be the last one. So my Y is going to be the last one. Fine. So X and Y segregation, I'm able to do it. Now, once my X and Y segregation is done, then we can try to divide our data set. We can try to divide our data set into train and test. And as we can see that my data set scale range is varying a lot for all of these columns, right? All of these columns, temperature, humidity, wind speed, hour of day, day of the week. So maybe I'll end up creating a bad model, overfitted model, underfitted model. So keeping that in a mind, we will try to standardize our data set. So we are going to call a standard scaler as well. So first, let's try to split our data. And then, so X train test split, I'm trying to call standard approach. Once again, we have done that hundreds of times in a past. And then we are trying to call a standard scaler. We have done this as well, again, more than 100 times, right, in a past. So we are trying to standardize this particular data set. Now, once this standardization is done, we are going to basically build a model. We are saying that okay, so in a very first layer, I'm going to have a 64 neurons. In a second one, 64 once again, I can try to add more and more layer over here. And then in a last layer, I will be having only one neuron. And I'm not keeping any kind of an activation function because I'm not looking for a probability, right? I'm looking for basically a final outcome. I'm looking for a regression. So this is a difference you will be able to find out between a classification model and a regression model. I'm looking for some value. So whatever value that I will get from the previous layer, combine it, give it to me in a last layer. So 64 neuron, I'm trying to pass my data over here. And then this is the model. If I would like to check that what is my model size. So maybe let me define all the above part over here. So yeah. So here, if I'm going to call model.summary, so it is going to show me the architecture that, okay, so this is the number of parameter which I'm going to train. And this is the first layer, second layer, and this is going to be the final output layer. So this is a very simple model which I have created, right? And this is something which I'm going to train upon. Yeah. So I'm going to train this particular model. Now, to compile this entire model, so what we can do, so we can try to call model.compile. We can try to pass a optimizer loss wise. So mean squared error, we are going to pass as we are talking about a regression problem. We are not talking about a classification problem. So my loss function is going to be changed and optimizer is going to be same. Yeah. Standard approach once again. Now, so once it's done, so we are going to call a model.fit, which is eventually call my training. So I'm going to pass my X train and Y train. 50 times I'm going to pass the whole data. So I'm going to update the weights after every 32th data, right? This is the meaning of a batch size and validation split. So 90:10, in which I'm going to divide the data for the validation during a training. Now, once it's done, right? Once it's done, so we can try to evaluate this model. So model.evaluate, we can try to pass X test and Y test, and it is going to evaluate it and it's going to give me loss and it is going to give me mean absolute error. Simple, right? And then once this part is done, I can try to call a model.save, as you can see. So model.save. So I'm going to save this model into a H5 format, Plus I am trying to do a standard scaler. So I have to save this particular instance as well, so that at the time of testing, I will be able to call it. So I'm going to basically save this one. Now, if everything is going to work fine for me, and again guys, so I'm not like, calling this one, or I'm not going to explain line by line. I'm not writing a code line by line. The reason is very simple, that we have done all of these things 100 times, right? 100 times. So now we are in a position where we can understand all of these things in one single go. Now let's do it. So let's try to call the training part of this model. So CLS and Python, Python, Python train model.py file. And let's see. So if we are going to get some issue, hopefully will not. Okay. So we are able to train the model, it looks like, and we are able to save the model. So h5 file, I'm able to save it. And then this scalar.save, or maybe I can try to use maybe a job lib over here, which I'm already using, right? And I can try to save it as a pickle file, .pkl file. So in a pickle format, I can try to save it, or even in this format, I can try to save it. Now, once this model has been saved, right? So I just need these two files, one and this two, right? I just need these two files. I can try to pass the data. Which data? So I can try to pass a data for this one, and I will be able to test it, right? I will be able to test it. So I can do a model testing. I can do a model testing over here. So now to do a model testing, I would like to call these two things, these two models, scalar model and energy consumption model, with the help of FastAPI. Yeah, with the help of FastAPI. So I would like to basically do a testing. So to do a testing, maybe I can try to create a new file called as app.py file. And we all know that what is the meaning of API, right? Kind of a route where we will be having some function sitting over there. So with the help of route, so we can try to call it from anywhere. And that is something called as API, right? That is something called as API for me. So here, right here inside app.py file, so try to call all the standard library. So FastAPI, I'm trying to call, and then try to create an object of a FastAPI. Simple, right? Object of the FastAPI, and then try to load a model. So which model? Energy model.h5. This is the model, and scalar model. Try to load these two models, so that first of all data will go here, and then it will try to go over here to do a prediction. And then just try to make it compatible with the pydantic. Yeah, pydantic. So we are going to pass a data as a list. It is going to check a type check, by the way. So this is basically a pydantic I'm trying to call. And then there is a predict function which I have written. So predict means, so it is going to take whatever data that you are going to pass. So it is going to take it. It is going to convert that into a compatible format. Then scalar.transform, it is going to call a scalar, the model which I have already saved. So it is going to basically like transform it, and then it is going to pass this scaled data into a prediction. I will be able to get a final return. Very simple, right? Now, if I have to convert that in an API, so I have to simply write @app dot post, and then here, so I can write /predict, only this much, right? Only this much I have to write, and automatically, right? Automatically this entire things will be exposed as an API. Once I'm going to run it in my local, so it will be exposed on my local host. And once I'm going to like host it on a cloud, it will be available on a cloud. So here, what we can do, we can try to test it first of all, that whether it is working for me or not. Now to test it, I can write over here that UVCon for a FastAPI like a execution. I have an app file, so consider that as a app, and then basically try to call reload. Now if everything is going to work fine for me, so I will be having my API. Otherwise it is going to give me some issue. Full object, Keras matrices, class name, function. Okay, so it is telling me that could not locate a function. MSE make sure a custom class R. Fine. So model dot predict. Okay, so let me fix this issue, by the way. or I can try to even go to this particular URL and I can just try to do a little bit of check over here. So this URL /docs docs, and yeah, so site can't be reached. So basically my API is crashing. Let me fix the issue. Okay, so just a small fix as per this error. So inside my training, so I have used loss is equals to MSC. It is not able to recognize it. So let's try to change it as a mean squared error in this way, so that it will be able to recognize it. And then just go over here and delete these two files. Yeah, so I've just deleted it. And then once again, so let's try to do a training. So here Python train model.py file. Within a fraction of a second it is going to train, and I will be having my new model, new version. So I've just done this change, guys. It was not able to recognize it. It was giving me an error for that. So CLS, and then I can try to run UVcorn app, my backend app, right? I don't have to do any kind of a changes in that one. And let's see. Yeah. So now I believe I'm going to get a good news. Application startup complete, and now just wait for a couple of more seconds. So I will be able to see something at this particular URL. Okay, so now if I'm going to click on this URL, I'm able to see a predict function, right? I'm able to see the predict function. And here, so I can try to pass my data and I will be able to get my final output. So here I can try to pass my data as a list. So whatever like a data which I would like to pass, I can try to pass it. And I can just try to call try this out, and maybe I can try out passing some of the data as a list over here. So let me do it. So let me try to like pass this data as a list. So here maybe I can try to use one of the data, paste it here, comma, remove all of these white spaces which we have in between. So comma, and then comma. So this is the correct format that we have now. Yeah, this is the correct format that we have now. Now I can try to click on execute. And let's see, so whether I'm okay. So prediction wise, I'm able to get this as a energy consumption. So 27.940. As per my data, it was supposed to be 38.7. But yeah, we are able to build a model, a bad one. Obviously, maybe we can try to increase a number of layers over here. We can try to change maybe epoch. We can try to change maybe a batch size. There are a lot of scope that we have. And based on that, I will be able to do a lot of fine tuning. But yeah, so we are able to build a model and we are able to see the prediction with the help of this FastAPI. So once I'm able to see the prediction, so maybe I can try to test this same API with a Postman. And in my previous lecture, I have already talked about a Postman. That Postman is a tool by which you will be able to test. You will be able to test the API. So let me open up a Postman, and I have already talked about that, how to do installation of the Postman in the previous lecture. So here I'm going to open up a new tab. I'm going to select a post as it's a post one. And then I'm going to pass this URL. So this local URL over here /predict, fine, /predict. Now header. So maybe I can try to leave it as it is. Body. So I can try to use a raw, and I can try to pass a same data which I'm trying to pass here. Same data which I'm trying to pass here inside a body. So let me pass this data and then click on send, and we are able to get a prediction once again. So even with the help of Postman, we are able to test this entire application. Very simple, right? So just try to pass this URL. At this URL, I have a function, as we all know that at this URL, I have this predict function. It's running on my local host, on my local system. And here, so yeah, 200 means it's a good output that we are able to see. We are able to get it. Now, once we are able to do a testing with respect to a Postman, now what is next? So next, maybe we can try to deploy only this API. Yeah, we can try to deploy that as a API. Where? On a render. So let's close everything. So let's close everything. Yeah, let's close this one, and this one. And let's try to talk about just a deployment. So here I can try to create a new folder, and maybe new folder is not required. So here itself, I can try to create a new file, and I can try to write it as a Docker file, DOCKERFILE, Docker file. So here I'm going to prepare my Docker file. Now what this Docker file is going to do, so it is going to help me out in terms of doing a deployment. And same thing we have seen even in my previous class. So here inside this Docker, so I'm going to install 3.10 along with the Debian operating system. Inside this, I'm going to create a working directory called as app. All this local file, I'm going to copy it inside this one. And then first of all, I'm going to run requirement.txt, and then this is going to spin my machine, and my app will be up and running at this particular location, right? At this particular location, my app will be up and running. Okay, so that's cool. Before that, so let me go to my app.py file, and here, so I'm trying to load a model, so which looks fine to me. Just a minute. So as such, I don't have to do any kind of a changes over here. So everything looks fine inside my app.py file, and technically I just need app.py file. Other files are not required, but even if you are keeping it, it is not going to harm you. Yeah, it is not going to harm you. So let me run this Docker. First of all, let me test this Docker, and then after testing this, or maybe even without like testing this Docker, so I will be able to push this entire thing inside my GitHub repository, because in my previous example, I have already tested a Docker. So if you have missed that, so please try to go ahead with the previous lecture in which I was already talking about a Docker. There is a separate lecture you will be able to find out just with respect to a Docker. So maybe without testing it inside my local, because I'm like 100% sure that it is going to work. So let's try to push this entire code base inside a GitHub repository. So what I will do, I'll try to open up my GitHub, and here, so I'm going to create a new repository inside a GitHub. So new, and then energy is a repository which I'm going to create. Now inside this repository, I'm going to push my entire code base. So first of all, git init, git add. So here, CLS, clean the screen, and I'm going to do git init, and then I'm going to do git add everything. That's the reason. So we have a dot, and then git commit -m message. This is my energy project. So fine, commit is done. Now what we have to do, so we have to call a branch main. So branch main, call it, attach a branch. Already steps are given, and we have already done that hundreds of times. And then finally push it to origin main. So push it to origin main. So once I'm going to push this entire code base, now if I'll go and refresh this GitHub repository, I will be able to find out all of these files. Yeah, all of these files I'm able to find out. Now what we are supposed to do, guys. So now we can try to open up a render. So you go to Google, render, and just go to this render.com, go inside the dashboard. If you have not logged in, so please try to log in. Otherwise, if you have already done the project from the past, which I have already taught you, so maybe you must be aware about the render. If not, just try to sign up inside the render platform. It's a platform, so which is going to give you an instance where you can try to deploy it, but a shared one with the limited resources. And again, so you don't have to add a card if you are not looking for a dedicated environment. So here, just try to click on new, just try to click on web service. And then from here, so you can try to select your GitHub repository in which you have a code. So energy is a repository. I'm going to like a select, and then language is equal to Docker, because I have a Docker image, and then I don't have to do anything. I can select a free over here, and then simple deploy web service. This is the only step which is required for this particular project. And if everything is going to work well for us, it will take at least 4 to 5 minutes of time. and you will be able to see your fast API up and running at this location / predict. You will be able to do the exact same thing that you are doing it with respect to a local URL. Simple, right? So just wait for 5 minutes of time and then we will be able to see the final deployed version. Okay, so looks like my API is live, by the way, and I can go and check over here at this URL. So /docs, my fast API seems to be live on this live URL. Yeah, I can try to do even a prediction. So just to do a prediction, I can click on try this out and I can try to pass the same data which I was trying to pass and execute. Let's see what is the outcome I'm going to receive. So prediction is 27.940. So yeah, this is the live API. Now I can try to integrate this API with any of the front-end application or any other application basically, right? So my API is live. I can try to do even a testing with this API. So maybe I can go to a Postman. Instead of using this URL, which is a localhost URL, I have changed it to my deployed URL. And then if I'm going to send, it is able to do a prediction, right? So my fast API is live, it's working, it's up and running, it's deployed. My backend is technically deployed. And yeah, so I can try to share this API with anyone. I can say that, okay, just try to do a post request and try to pass this data. Every one of them will be able to use my model. So pretty much amazing for all of us guys. We are able to build another project. Let me summarize this part, by the way. So let me open up my Scribble ink. So what is the step that we have done, right? What is the step that we have done? So first of all, obviously step number 1, train the model, right? So after training a model, basically, we are going to expose it as API with the help of obviously fast API. And when we are trying to train the model, so basically we are talking about an artificial neural network based model. Obviously this is the regression model that we have used. Now step number 3 that we have taken over here, that test a model in local and with Postman. 4th, Dockerize the solution. 5th, deploy on render. 6th, test once again. Simple, right? So this is the step that we have followed in this entire project throughout. And yeah, successfully we are able to complete this particular project. The whole idea, the whole intention behind showing you this project was very simple. To teach you that how in an end-to-end manner we can try to create our own API, we can try to train our own model, whether it's a small, it's a big, that's a different story, because with every model that story is going to change. With the data set, it is obviously going to change. How we can try to Dockerize this, obviously we are able to learn that part as well, and then eventually how we can try to deploy it on a render platform. So each and everything we are able to understand. So with that, thank you so much everyone, take care and see you again in my upcoming chapters.